5 minutes लाइव ठीक है जी 5 मिनट अच्छी
I change this. Which one? Okay.
Press a B.
Okay.
And this is the letter.
This one, red one.
Yeah.
Two more minutes then
Okay.
Okay, so welcome all to the last day of ISM. One announcement before we start. Someone has left his or her bag in the dining area and it's still waiting there for you. Is that right? Yeah, NISER. Okay, so our first talk would be by Anindo Sinha and he'll reimagine the origins of string theory.
Okay, so thank you very much, and I'd like to start by thanking the organizers for organizing this wonderful conference. So I'm going to talk about reimagining the origins of string theory. So we are in the day of LLMs and AI, so obviously I did the obvious thing. I asked ChatGPT what it thinks of string theory, and I asked it to explain it to me using a cartoon. This is what it produced. And this is the kind of criticism that you probably frequently face. So it says that call me when you're down to 3 vacua, not 10 to the power 100. So one of the existential questions that we ask is how rigid is the string framework? By rigidity, I mean how mathematically internally consistent is the string framework. And to address this, I'm going to tell you about how string theory originated. So string theory originated with an attempt to explain hadron scattering data. And what happened is that This was pre-QCD days, and people were really trying to understand experimental results in pion nucleon scattering. And there is a famous paper by Dolan, Horn and Schmidt, DHS, from September 1967, which suggested mildly, and I'll explain why I say mildly, that experimental data for pion nucleon scattering needed a scattering amplitude. So this is scattering amplitude as a function of the Mandelstam invariance, S and T. And this particular amplitude in pion nucleon scattering had two-channel symmetry, exhibited a peculiar feature where the amplitude could be expanded either in terms of the S-channel poles or in terms of the T-channel poles. This was what they suggested. And this is what is called duality. In the old days, this is what is called the world sheet duality in modern language. And this led to the invention, creation of what are called dual resonance models. And Veneziano in 1968 found an amplitude which had the correct Regge behavior, which turned out to be the Euler beta function. And in modern language, this is what we interpret as 2-to-2 open string scattering. And this was consistent with bootstrap constraints. It had the correct Regge behavior. It solved crossing symmetry. And all this is beautifully reviewed in a set of reminiscences in this book called The Birth of String Theory. I happen to be of a certain age where I'm beginning to get interested in existential questions and historical origins of things that I'm doing. So I actually really like reading this book. So this was the experimental data. Let's just go through this slide a little bit. So if you plot the this you can mentally replace by the angular momentum J versus m square, and you plot it for the light mesons, then you will see that there are various trajectories. You will see various resonances appearing on these trajectories, and they are all appear to lie on approximately straight lines. These are called Regge trajectories. The intercept of the Regge trajectory is 0.5. High energy scattering also suggests that there should be something called a Pomeron trajectory. You don't see any particles on this Pomeron trajectory, but it has an intercept of 1. The other notable feature for the Regge trajectory is so this is for the some leading Regge trajectories. Yeah. Yes. That's right. So I'm considering the rho trajectory, which is usually what is plotted, and that is the leading Regge trajectory. So the rho and its subsequent other daughter particles, the daughter particles are going to lie on this trajectory. And so you're right. I mean, there will be other Regge trajectories with increasing slope. Right. So they are approximately parallel. With slightly different intercepts, but so the point is that there are many scattering amplitudes which exhibit this kind of a linear behavior. The point, another point is that these are resonances, and resonances mean that they have a width, so they have a finite decay time. So in fact, beyond say spin 6, if you open PDG, I don't know how many of you ever opened PDG. How many of you have opened PDG? Okay, very good. So some of you have opened PDG. You will see actually that beyond spin 6, you're not going to see anything because the width of the particle has become so big that you won't be able to see a Bright-Wigner type resonance. And another point which wasn't known at that point in the early days is that there is something called the F0 trajectory, which is this. This is a spin 0 particle. This has got a large width, and this trajectory is problematic. In fact, this trajectory does not look like this. This trajectory looks almost horizontal, and we should keep this in mind. How to take this into account is not clearly understood. And this is what is called a Chu-Frotchi plot. If you open old textbooks or even modern textbooks to sort of see how the Regge trajectory is taken into account, this is the picture that you should have in mind. So there is this whole tower of particles that is exchanged at a time. This is what is called a reggion. And this gives a high energy scattering cross section, which is governed by the intercept. So the intercept here, this 0.5, is what plays a role here. So this total cross section is related to the forward limit. And when you actually see the total scattering cross section, you will see that indeed initially it drops, but then it begins to rise as well in certain cases. So these are the kind of experimental data that is available. And because they rise, this alpha 0 has to become bigger than 1. And the trajectory that gives you alpha 0 bigger than 1 is what is called the Pomeron. Pomeron in modern language is a closed string, state. So one thing that people started doing is that they started making what is called a narrow resonance approximation. So they pretended that the lifetime of the particle is infinity, and they wanted to actually see whether they managed to get analytic mileage from them. You mean the Froissart type behavior? No. So that is there is no conclusive evidence that there is a Froissart behavior in the proton scattering. Yeah, but it is the Pomeron, the way that it appears in string theory is through through closed strings. So in that sense, I mean, I will shortly review that string theory actually does not give you the correct intercept. So actually, we don't have an understanding of these results from string theory. Yeah, that's right. Yeah, exactly. So after Veneziano's paper, it's fascinating to actually compare two very famous papers. One of them is Veneziano's and the other one is Weinberg's. So Veneziano's paper came out in 1968, Weinberg's paper came out in 1967. And this was pre-internet days. So as you can see, Veneziano's paper citation is in red and Weinberg's paper citation is in blue. Weinberg's paper citation famously did not take off until 2-3 years. Veneziano's paper citation took off immediately. In 1969, there were 165 papers that were written that cited Veneziano's paper. So there was really a lot of activity, and it's worth trying to figure out why there was so much activity. And in fact, you can see that after 1979, there was some drastic drop in the number of citations. In fact, some of the years Veneziano's paper just had 2 or 3 citations. And now, presently, it's beginning to take off a little bit more because there are multiple groups in the world who are re-examining the question of bootstrapping string theory. So this is what happened from 1969 to 1972. So this is sort of a one-slide summary as to why there was so much activity, why people took so much interest in what happened. So around 1969, the attempt was to come up with a theory to explain hadron physics that was consistent with S-matrix theory. So Veneziano's model was a bit too simplistic, and so people tried to play around with the model. So there is something that people invented, which was called the Lovelace-Shapiro model, which was more consistent with data. So people wanted to come up with a phenomenological understanding of hadron physics. But what happened is, because of self-consistency, one needed to actually also talk about n-particle generalization. So Bardakci and Ruegg in 1969 found 5-particle generalization. Again, if you open Bardakci and Ruegg, you'll see that they were talking in the language of the integral formula, or the generalization of the integral formula for the Euler beta function, and how you could actually change that to get the correct Regge behavior. Soon after this paper, it was generalized to n particles by Koba-Nielsen, and I will review why these generalizations are important. And this happened, both of these happened in 1969. So the n particle generalization is something to keep in mind. These generalizations pass consistent factorization checks. I will also review what factorization means. And these were performed by Fubini and Veneziano and Bardakci and Mandelstam also in 1969. Fubini and Veneziano's paper found that there is a Hagedorn growth in the degeneracy, and the degeneracy went exponentially using the Hardy-Ramanujan formula. Around the same time, to sort of systematize factorization, the oscillator picture was developed by Fubini, Gordon, and Veneziano, and also separately by Nambu in 1969. There was some rough hint that there should be some underlying world sheet, or what we conventionally now learn in textbooks, the string picture. This was again the same year, but the utility of this picture was understood much later. Using the oscillator picture, field theory vertices and propagators were found. So this was first done by Scuto, and then this was an asymmetric cubic vertex. I'll again tell you what these mean. And then it was generalized by Kaneshi, Schwemmer, and Veneziano, which is called the CSB vertex again in 1969. And then Virasoro found that for the intercept 1, which was sort of the only thing that was consistent, the intercept had to be half, but the consistency said that the intercept had to be 1. An infinite number of null states could be found, and this is sort of analogous to the gauge freedom that removed the longitudinal modes of a photon. Then, because of the cubic vertex, loops were constructed, and then to remove these unphysical states, these DDF type vertex operators were constructed, which had positive norm, followed by the no-ghost theorem. And this the critical dimension of bosonic string theory, that it is d equal to 26, was actually found not from the no-ghost theorem first, but it was actually discovered by Lovelace in 1971 by looking at non-planar loop diagrams. So these loop diagrams had unphysical singularities, so there was some branch cut, and that became a pole, which now can be interpreted as a closed string only for d equal to 26. Okay.
Step 4 from step 3 was
the oscillator picture?
Yeah.
So this oscillator picture actually systematized factorization. So I will tell you what factorization means, and then how the oscillator picture makes it easier to see. Yeah. So all these developments are beautifully summarized in Veneziano's reminiscence in this The Birth of String Theory book. So this is what factorization means. So this is something that you see in quantum field theory. This is not the kind of vertex that we're going to encounter for the Veneziano model. You only encounter cubic vertices, but suppose you have incoming states P1, P2, P3 going to Q1, Q2, Q3. Then on the residue of the intermediate, when the intermediate state goes on shell, should factorize into a function of the incoming momenta times a function of the outgoing momenta, and also this should be Lorentz invariant. Okay. So the Koba-Nielsen amplitude gave hints of this underlying harmonic oscillator structure, because that what happened is that the n particle generalization, when you try to examine factorization, it gave rise to or sort of begged for an reformulation in terms of a harmonic oscillator, which later became the quantized modes of the of x mu on the world sheet. And this was initially derived using coherent state techniques. So if you look at the old papers, in particular, if you look at CSV, Kaneshi, Schwemmer, Veneziano, they actually cite Clauder and Sudarshan's book as a standard reference to learn these coherent state techniques. And this is what led to the vertex operator picture. So what happened, so answer to your question is that once the oscillator picture was developed, you were able to associate a vertex which only depended on the incoming modes, and then the outgoing states were in terms of a vertex that depended on the outgoing modes, and as a result it naturally had a factorized structure. So this oscillator algebra took on this form where you introduce this eta mu nu. So eta mu nu is a Minkowski metric. So there is a minus in the signature. It's minus plus plus or whatever, and so it's because of that that leads to the question of non-unitary states. This oscillator picture also gave us an understanding how the Hagedorn degeneracy, which was predicted by Hagedorn using statistical mechanics bootstrap or statistical bootstrap before the origins of string theory. Yeah, that is because K mu is the 4 momenta or whatever. So they were talking in the language of 4 momenta because they did not know that D should be equal to 26. So K mu should have been associated with an oscillator, and then you have to contract that mu. So the natural thing to do would be to introduce an oscillator with an index mu. Yes. The other thing is, let me go through the importance of n particle. So suppose, so this is the 5 particle picture that you have for the generalization of the Veneziano amplitude. So I have labeled by 0 the lightest state and m by heavy state. So 2 particles come in, exchange a heavy state, light particle goes out, and again there is an exchange of heavy particle. So if you factorize, you can, so what are the cubic vertices that you see here? So you see 0, 0 m, and you also see 0 mm from the 5 particles. So these are the 2 cubic vertices that you can actually read off, or with some work you can actually work out from this picture. Using these vertices, you can actually construct a one loop diagram. Okay, and you can study perturbative unitarity for this one loop diagram. But if you really want to do any loop, you have to derive the MMM cubic vertex, where you have heavy states, all 3 heavy states. So that in order to do that, you have to go to at least 6 particles, because the 5 particle does not give you MMM. The 6 particle, this particular thing actually gives you MMM. So in the language of CFT, which Pratham is going to talk about in the next lecture, this is called the comb channel. And this is because it looks like a comb if you arrange the legs appropriately. And then this is called the snowflake channel, because if you drew it a little bit better, it looks like a snowflake. But this factorization actually gives rise to the MMM cubic vertex, and this is what is called the CSV vertex. It enables you to construct multi-loop amplitudes. Okay. Yeah. You could do that. So then you'll have to actually solve the bootstrap equation with the 4 the heavy particle as the external state. So this is not how historically it was done. Actually, people guessed the n particle generalization, and this is actually a challenge. So if you're thinking of sort of revolutionizing string theory and winning a Nobel Prize, then the thing that you have to do immediately is to come up with an n particle generalization and come up with these field theory rules. Okay. So this is what actually makes it much harder, because these were all guessed. There wasn't a systematic procedure of sort of self-consistently deriving all this. But, and there is a but obviously, these early attempts to construct a physical model to explain hadron scattering experiments failed. And the intercept was wrong. Fixed angle amplitudes were exponentially soft, contradicting experiments. Okay, so this is one of the drawbacks that these kind of amplitudes, string theory amplitudes had. And of course, introducing supersymmetry also did not help. You didn't get an explanation for hadron scattering. Now, this last point, fixed angle scattering being exponentially soft, in fact has a potential resolution, and this was provided by Polchinski and Strassler via the ADS-CFT correspondence. This paper actually hints that a warp factor can convert this exponentially soft behavior to a power law, and these are kind of qualitative arguments. But one thing to keep in mind is that if somehow this mechanism turned out to be unique, that you require a warp factor to convert an exponentially soft behavior to a power law, maybe this could be an indirect hint that you must have extra dimensions. Now, there have been sort of lots of bottom-up approaches using the ADS safety correspondence. This is a sample paper from 2021. And by bottom-up, I mean that you put in sort of arbitrary potentials by hand to come up with some kind of quantitative, semi-quantitative explanations for hadron scattering, hadron spectrum, so the Regé spectrum. But these models are all phenomenological with no embedding in string theory, and no single model explains all. And moreover, there is no ADS safety understanding of the amplitude itself so far. Real QCD will probably be some not yet understood deformation of ADS and potentially quite stringy. So we really don't know how to do this from first principles. So yeah, of hadron scattering, pion nucleon scattering. So this was the phenomenological motivation for coming up with the Veneziana model. So at this point, you ask ChatGPT to summarize the state of affairs, and it comes up with a cartoon like this. So how have we done with connecting with experiments? And it says we have made huge conceptual advances. The snail has almost finished the prelude. So this is string theory and this is experiment. And I draw your attention to the fact that the snail is pointing at the opposite direction, not towards the experiment. So so indeed, it's so ChatGPT seems to know where string theory is heading. And it has also introduced a new terminology. It says that string theory progress measured in snail's lengths to experiment. So what do we do about this? So one thing, there are two things that you can do. Either you stick to the top-down approach, you take the rules of string theory very seriously, and then you hopefully you find the correct vacuum or a correct set of rules. That is definitely a potential approach. But on the other hand, you can develop a bottom-up approach, sort of a bootstrap approach. And why you want to do that is because now you have better understanding what constraints to put in, better sort of technology, numerical methods, computational power, and so on. So you might want to develop a bottom-up approach, and that is the approach that we are going to take. So what are the bottom-up requirements? So the bottom-up requirements, at least these are some minimal set of bottom-up requirements that we should keep in mind, is that there is some evidence that there is Regé behavior, at least up to some spin. We should keep this in mind. Regé behavior at small forward angle limit should be a constraint to put in. We should also remember that the width increases as the mass increases. So that is also something to keep in mind. So whether this narrow resonance approximation that gave rise to the Veneziana amplitude is the correct thing to do, we don't know, but then let's go with that. We also should remember about the F0 Regé trajectory. I said that there are these Regé trajectories which had slope 1 and intercept 0.5. But the F0 trajectory was parallel, at least that is the understanding so far. So we need to keep that in mind. We need to actually demand that there should be power law fixed angle scattering behavior, not the exponentially soft behavior like string theory. It should be consistent with crossing symmetry. It should have the correct intercept that is consistent with data. Then there are these consistency conditions. There should not be any negative norm states. It should have the correct factorization for n particle, and then these rules that you get from the n particle should enable you to construct loops, and the loop should have the correct analytic structure. These are the minimal set of conditions. There could be other set of consistency conditions that you can come up with. The point is that this is a very tall task. From the bootstrap, we have made very little progress, and the kind of progress that we have made, I'm going to describe. And also this is a personal take, so I will describe what I feel is at least the correct starting point for the first three. Okay. So the bootstrap program attempts to directly construct and constrain consistent S matrices. There is no Lagrangian. And it is not clear whether the amplitudes that you get out of these in the space of consistent S matrices, whether there's an oscillator picture or a world sheet picture, whether that emerges, it's also not clear. The kind of sort of first level questions that we ask is what basis do we use for the amplitude? So what are the generalizations for the Euler beta function type objects that we could use for the amplitudes? And we should also keep in mind that we want to truncate because maybe we don't want to put in these narrow resonance approximation beyond a certain energy scale. We want to actually only impose it up to a certain energy scale. So we want to truncate in level number while doing numerics. So it makes sense to use a basis that is manifestly crossing symmetric and not which does not have this duality property. So why this duality property is going to be a problem, I'm going to make clear when I show you explicit expressions. And the question is, does such a basis exist? The modern bootstrap is designed to give a space of allowed amplitudes, and for sanity checks, this is something that we will always anchor because string theory is a self-consistent, mathematically consistent theory. We will demand that string theory lives in this space. Okay, so whether it is smoothly connected to the actual interesting S matrix, I don't know, but then it should be an allowed solution to the set of equations that we are going to get. Yes. No, so the way that I'm going to set up the bootstrap, it will be somewhere anywhere inside the space. So what you have in mind is that if you kept adding consistency conditions, maybe you're going to start getting some deformations around the allowed theory if you're lucky. So you have to identify the correct set of consistency conditions to put so far as that is concerned. So I'm going to demand a weaker condition. I'm not going to demand that we're going to see kinks and it should be at the boundary. I'm going to demand a weaker set of conditions that it should be inside the space. And if you are lucky, the phenomenologically relevant answer will be in this space. So this is based on these set of papers. So this was Arnab Saha, who's a postdoc with me in ISC from early January last year. And then Faizan Bhatt, who was my graduate student, and Debapriya, who's still my graduate student. Faizan is a postdoc in INFN. And Arnab, then we actually provided a rigorous derivation for the dispersion relation that we're going to use in a paper with Faizan and Arnab earlier this year. But I should also tell you that this actually relies heavily on work that we have done over the last decade or so. In particular, it originated from thinking about critical phenomena. And all this takes key insights from string theory and quantum field theory. And I don't know if how many of you have seen, but there is a recent byproduct where we made a connection between logarithmic conformal field theories and Ramanujan's 1/pi series, which appeared, which was published in PRL this month. So let's go to the basis. So how many of you have learned string theory from Green, Schwarz, Witten? Okay, so expectedly, I would say 10% of the audience. So this is Green, Schwarz, Witten volume 1, and I'm quoting from the introductory chapter. What you should keep in mind is what I've highlighted. The duality hypothesis, they are talking about this equivalence between the sum over S channel poles and sum over T channel poles, the dual resonance hypothesis, never had more than slender experimental support, and the Veneziano model was merely an ad hoc way of satisfying this not so well motivated hypothesis. And based on this, there are several statements in the old literature which says that string theory is very different from quantum field theory, because this picture actually tells you that in the Feynman diagram language, we have the S channel and we have the T channel. Say we are scattering colored particles, so we'll have only 2 channels. And if we fatten up these lines, you are going to get a worldsheet picture like this. But then you can see that, okay, this looks like a membrane or something, and then you stretch it, and you can actually make it, the worldsheet picture, look like this. So this and this are apparently equivalent. So from the string theory perspective, there is no need to add these 2 channels, or just computing one of them is going to be good enough. Okay, so this is what how we explain the duality hypothesis pictorially. But modern understanding based on string field theory gives an alternative picture. And let me illustrate this using the closed string case, because this is what I learned from reading Ashok's paper. I'll go to that in a bit. But I should actually tell you that you should open DHS to actually read what they said. So Dolan-Horn-Schmidt actually never said that the amplitude should be only given in terms of the sum over the t, in modern language or modern notation, this is actually the sum over t channel poles. They say they were looking at experimental data, and they said that the experimental data would be consistent if we added the t channel poles and the s channel poles, but then if we just did this naively, we would get too big an amplitude, and we need to subtract off something, some expectation value of something, to get the correct magnitude of the amplitude. And then they make some hand-wavy statements, and they say that if this was if the resonances were sort of closely spaced, then you would get only the first term. And this is what is interpreted as worldsheet duality. So in fact, people during those days had a lot of fights between themselves. So there was a group which said that we just need to add this term and that term, and that went by the name of the interference model. Nobody had any statement about whether something needed to be subtracted off or not. And this so-called interference model was trashed during those days. Now, if you read the wording, so I won't read it for you, but then if you read, open the paper and read what they're saying, it does seem like that the authors are clutching at proverbial straws. And so this is what Greenshaw-Sweetan were alluding to, that there wasn't really a very strong claim for this dual resonance hypothesis. And these are confusing statements in the old literature that have never been clarified. So if you open Mandelstam's famous physics reports article on dual resonance models, he gives you these two pictures. So he says that if there are elementary particles, then you do indeed think in the language of quantum field theory, you add up both the channels. But if you think in the language of narrow resonances, which is what a pion is, then you either sum over one channel or the other channel, but not both. And when you open various this textbook, The Birth of String Theory, and you search for double counting, you will see several mentions of double counting, which actually say that if you did this when you are scattering composite narrow resonances, then it will amount to double counting, because apparently summing over just these poles already knows about the entire amplitude, so there is no need to add these two separately. So this John Schwartz's reminiscence in the textbook talks about double counting. Michael Green's reminiscence also talks about double counting, and so on. No, they didn't, and that is exactly going to be the point. So this is what I learned from Ashok. So I was deeply distressed for a while, and so I went and talked to the maestro, and I asked him, where is this decomposition in explicit decomposition in the language of quantum field theory for the Wiener-Jena amplitude? Remarkably, this is the first paper which actually gave such an explicit decomposition. Although, sort of, if you open Polchinski's textbook and read chapter 9 carefully, which I'm absolutely confident none of you have done, then it is already hinted in that chapter. So this is hinted by a procedure called plumbing fixture. So you take two spheres, insert vertex operators, and the third vertex operator, you join them up. Then what happens is that there's a choice of coordinates that you can make where you're inserting these vertex operators, and the choice of coordinates, there is a free parameter lambda. So this lambda in this choice of coordinates has to be, the real value of lambda has to be bigger than 3 for convergence issues. And it turns out that looking at the boundary of the modelized space, you're going to see the 3 channels emerging, and there is going to be a white region which is not covered, and this white region is what gives rise to this contact terms. Okay, so this is the string field theory insight. Okay, this was actually first pointed out to me in something that Debashish has forgotten, but in a conference here in NISER, probably in this room, during Sudhakar's 60th birthday. Oh, sorry, in NISER, yes. Which is NISER. I mean, NISER is anyway NISER, yes. Anyway, so if you open Polchinski's textbook and you ask that, okay, let me try and use this for my own benefit, I made no progress for 2 years, but then that is how the cookie crumbles. So that is how research works. You sacrifice a few graduate students and then move on. So the one thing to note is that there is a parameter. So it actually tells you that if you take these take this whole series seriously, and if you truncate, then you're going to see the appearance of this parameter in the answer. If you keep all the terms, all the massive modes, then the dependence on the parameter goes away, as it should. But if you truncate it, it will be sensitive to the parameter. And this parameter can be made sense of using field definition. I'll tell you what in a bit. So in the language of OpenString, so this is something that if you open Gradstrand and Rijek, so which nobody does anymore. So this is this huge, thick, fat textbook which is used as a paperweight or weightlifting purposes nowadays. But if you open that, you are going to see two standard representations for the Euler beta function. The first one is the expansion in terms of a single channel pole. So you only have this. So you only see, so this is the Euler beta function. They are a product of gamma functions. So you have poles in both the channels. So you only see poles in one channel. So obviously this has a finite or some restricted domain of convergence. This only converges when the real part of S2 is less than 0. And that is exactly what is expected, because the poles lie when S2 is equal to an integer on the right hand side. So you don't want to hit the poles. So the real part of S2 has to be less than 0. And similarly, you expand in terms of the other channel, you'll get this restriction. And this is the picture that you get. So this is the standard integral representation, which I'm going to talk about in a bit, a familiar integral representation for the Euler beta function. The representation 2, which is sort of unfamiliar, actually is this. So this representation manifests poles in both channels. It is dressed by a quantity which is similar to, which looks similar to the quantity here, the residue here. This residue here, the notation is that of a Pochhammer symbol. Is basically, if the subscript is an integer, then you get a degree n polynomial in the variable a. So these would be a degree n polynomial in S2. Similarly, this would be a degree n polynomial in S1 plus S2 in this combination. The last representation is rarely mentioned in the string literature, because this does have a feeling that this looks like quantum field theory. But again, if you dig deep, it is discussed in Green-Schwarz-Wheaton 1 at the integral level. I will show you this in a bit, in terms of the CSV vertex. The CSV is Kaneshi-Schwimmer-Veneziano vertex, the MMM cubic vertex that I mentioned. And so in the language of diagrams, this will actually look like as if you are trying to glue two disks together, and you have to add both of them. Now, neither of these representations, and these are known representations, actually meet the string field theory expectations, which tells us that the only non-analyticity should be at the poles and nowhere else. So these have non-analyticities. Oh, I forgot to write that, but the real part of S1 plus S2 here has to be bigger than 0, bigger than -1. And so this also has a restricted domain of convergence. And another important point is that neither of these representations exhibit this parametric ambiguity that we saw in the string field theory calculation. So this is a favorite quotation that I like showing. By Alexander Polyakov. The garbage of the past often becomes the treasure of the present, and vice versa. I leave it open to interpretation what garbage is in this context, but yeah. Yes. The radius of convergence, they have some overlapping region, yes. So no, there is an overlapping region. So there are two representations that I showed you. These, this is 1, this is 2. So this requires real part of S2 less than 0, and this requires real part of S1 less than 0. This one I will show you the exact domain of convergence. I think it reads like real part of S1 plus S2 has to be bigger than -1. So a condition of that kind. No, so using these two, you cannot cover all the all S1, S2 space. Yes. Yes. Absolutely. Yes. Yes. Yeah. So the expectation was, I'm going to set up the bootstrap program, and I'm going to use level truncation. So I'm not going to keep all the infinite modes. So I want a representation which enables me to truncate in level and do things numerically. Yeah, so I'm going to develop a sort of a new set of techniques which will, beta function is going to be one of the solutions, but not the only solution. Yeah, not at tree level. So I'm going to develop a dispersion relation which at least at tree level will give you this as a solution, but because it's a dispersion relation, you can also look at it non-perturbatively. The lambda that I talked about, at least in the string field theory interpretation, is in the choice of coordinates that you have. You can reinterpret that in terms of field definition. I'll go over it in a little bit. There are multiple ways of thinking about it, or you can also think that there was this worldsheet picture and I'm stretching it one way or stretching it the other way. You can think of it as some elasticity of that worldsheet. So the dispersion relation that I'm going to develop is going to be dimension agnostic. Yeah. Here also it's dimension agnostic and it's tree level. So when you discuss tree level unitarity, you only get an inequality. You get d less than equal to 26. So yeah, you don't get the equality. That's right. So what we are going to do is use dispersion relations. So what are dispersion relations? It's just Cauchy's theorem. You know some analyticity property of your amplitude. So there could be branch cuts. So you just write down Cauchy's theorem. You start off with a large contour at infinity. You wrap around the branch cuts, or if there are poles as well, you could wrap around those poles as well. And because Cauchy's theorem is for a single variable, you require to do something, because this is an amplitude with two variables. I'm talking about 2 to 2 scattering for now. So you will have to do something with the second variable. So what you do is you hold the second variable fixed and you write down a dispersion relation in the first variable. And this is what is called fixed T dispersion relation. The second variable Manders time T is held fixed. So that's the idea of writing our dispersion relation. That's all that you need to know so far as this is concerned. And for crossing symmetry, you require to impose that m of st should be equal to m of ts. We are again focusing on two-channel symmetry. But if you use the fixed T dispersion relation, this symmetry is not manifest. So you get extra constraints from this equality. In modern S matrix bootstrap, this is the constraints that come from this condition are what are called null constraints. Further, if you use this for the Veneziano case, and again, as I said, that you're holding T fixed, so the poles in T will not be visible. This means that there will be a limited domain of convergence and does not make the analytic structure of the Euler beta function manifest. So we require a new kind of dispersion relation, which is going to be, so I'm doing pretty badly with time, but let's see what we can do. So we're going to draw some valuable insights from string theory. So what are the insights? So one is this picture that I've already shown. So there is this duality between these two channels, and so in the string picture you have a representation which actually enables you to talk in the language of one channel. The other not very well emphasized point is the following. So you see, this is the integral representation of the Euler beta function. Now for the students, this is an exercise for you. Find the change of variables that gives rise to this second equivalent representation. Now the difference between the first representation and the second representation is that in the second representation you actually have manifest crossing symmetry. If you interchange S1 and S2, here it is not manifest, but here it is absolutely manifest. And you do have an additional term, so you can split it up into two different terms. If you expanded this the integrand binomially, then and integrated term by term, you get this series, which needed real part of S2 to be less than 0. And if you did the same thing for the second representation, you actually get the second equivalent representation, but which requires real part of S1 plus S2 to be bigger than -1 for convergence. The way that you interpret it in the worldsheet language is that, so this is the open string worldsheet. You can actually insert two vertex operators at the worldsheet the end of the open string. 1 and 4 are the incoming and outgoing states, or you can actually insert one at the one end and the other one at the other end, and when you do that, you have to sum over both possibilities. And so this is the worldsheet understanding of this integral representation. So this is explained but not very well emphasized in the string textbooks. So we want a dispersive representation that enables both these pictures to be captured. Now I wanted to actually tell you what is this interpretation, another interpretation of this lambda, this parameter, and because I want a parametric ambiguity in my new representation as well. So this is how you get this parametric ambiguity. You have some light particles and say that you have some heavy particles, and say the interaction between these light particles phi 1 and phi 2 with the heavy particle, say psi 2, is through a cubic interaction phi 1, phi 2, psi 2. Now what you can do is you can redefine the heavy particle through psi 2 plus lambda times phi 1, phi 2, and no, these are all bosonic fields. So no fermions. I'm just using the same notation for these fields. So what you can do is you can redefine. So this cubic interaction was there in the fundamental Lagrangian, and then after you do this redefinition, you have generated a lambda phi 1, phi 2, phi 1, phi 2 term. But then after doing this redefinition, you can drop all these heavy terms. So this interaction term, this cubic interaction, now has generated this extra piece which only cares about the light fields, and this is what is a contact interaction with this parameter that I have introduced through this redefinition. This new term only depends on the light field, and so here is the imprint of the heavy fields. And so this is another way of thinking about this parametric ambiguity, that if you truncate in the heavy fields, then there is going to be some ambiguity in your representation, and thus we expect a parametric ambiguity in the basis. So I'm going to use this parametric ambiguity in some clever way. The objective is that I am going to have a new representation that captures this single channel expansion that the worldsheet gives, but also this second sum over two channels that I told you that is expected from worldsheet intuition. So this is what I call a stringy dispersion relation, the new basis. So if you want a derivation, so we have a nice simple derivation which will take 10 or 15 minutes to explain, so I don't want to go into that. But this is the form that we have. So let's go through this representation a little carefully. So this is the amplitude. It's a function of S1 and S2. S and T mentally you can replace. S1 and S2 are the same thing as S and T. So it's an integral over the cut. So there could be some singularity. So in the tree level language, you have poles, isolated poles, and you're wrapping your contour along the isolated poles on the real axis. So this is what I call a kernel. The kernel actually looks like the sum of Feynman diagrams. So this would be like the S channel, this would be like the T channel, and this would be like a contact term. This is the absorptive part. So this is the discontinuity of the amplitude across the singularities. The thing to note here is that the second argument in the fixed T dispersion relation would have been T, but in this new dispersion relation is something more complicated. It's a quadratic S1, S2, and then there are some linear terms in S1, S2 as well, divided by the integration variable. So this is different from what you would actually encounter in the standard fixed T dispersion relation. Now what happens is, because of this parameter lambda, I can dial this parameter and interpolate between various representations. This parameter actually enables me to go from the single channel representation that I told you, the worldsheet, the Euler beta function the standard form, but you also have this sum over channels interpretation as well. So this is why I wanted to introduce a parameter. This parameter also plays some other important numerical roles. We have been working on a 5-particle version, which I'll flash right at the end. This parameter enables me to interpolate between all known different kinds of dispersion relations that exist in the literature. So let's see how that works. So just again, see the first term is like the S channel, the second term is like the T channel, and the third term is like the contact term. And how does it work? So let's go through an example. So let's put lambda equal to minus S1. So if lambda is equal to minus S1, this and the first term cancel. and then when lambda is equal to minus S1, this also cancels, and this is going to become S1. Okay, so this simply becomes S1, and you get the T-channel representation of the amplitude. You do the same thing with lambda equal to minus S2, you get the fixed T dispersion relation, which is this this guy. This new representation actually gives me an entirely new series for the Euler beta function. So the Euler beta function now has a completely Feynman diagram kind of feeling to it. You see the S1 poles, you see the S2 poles, you also see this parametric ambiguity, and the beauty of this representation is that each of these terms converges on its own. There are no further singularities, it converges everywhere, it's absolutely convergent. So there is no singularity except at the poles. The convergence actually requires some condition on the parameter, but that's fine. This is similar to the restriction that we had on the choice of coordinates. If you remember, the real part of lambda had to be bigger than 3, so that it's similar to that kind of a restriction. So this new representation manifests poles in both channels. Each piece is analytic on its own away from poles. It has this parametric form that I expect, and also enables truncation, but still captures Regge and exponential softness. So if you truncate, typically you lose something. You really don't have exponential softness if you truncate in the fixed T representation, but this representation does. So in fact, we use dispersion relations to prove this representation, and now there is an alternative proof by the Swedish mathematician Hallman Rosengren, who found a different proof of the same series for mathematicians. Okay, so it's very easy to see that if you put lambda equal to minus S1, then you get a single channel expansion, and the single channel expansion is precisely the form that you that is there in Grafstein and Regge. Yes. 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 Yes, and that's exactly the point, because you're going to get a single channel representation which is only convergent if the real part of S1 is bigger than 0, less than 0. So it has exactly the same convergence criteria. Yeah. Yes, this is also valid when S1 is 12 complex. So that one is a dispersion relation. So I'm assuming that so in this particular case the poles are on the real axis, but you can actually move the poles anywhere that you want. You can have cuts as well. You have to wrap your contour around the cuts, and so it will have a more complicated form than the simple real integral that I showed. So this also tells you that maybe you can come up with a Lagrangian description of this, which has a form of a higher spin theory. So just to advertise, a corollary of this was highlighted as one of the coolest mathematical discoveries by Scientific American, and that is new formula for pi. Because if you take lambda to be much bigger than 1, what you get is the summand becomes the Madhava series, and the Madhava series. So basically, this new formula is an infinite number of new formulas for pi, which interpolates to the Madhava series. So unresolved question is that we need to find a change of variables at the level of the integral. So a good question for students is to see if you can come up with a change of variables from this integral form and get the new representation for the Euler beta function. It's quite challenging because you see you have S1, S2 divided by n, and in the representation S1 and S2 don't talk to each other quadratically, they are always linear. But we can also easily modify this to accommodate different sort of, because it's a dispersion relation, you can actually accommodate much very different high energy behavior. So you can actually accommodate power law behavior in addition to the exponentially soft behavior in the fixed angle limit. for example, so how do you get it from a string field theory way of doing the calculations? So in the last few minutes, I'm going to just tell you about how we have been trying to use this for the string bootstrap at tree level. And I have a different take. So there have been lots of recent attempts, and some of these recent attempts have inbuilt worldsheet duality, which I feel is not the correct way of doing it. But anyway, so we are not going to demand inbuilt worldsheet duality. So so we have been using this dispersion relation to come up with a new basis. So what we do is we assume for now, so I will relax the assumption, but assume that you have an integer spaced spectrum exactly like string theory. You separate out the massless pole. This is the 1/st pole that you see in the form factor for gluon scattering. So we are going to restrict our attention to gluon scattering in superstring theory. My interest is to see what criteria we need to put in to isolate string theory. So we want a basis, and the basis now has a different form than what people use. So because of the dispersion relation, the argument of the Gegenbauer polynomials is no longer in terms of 1 plus s by t to 2t by s, or the usual conventional fixed t form, but it takes on this form, and then there is parametric ambiguity as well. So how do we constrain? So what we do is this is the most important thing. We minimize a quantity which you can interpret as the first finite moment of entangling power. So you can think that we are trying to minimize the amount of entanglement that is being generated in scattering. So we are trying to minimize the amount of entanglement that is generated in scattering. Why? Because we are in a weakly coupled theory. So weakly coupled theory should not generate too much entanglement. So that's a nice picture that we have, that maybe there is a entanglement minimization at play here. This is we are scattering gluons, so there are helicities, so entanglement in the helicity of the gluons. Yes, yeah, how much entanglement is generated. And so here I usually joke at this point that I worry about the kind of job prospects for my students. So it's good to put in machine learning, throw in quantum computing wherever possible. So but here actually naturally machine learning helps, and so we are actually going to use some machine learning tricks while doing this. So one thing that happens is that when you actually do this for the string point, by string point I mean that I have fixed the two Wilson coefficients to the string values, and then I'm actually minimizing the entangling power. You get the answer for the CLs, the coefficients in front of the Gegenbauers, to be very similar to what you get for string theory. So you can take some points. So for example, n equal to 14 for the first daughter trajectory, you are going to see that the exact answer is this, and the numerical bootstrap answer gives you this. So this gives you a space of allowed S matrices. So the blue region is a space of allowed S matrices which are close to respecting this worldsheet duality. And string theory, of course, lies in that region. So that is that point. But you also get a whole space of other interesting theories. In particular, people have considered deforming string theory away. There are these what people have considered are hypergeometric deformations for the open superstring, which was done by Mansfield and Spradlin in 24. So the blue is where you have this dual resonance hypothesis being satisfied, sort of how well it is satisfied. And the yellow and red are, it is not satisfied well at all. Yeah, so these are Wilson coefficients. So this is a particular low energy Wilson coefficient, and this is also a particular low energy Wilson coefficient. We see that the allowed space of theories in that space. So another reason why machine learning actually helps is to track the Regé pole. So the Regé pole is a pole in the complex L plane. So you want your machine to learn a function of two variables, and you want to complexify L and look at poles in that. So it seems to pick up the Regé pole reasonably well. I mean, there are some subtleties, so it's not perfectly accurate, but it seems to do it reasonably well. So what is special about string theory? Now what I'm going to do is, instead of assuming an integer space spectrum, I'm going to randomize the spectrum. It is still going to be on the real axis, but I'm going to randomize the spectrum. And I'm going to, on this slide, I've done it using SDPB. So I've actually done minimized entanglement. So string theory appears to be the answer that gives you minimum entanglement. Okay, everything else seems to be above. So in fact, for any of these points, these are all allowed S matrices. Any of these points that are close to this red line, which is the string value, you get a total scattering cross section that is reasonably similar to string theory. Whereas if you consider some random S matrices away, you get different total scattering cross sections. And in fact, these total scattering cross sections are at least an order of magnitude bigger than these ones that are close to this red line. So this is last slide. I want to flash that we have been working on a 5-particle dispersion relation. We have written down the answer by assuming that there are only these cubic type interactions. So we have an analog of the kernel, we have an analog of the absorptive part. There are these primed variables. So as I said, that these t got replaced by something else, which was a combination of s and t and the integration variable. So there is a set of equations that these prime variables have to be satisfied. We have worked out what these equations are, but we have not managed to solve these prime variable equations as yet because they are a bit complicated. And this is work in progress. And in the next talk, Apratim is going to tell more about the 5-particle and n-particle objects in CFT. So maybe we'll get some new insights from the CFT. So challenges ahead. So I think we have roughly a fair control over the first 3 targets. We wanted to put in Rege behavior at small angle forward limit. We can do that. We want to put in power law fixed angle scattering behavior, not the exponentially soft behavior. We can also do that. We have inbuilt crossing symmetry. Now, correct intercept, we can have all kinds of intercept. I don't know how to get the correct intercept. I don't have any idea how to show that there are no ghosts. We have only worked up till the 5 particles, so we don't have a procedure to get the CSB vertex as yet. And so that means that we don't yet know how to construct loops in the most general way possible. But one thing is that the rigidity of string theory is hard to emulate. Nobody has managed to actually come up with a similar program which satisfies everything. And so how do we accomplish what string theory has done so far without the worldsheet? So obviously, the same thing to do is to go back to the oscillator model, not demand that there is a worldsheet, and see whether either the algebra, the oscillator algebra can be modified, or sort of a step 1 would be that you start up with the oscillator model, use the new Euler beta representation to rederive the vertices in propagator, and this is some work in progress so far. So thank you very much for your attention.
Thank you. We'll take one question. Maybe someone who has not asked. 2. You have not asked.
So I missed one thing. So this hadron scattering we know is described by QCD, right? I mean,
Yes.
It's the same hadrons you are talking about. So how is it? So in that plot, I mean, where you have string theory at one point and then you have this lots of other things. I mean, they are all string.
So one of
theories,
these points. So here we have assumed that there is an integer space spectrum. So you have not assumed real values for the real part of the resonances.
But do you expect them to be all consistent theories, or they will just like I mean, when
so if you do it correctly,
so
obviously
it is
you should get
usually
the QCD
said
answer
that I
somewhere.
mean string theory has no like that sort of the unique worldsheet here. So I mean, do you have any comments on that, like, or I may have misunderstood it actually?
No, so you are
So-
saying that
so in these
will you have any
plots-
other worldsheet description for any other point? Is that your question?
Not just worldsheet, but are they consistent in?
So if you put in enough constraints, you expect to see QCD as an allowed solution as well.
I see. So that I mean that also you are calling string, like quote unquote string theory.
Yeah. So in this picture, because I've not put in any real experimental values.
Yeah, but how will you get the SU3? The 3, I mean, it.
So this is only a restricted sector.
I
So
see.
this is only the QCD sector.
Like the rank of the gauge group and these things will
So
not
the-
come out of the
these
bootstrap.
things you can't.
Fine.
I'm assuming that those are inbuilt.
Last question, Gyan. Rest I have to request, please catch one in the
Yeah.
afterwards.
So I'll just tell a few facts. I have lived long enough. The first is actually this FESR duality. It was first by Igi and Matsuda.
Uh-huh.
Pi minus p going to pi 0 n, because in the cross channel there is only one trajectory. Second is actually 1972 in ISR experiment, they found that PP cross sections were rising.
Okay.
So this was bad news for Rege pole people.
Right.
Because Pomeranchuk intercept cannot exceed 1. It will
Right.
not. So they actually introduced the Rege calculus and Rege cuts. So the cross section will be logarithmically corrected. And today, if you look at PDF, LHC data and further cosmic ray data, they show the cross section is rising as log a square. The coefficient is not determined.
Yeah. But you could fit anything. I mean, log square is one of the particular fits. I mean,
Well,
one of the-
actually, people tried power law. Then 3 people in Wisconsin, they showed that there's some error in their codes.
okay.
So this is, I think, is undisputed. Okay, then there is a question that how come Veneziano and Virasoro published these 2 papers in few months interval?
Okay. I don't know. You'll know.
At tea time. Okay. Then this is actually I have verified. Gabriele was visiting only for 2 months, and when he wrote down this paper, when he wrote the preprint, many people opposed, and when he eventually wrote the paper, which was published in Novecimento, some permanent staff of CERN commented, if this model were correct, donkeys will be horses.
Good to know.
Okay, let's thank Honindo once again. Our next speaker is Apratim, and he'll talk about bootstrappy explorations of QFTs in ADS.
Hello. Am I audible?
Hello.
Hello, everyone. It's a pleasure to be in ISM. So I thank the organizers for giving me this opportunity and putting up this wonderful conference. I'll talk about some bootstrappy explorations of quantum field theories in ADS. So what I'm going to tell you about is I'm going to put some quantum field theory in ADS background and see what happens. Okay. Okay. So it's an empty ADS background I'm talking about. It's a very simple setup. So you just take your favorite quantum field theory and put it in a cloud space. That's all. Now, why do I do this? Because as you know, that even just kinematically, if you do that, it will always have a conformal field theory at the boundary. So you can think of this as in terms of this picture. So you can have a parameter space of that quantum field theory. It can be like a part of the fourth theory with a mass and lambda, and in the parameter space there will be RG flows. You can have fixed points. This is all happening in the bulk in my setup, and in the boundary, all these points in it, every point in this parameter space will be a CFT. In that sense, if you have RG flows, there will be like families of CFTs connected to each other. No, these are not local systems. But the point is, we can understand the parameter space of quantum field theories, what is allowed, what is not allowed, using conformal bootstrapping. So just using something similar to an IR regulator, which is like the ADS radius, you can use the power of conformal bootstrap to understand this quantum field theory. Okay. So you could have so instead of using conformal bootstrap, it could also be possible to use something like S-matrix bootstrap, something similar to what Anindya told us about, using dispersion relations, which doesn't just hold for string theory, but also for any quantum field theories. Okay, but then why am I using conformal bootstrap? It's because intuitions, developments on conformal bootstrap are much more and more well developed. It's more, the techniques are robust and more well understood, and I will tell you how that will be very important. Yeah, these are families of CFTs. Okay, so thanks for pointing this. This is just an analogy. Yeah, exactly same as in, I mean, it's a parameter space of quantum field theories, and every point in quantum field theory is a CFT, some non-local CFTs. The goal of this program is to identify. Yes. Yeah. In the bulk, yes. All of them correspond to some CFTs on the boundary. Every point on this line, even not just these guys. Yeah. It's a CFT in the bulk is like a boundary CFT. So it's like a all these are CFTs in the bulk, and then you have some CFTs also. So you're having an entire RG flow in the bulk. So the point is you can extract all of that using, that's it. Yeah. Yes. Yeah. All right. I just wanted to say one more point here. Yeah, that the goal, it's not as easy as it sounds that you can track an entire RG flow from one fixed point to another fixed point just from conformal bootstrap. It's a hard thing to do, although there are papers who have tried to identify such things. I'll try to briefly review those things a little bit. But the main point is, if you are using conformal bootstrap to understand these things, it's a non-perturbative thing. That's the beauty. Whatever you understand, whatever you are getting, it's a non-perturbative flow from one point to another. Yeah. Yeah. Mm-hmm. Yeah. Yeah. Sure. Mm-hmm.
Sometimes you can think of something that determines the CFT as the value is at RA.
Mm-hmm. Oh yeah.
Okay. I'm trying to understand
what is the what does the
means that you kind of get different
mm-hmm.
you have to change the effective field RA, which means that you are kind of, you can do it in various ways.
Yes.
I'm trying to see how you're thinking about.
Yes.
Are you changing the RABS in each of these cases?
Okay, so my set, I'll give you how I understand these fixed points. So we can think of one fixed point as a free theory, which is like putting a free massless scalar in ADS. In that sense, I'm putting a CFT on the bar. You can also put something else like a minimal model in also in ADS. So you know all the dimensions, and in that sense, it's still a CFT. You know every correlation function. So yeah, so that's what I'm doing. But yeah, I know, but that week I can talk a little bit later. I don't want to spend too much time talking about that. But
let's say lambda 5.
Yes. Yes. I know. Yes.
So now at point you stop at some lambda star.
Yes.
At R.
Mm-hmm.
So that is the thing that will
Sure.
data define this field.
That's true. Mm-hmm.
Now if you want to kind of explore all of this, you have to change the lambda star at R.
Mm-hmm. Yeah. So you can, the setup is like a BCFT. So this, so what happens in the BCFT? The boundary is set by the radius. So you can, so obviously in the BCFT the full conformal symmetry is broken. So it's, yeah. Yes. I'm literally putting, you can think of this, I can spend more time on it later on, but I'm not going to spend more time right now. But the thing is, you can put, if you take a Wieser-Fischer fixed point or any CFT in a boundary CFT, then it defines the specific way you can identify the CFT living on the boundary. Yeah, so that's what is happening here. Yeah, maybe I can talk to clarify this point later after. All right. So okay, so this is how I plan my talk. So first I'll talk about how RG flows can be identified. How these RG flows are certain the lines joining one point in the KFT space to another point can be identified with a bootstrappy OP maximization like procedure. In these kind of programs, it is important to have like a handle on mixed and higher point correlation functions. I'll talk about some developments on those fields, bootstrapping 5 and 6 point functions, and then some ongoing work that I'm currently doing with my students and some other people. Right? Okay, so the setup is I'm going to use the following tools. Crossing symmetry, because I'm a bootstrapper, so I have crossing symmetry. So here it's the crossing relation for a generic 4-point function with all non-identical external scalars. Okay, so yeah, and I'm particularly will focus on 1D CFTs. Why 1D? 1D because 1D is a 1D has a very simple kinematics. Okay, and so it's easier to track down. You have just one cross ratio. So you have in CFT, in a 4-point function in a CFT, for instance, you have 2 cross ratios, U and V, and you set U and V's to Z and 1 minus Z, like that, and then you just have one cross ratio. I hope it's a one property of 1D CFT because you cannot have spin in 1D. And yeah, that this is the second this point that there is no spin in 1D. Okay, only scalar operators in the OP. Okay, so what is the general strategy in conformal bootstrap? So you can find, so the general strategy is the following, at least when you are doing a non-perturbative numerical bootstrap, is you can assume a little bit of the spectrum, and then you can try to put bounds on the rest of the spectrum. And that bounds, whenever you find a bound, you actually end up finding an entire spectrum as well, along with it. Just briefly, let's say that you have an OP, phi and phi, 2 scalars, and you assume that you know what the first operator after identity is. That you have an identity operator, dimension 0, and then you have an operator with certain OP coefficient. This A is the OP coefficient squared for identical external scalars. You have 2 identical external scalars, so it's a positive number, square of OP coefficient. And let's say that you know exactly what this delta 1 and A are. Now let me ask, these OP coefficients depend on, I mean, this can be anything. Yeah. Yeah, this whole procedure depends on also, delta phi also. We have to choose delta phi, and this putting bounds also depend on delta phi. So then you ask, what's the maximum possible value of the second operator? This is an example. So you can ask this question, what's the maximum possible value of the second delta 2? And then you end up finding a bound to delta 2. Okay, my picture is, my bound should have been here. So it's imagine that this colored area goes up till here. It's a bound on delta 2. Once you reach the bound, if you're at the bound, you actually end up having an entire spectrum that corresponds to what saturates the bound. It's a CFT that saturates the bound. So it's a possible solution to the OP. So that's how you get one possible solution to the OP. But this is just one OP. It cannot specify the entire CFT. Let me explain this statement a little better. consider general dimension for just one moment. In a general dimension, if you have two scalar fields, phi and phi, it can have symmetric traceless operators in the OP just from group theory, representation theory. But then you can also have mixed symmetry tensors in the CFT. Those are allowed operators, but they cannot enter in the OP of two scalar fields. So you have no access on these operators of the CFT, which are also present. So no matter how hard you try, just an OP of two scalars cannot specify the entire CFT. Okay? But they will not enter the OP of phi and phi. I can construct it, but they will not be present in the OPE. That's what I mean. It's just a property of. I mean, there's no way to make this operator. It will have OP coefficient 0 from the representation theory, and a mixed symmetry tensor. So that's the point. So you cannot have access to the full CFT from just two OP of two scalars. So in order to know further, in order to know more about what are the other operators possible in the theory, we have to access a system of more OPs, which means a system of non-identical scalars. So maybe, for instance, simultaneously bootstrap 3 correlation functions. Okay, or you can look at higher point functions. Higher point functions are very nice because they actually have access to not just a finite number of multiple OPs, but an infinite number of OPs. So you can consider OPs of two scalars, and then whatever operator is appearing here, you take the OP of that with respect to the other field, and in this way, you have access to an infinite number of OPs in a single higher point function. But the problem is, kinematics of higher point functions are harder. Right? So in this way, you can simultaneously put constraints on more and more OPs. Yes.
But whatever you get, like again, OP with phi, you get all those.
Yeah. Yes, that's the point. Although this is 1D, there will be mixed symmetries are not present, but also there are more complicated operators, more operators which are not present trivially. Okay, so what are the question now is, what are the minimum input or assumptions that you need to give in order to get something that you're interested in? For this talk, you're interested in quantum field theories in ADS. What are the minimum assumptions that are required? So this is a simple setup that I will actually talk about. You can have free theories, free massless, free massive theory, bosons in ADS, and you can have free massive theories in ADS also. And there is a nice prediction from Bootstrap that tells you there is a flow from one of these, from the free boson to free fermion, if you add a pi to the 4th deformation. So let me tell you about what can Bootstrap say about flowing from one theory to the other. Okay. All right. So how does Bootstrap know about free bosons? So let me just quickly review this. So to identify just free bosons from a single correlator Bootstrap problem, you can ask, let's keep the first dimension in the OP. So in the OP there will be identity. In phi and phi OP there will be identity, and then there is some operator delta 0, and let's fix it at 2 delta phi. That's an input. 2 delta phi is something that we expect from generalized free theory, like this free theory in ADS. And let's demand that you maximize the OP coefficient of this operator. Okay. The solution turns out to be something that exactly matches with the free theory spectrum. Okay. So whatever solution that maximizes the OP coefficient, this one, is the free theory in ADS. The boundary of ADS that is a safety. It's called. Yeah, but on the boundary, it's a, there is a, in the boundary. Yeah. The first, the small files, the dimension corresponds to. All right. So now you can play the same game. Why? Oh, it's an observation. At this point, it's an observation that if you maximize the OP coefficient, it turns out that it turns out to be the spectrum of frequency. Okay, but now you can extend that observation to understand further other things in the spectrum. For example, this is just one OP. Can the yeah squares? Yeah, squares. Yeah, sure. This is the OP coefficient square. And then if you keep for an OP like phi and phi square, or phi square and phi square, you can ask the same game. You can keep the first operators fixed and then ask to maximize the first OP coefficient of these guys. And then they also turn out to be the OP, exactly the spectrum of GFF as we expect. Yeah. Same maximization, sorry? Oh yeah. Yes, exactly. Right. Yeah. Yes. Roughly. Yeah. Sorry. Which variable am I? Sorry, I can. Right now there is no. I mean, right now we're finding we're trying to find a. There's a variable. I mean, we have this OP coefficient. We're trying to look for a solution that has the maximum value of this guy. It's a procedure called semi-definite programming in Bootstrap. It's a technical thing. I can talk to you later after that. So this, sorry, you demand unitary. Sorry. No, it's an infinite spectrum. Yeah. Yes. Everything is infinite. There is no real alternative. Yeah. Okay. So now you can ask, if you deform the GFF spectrum a little bit, the free theory spectrum, how do you deform? You change the first operator to not the free theory value to something else. And then it asks the same question of maximizing OP coefficients. It turns out that it gives something that looks like a flow. So in this spectrum, the flow of this entire spectrum, this is from this paper, by the way. If you look at the leftmost part, which is closer to the free theory result, it corresponds to perturbation theory. You can compute this part analytically, and it matches with. I mean, you can compute it using Witten diagram, and it matches. But then the right side of the spectrum is completely non-perturbative. We are flowing from a perturbative regime to non-perturbative by demanding maximization of OP coefficients. Sorry. This no. Just turns out to be like this. Yes. Yeah. There are a lot of free parameters. I mean, I'm just changing this guy, delta 0, the first one, and the others turn out to be like this. No. There's. I mean, I'm no assumption like that. It's just I'm just maximizing. Deforming delta 0. Yes, that's it. Yes. Okay. Now, why is this spectrum ending at 3? Because 3 is the maximum possible value of the first operator, delta 0. It's a maximum value of the delta 0 operator. You cannot have. It's actually a solution to another problem called the gap maximization problem. If you demanded that what is the maximum value of the first operator, delta 0, it's exactly 3. I mean, I assume that my external dimension is 1, and then if you do that, then the upper bound to delta 0, which is another bootstrap problem, turns out to be 3. So the picture, so the point where the picture ended is the point which is the solution to this gap maximization problem. And this gap maximization problem corresponds to the OP spectrum of the free fermions. Okay? It's a spectrum that corresponds to 2 delta 5 plus 1s, 2 delta 5 plus 3s, plus 5s, and so on. And you can do the math in your mind that if you have a dimension like this, it actually corresponds to operators of like that, because if this will have a delta 5 dimension, and then you have to have, since they're like a fermion pseudoscalar anti-commuting pseudoscalars, you need to have a derivatives, odd number derivatives. Yeah. Free fermions. So this is in ADS2. Yeah. There's a marginal operator here, so you actually cannot deform it in ADS and go to another. Yeah. Yeah. Okay. So how do we know that this spectrum that I'm showing you is really GNS free fermions and not something else? So that for that I have to know other OPs also, not just psi and psi. So let me show you how that happens. How you can do that. You can do that by going away from 4-point level bootstrap and go to 6-point level bootstrap. For 6 points, you can take, you saw from one of the talk, there are channels that correspond to Coombe channels and snowflake channels. A Coombe channel looks like this. This is how it looks like a Coombe, by the way. And you take 2 different Coombe channels, okay? And you put cross-symmetry there. And how it works is the following. You assume that when you have a Coombe channel, you can easily see that there will be 3 operators in the OP, not just 1. But one of these operators, one of these O1s and these O3s, you actually know, because they are what appear in the phi OP. And assume that you know them from the 4-point level. Assume that you know exactly what O1s appear in this Coombe channel. But you don't know what O2 is. Okay? Can you put bounds, or can you know about these O2 operators? So this is what you can do. You put the free fermion spectrum here in this OP. It's something that you know from 4-point level. And you ask the question, what is the maximum value of the operator O2 in all possible OPs like this? So whenever you have O2, whenever you're talking about this middle operator in the Coombe channel, you're actually talking about an infinite number of OPs, because you're at a 6-point bootstrap. You're doing a 6-point, you're looking at a 6-point correlation. Yeah, the same set of operators. Yes, exactly. No, not here. Sorry, but I can tell you afterwards. Okay, so this exactly matches with the free fermion expectation, and that's how you know that there is another. If you demand the maximization of the O2 operator, you end up landing at exactly the free fermion spectrum at 6-point level. So this is how you pinpoint GNS free fermions. So this is a small summary. This is just summary, and I have like 2 or 3 slides after this. And this is how you go from free fermion to free boson to free fermion, and the RG flows can be labeled as CFT saturating OP coefficients, and the end point is a CFT that saturates the gap. Yes. Yeah, nothing. Yeah. Yeah, you can have any free scalar theory or like part of the 4th theory.
Gravity is not dynamic.
Yeah, gravity is a dynamic. Yeah. Okay. Sorry. So last 2 or 3 minutes. Yeah. So now, if you're talking about ADS RG flows, we're talking about ADS RG flows. there is one nice bootstrap framework that actually helps you that actually naturally encodes the deformations around free theories. This is the Polyakov bootstrap. Its sum rules, it's a special set of sum rules that you get from this Polyakov bootstrap approach that manifestly solves the free theory spectrum. Okay, and it also trivializes these extremal theories like the free fermion set. So this special approach. So the sum rules that you get from Polyakov bootstrap, they are special because if you plot this omega delta, they have zeros at very special places. So they have zeros exactly where you expect your free theory to lie. And since there are zeros, the free theory is a trivial solution to these sum rules. And that's how it's easy to solve. That's how they encode the RG flows in areas or any deformations of free theories in areas. Now, can you extend this Polyakov bootstrap setup, which is usually only for 4 points, to higher point functions or more general setups? For higher point functions, this was done at the 5-point level. So you have to define something called a Polyakov block. A Polyakov block is something that has all the kinematic properties of a CFT correlation function, like Regge boundedness, closing, analyticity, but it's not immediately consistent with the usual conformal block expansion. You have to identify a Polyakov block and make it, and you have to kill these infinite spurious blocks that are associated with the Polyakov block. So that's what gives the bootstrap constraints. So Polyakov block for a 5-point function turns out to be a finite series of Witten diagrams. So this is what we did. Okay, I forgot to refer to the cite the paper. It was a paper by I wrote with Antonio Antunes and Sebastian Hens, and it trivializes cubic or Z2 odd deformations in ADS2. You can also try to understand Polyakov bootstrap in general dimension, where crossing symmetric dispersion relations that I talked about are going to be very helpful. This is the expectation. One challenge in this dispersion relations is that in the context of CFTs, they don't have positivity. It means you cannot use unitarity to impose bounds on CFTs. So if you don't have unitarity, you can also progress. You can also make progress by using truncated bootstrap. So truncated bootstrap is simply you said that you have n number of sum rules and n variables, and you solve them. And if you just play the same game as I showed before for the 1D setup, then you get a result that is very close to the OP maximization procedure without using unitarity, but you just using truncated bootstrap. So this is the conclusion and outlook of my talk. I'm over time, so I'm not going to read them out loud, so you can review it. Yeah, 2 minutes? Okay, I'll leave it for the questions.
Questions?
So nice talk. So as you said that by adding a 5-4 interaction, you are going from boson to fermion by bootstrap. So first question is whether it can be reversed by adding some fermionic interaction and going to bosonic.
Oh, it's a very interesting technical question. No with quotes, because let me go with maybe the better plot. Very good. So you see that if you're deforming the spectrum, it's almost the spectrum actually is not too deformed until you reach the very end, and then it jumps a little bit. Okay, so this jump means that it's going to a non-perturbative solution at the very end. So there is no trivial. So if you start from the right, there is no trivial deformation that immediately lets you come to this side. So there is no, the answer is there is no trivial deformation to the free fermion that takes you to the free boson, but it's a very specific non-trivial deformation. Okay. So
and the second and the second question is does it have some supersymmetric implications, like supersymmetric is boson to fermion? I'm very noob in supersymmetry.
Yeah, there is no duality. There is a supersymmetry because one single theory does not have symmetry between bosons and fermions. But you can think of that if it's implying some kind of duality between, like there's some parameter that you can tune that takes you from free bosons and fermions. That is still I don't know yet.
Okay, thank you.
So I just have a curiosity, like in flat space, right? You are studying like in the boundary of ADS, you are just studying like CFT. Like if suppose someone want to understand in a flat space the RG flow between two CFT, what the ADS picture it corresponds to? Do you have an idea?
If
So suppose in the boundary, I want to study RG flow between two CFTs.
yeah.
Like what will be the corresponding bulk picture? Do you have any idea?
Oh. On the boundary, you want to study an RG flow, but
Yes.
then you are going away from conformality at the boundary.
That's true. That's true. So
Okay.
do ADS safety help me some way, or what the bulk picture I should look for?
Hmm. You can. So this is
Okay. Okay. I don't know.
don't that break. We want to break. Okay. I see.
Very basic question. So if you have a theory in the bulk with gravity, and if you have a theory in the bulk that you just some quantum field theory on curved space time, what is the signature in the boundary theory?
It will have a stress tensor then. So you want to have gravity, granular gravity in the bulk, right? Then it will turn on a lot of operators. It'll go little out of control. My setup was a controlled setup. So if you turn on gravity, then you will have you're turning on a lot of operators in the OPE. There will be a stress tensor that will be present. So you have to, so those things will, and so you need to look out for them. So it will have a more complicated setup, and you need to know how to, look at more and more OPEs in order to really understand what the bulk theory is.
So a priori, your theories are non-unitary and
Non-local.
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 Just one clarification. Are you putting in the information of the bulk coupling, like the lambda 5-4 if you are talking about? That bulk coupling information, are you putting into these anomalous dimensions?
No.
Or they are just parameters here? So how do you know it's a lambda 5-4 deformation? It could be some other deformation as well, right?
It could be not just lambda 5 to the 4, but any Z2 preserving deformation, like
Okay.
lambda 5 to the 4 plus 5 to the G 5 to the 6, 5 to the 8, something similar.
I see.
But with lambda 5 to the 4, if you do a Witten diagram computation, it matches, and you compute 4-point functions, it matches with the left.
I see.
Okay, so let's thank Apratim once again. We have tea break now. Let's return at 11:35.
Hello. Yes.
Okay, so let's start again after tea break. David will talk about bubbling saddles of the gravitational index. David?
Okay. Hi. Can you hear me? Yeah. Hi, everybody. Let me also start by thanking the organizers for the invitation, as well as for setting up such a nice meeting. This is my third Indian strings meeting, and I'm always happy to be back to India. So the main character of this talk is going to be the gravitational index and its bubbling saddles. And the talk is based on work I've done in collaboration with Alejandro Ruiz Perez, who is currently a postdoc at the University of Murcia, and Enrico Turetta, who was my PhD student. He's currently a postdoc at Kyunghee University in Korea. So let me start by reminding you of a very robust partition function. It is the refined Witten index. Take a supersymmetric quantum field theory. We can define this object that counts states weighted with -1 to the f. So we have bosonic states counted with a plus sign and fermionic states counted with a minus sign. And provided this charge is J, that stands for angular momentum, and Q, that stands for electric charge, commute with the supercharge, this object is a supersymmetric partition function. Namely, it only receives contributions from supersymmetric states. There is no, because of this, there is no dependence on beta, on the inverse temperature. And it only depends on this angular velocity omega and electrostatic potential phi. And in addition, it is independent of continuous deformations of the theory, in particular its energy flow invariant. So it's a very robust partition function. And we may be interested in using this object to explore quantum gravity. A priori, this is defined in a supersymmetric quantum field theory with no gravity, but today we will try to define this object and compute some of its saddles directly in gravity. So the question definitely has a positive answer, because we know that many of the successful black hole microstate counting results that are around in the literature reduce to the computation of some index, one way or another. And also, if we remind about holography, this may be a conformal field theory partition function, but given the identity between partition functions, that is the master equation of holography, we could argue that the same object can also be defined directly in gravity, which is the scope of the talk today. So we will try to do this by using the path integral formulation. So the path integral formulation prescribes to path integrate over all the fields in the theory, including the metric. Now we are in gravity, on the gravity side. And of course, this function, this is a function of what? This is a function of the boundary conditions that we have to specify and keep fixed. And I will come back to this. Of course, this is a very hard object, and I'm not aiming at computing it exactly now, also because we would need an embedding into a UV complete theory, which we are not going to do today. We will be happy with working with the semi-classical approximation, where this partition function is approximated by saddles. What are these saddles? They are solutions to the classical equations of motion, which have a finite Euclidean action. And given the fact that we may have many different saddles may dominate for different regimes of the boundary conditions that we are going to define now. So let me take a concrete setup. The concrete setup will be the one of 5-dimensional supergravity, pure, in this case, 5-dimensional supergravity. Of course, we could generalize to more complicated theories, but this is somehow the simplest setup I'm interested in. The theory has the metric, gravitino fields, and a gauge field, A, whose field strength is F. In this setup, 5D supergravity, asymptotically flat, no cosmological constant, so no manifest holography here. Even if this setup is particularly simple, with the set of solutions that we may have, supersymmetric solutions in Lorentzian signature for now, is very rich. Why? Because uniqueness theorems don't work in 5D, asymptotically flat, so we may have many different topologies in the bulk. If we consider solutions with the horizon, there are different possible topologies for the horizon itself. We may have an S3 topology, which gives rise to the well-known BMPV black hole, but we may also have S2 times S1 topology of the horizon. This corresponds to the black ring of M-parallel collaborators, and we may also have more exotic topologies that correspond to these lens spaces that can be seen as orbifolds of S3. They are called black lenses because of the lens space topology of the horizon. There are also horizonless solutions, which also have a non-trivial topology. They somehow sustain themselves thanks to the presence of fluxes, and they are called topological solitons, and in the language of the fuzzball community, bubbling solutions. And they will also play some role for us. So why are we interested in considering solutions with different topology? Well, because we may be trying to compare these solutions. Think about the microcanonical ensemble for a moment. We fix the charges and then we compare the entropies. In this setup, it is known that fixing the charges does not determine the solution uniquely. And indeed, we may have solutions with the same charges that can be compared. For instance, the BMPV black hole and these topological solitons can share in some regime of the parameters the same charges. Also, there are black objects, that is black objects with some horizon, that have the same charges of the BMPV black hole, but carry a larger entropy. These are solutions with the horizon and some topology outside the horizon, as it was pointed out in this paper. So it is interesting to compare solutions and in some statistical ensemble. What we are interested in today is the grand canonical ensemble, so we will be interested in comparing solutions that share the same chemical potentials rather than charges. So in order to do this, I have to fix my boundary conditions and define these chemical potentials. Since the solution is asymptotically flat, it will have, the metric will have this form. Now the explicit form of the metric is not particularly important for the talk, but I'm presenting this just to introduce the different symmetries that will play a role. So we have the Euclidean time tau, and correspondingly we will have some energy E. Then there are two rotations in the asymptotic S3 that are these angles phi and psi defined like this. So provided these identifications are realized, this metric here defines an S3, and the corresponding angular momenta will be J plus for phi and J minus for psi. And then we have an electric charge because we have a gauge field A, which gives rise to an electric charge Q. We are interested in the conjugate chemical potentials. These can be introduced as boundary conditions. So while we go around the thermal circles with a period beta, we also shift the angles by angular velocities omega plus and omega minus. This introduces the chemical potentials. This identification here, this prescription, is a boundary condition for all the fields and introduces for us the chemical potentials as it is standard. And we also introduce an electrostatic potential phi as a gauge holonomy for the gauge field we have in the game. Another way of seeing these chemical potentials in the geometry is this statement that I declare that the vectors that have two pi periodic orbits are the following ones. There is this vector here, which is my thermal vector. It's represented here. It has a closed orbit. So declaring that this is a closed orbit fixes my chemical potentials. And then I declare that these other two vectors also have closed orbits. They represent the two U1s in the S3 that is represented here. What does this mean? This is S3, although it's not really manifest. This is S3 seen as a foliation over an interval, a foliation generically by a torus, but at the extreme of the interval, one of the two circles may shrink. And here I'm representing the vectors that shrink in these coordinates. So this is the S3 at infinity, but there will be an S3 in the bulk as well. This is meant to be the thermal circle at infinity. It may collapse or not in the bulk. Question. Oh, no. It's just conventional. It's just because the way I define these coordinates. It's just purely conventional. Nothing more than. Yeah, it's purely conventional. Sorry, it's just related to conventions we use in the paper. Nothing more than that. I could change the angle for minus itself. Okay, I've declared, so this, I'm showing these vectors and the possibility that they collapse, and in particular this one in the bulk, because they are going to play a crucial role in the, they form a basis of U1s and they play a crucial role in the talk. This vector, when this vector collapses, we find a horizon. If it doesn't, the solution will not have a horizon. So now I use these boundary conditions to define my partition function. So given what the boundary conditions we have fixed, the path integral will compute for me a partition function of this form, which a priori depends on all the chemical potentials. Here I'm using the superalgebra instead of the Hamiltonian of the energy to define the Hamiltonian. However, as I said before, we are interested in partition functions that only receives contributions from supersymmetric configurations. This can be achieved by introducing the -1 to the f. How do we do this? By realizing that -1 to the f can be obtained, constructed as a combination of angular momenta. And therefore, if we fix omega plus in this way, then we actually implement and just redefine chemical potentials in this way. This very same partition function can be written in this way, which is now takes the form of an index, and therefore we call this the path integral in gravity, computing this partition function. So with these boundary conditions, a gravitational index. We will see that this condition is actually met by the solutions we construct. So we will argue that the solutions we construct will contribute to this index. So the question that I'm after now is, what are the saddles of the index? What among the Lorentzian solutions we know, among the possible topologies that we know exist in Lorentzian signature, what of these topologies can possibly contribute to this partition function that I just defined? So in order to answer the question, we should realize that the index only receives contributions from supersymmetric configurations, so we need to find supersymmetric solutions. However, we are in the Euclidean setup, so there will be supersymmetric Euclidean solutions, which a priori should have a finite beta, because this gravitational partition function is defined a priori at finite beta, although we know that the final result should be independent of beta. So this means that they should be non-extremal solutions. Lorentzian solutions of this type that are supersymmetric and non-extremal are not well defined. However, here we are in the Euclidean setup and we'll search for saddles of some function, so we will also allow for a complexification, and this will allow us to construct it's the interpretation of time, but there will be something more. Generically, we will allow the metric to be generically complex, as well as the gauge field. It's a formal finite temperature, if you want. It's the parameter that now appears in front of the supersymmetric Hamiltonian here. So manifestly, this object will not depend on temperature. So and it is a supersymmetric object. So it is going to be independent. The partition function is going to be independent of this parameter. As you can see now, I mean, it doesn't multiply the energy only, because I've redefined the other chemical potentials in this way. So it's not formally, it's just formally a temperature. Or in the setup I'm considering, this is asymptotically flat, and the superalgebra doesn't contain J plus or J minus here. I have picked one particular supercharge. Maybe I should have said this. This Q here is one particular supercharge, so it's a subsector of the full superalgebra. Yeah, if I was in IDS, there would be some J here and there, but I'm setting the cosmological constant to 0. Question. Yeah, precisely. That's correct. So, yeah, this is because the fermions they are charged under this combination. They are antiperiodic under this, the U1 identified by this combination of the angular momenta, and so it fixes the fact that the fermions will be. So yeah, it introduces this -1 to the f. So this is the boundary condition for the fermions. The remaining part of the boundary conditions are encoded in this omega and phi, but these quantities commute with the supercharge, so they fix the boundary conditions, if you want, for the whole multiplet, but it doesn't distinguish between fermionic and bosonic modes. So this other combination commutes with the supercharge. So the theory I'm working with is five-dimensional, pure five-dimensional supergravity. It has 8 supercharges. Yeah, it's the minimal theory in 5D, minimal supergravity in 5D. Okay, so I define this object. I'm after the saddles. These are the properties that they have to satisfy. Eventually, these are constructed at finite beta. Eventually, we may try to send beta to infinity to make contact with the Lorentzian solutions that are only defined after we take the extremal limit. So let me first remind you of what is the supersymmetric solution, what is the supersymmetric structure of these solutions in Lorentzian signature, and then we bicrotate. Here you see some factors of I because I'm already bicrotating. Anyway, supersymmetric solutions with an extra U1 symmetry have this form here. The form is not important. I just want to emphasize that once we have supersymmetry, we have one Killing vector that is del tau here. In addition, I'm requiring an extra symmetry that commutes with the supercharges, and I am going, this is generated by this other Killing vector del psi. Once we have specified this, the form of the supersymmetric solutions is fixed. This has been realized long ago, and this is the metric and the gauge field. The details are not important. Let me just stress that the whole solution, at least the ones we are interested in, are fixed by harmonic functions, in particular by 2 harmonic functions. Harmonic functions in which space? In R3. You see there is an R3 factor, so these are harmonic functions in R3. They are characterized by some coefficients, and then by some special points from which we are measuring the distance. This RA is the distance from the special point A that are called centers usually. So there are some constraints on the coefficients, but apart from this, these are fixed coefficients that for us will be complex generically. The solutions, yes, they are charged, but importantly, the charges don't fix the solution immediately. That's what I'm going to say. They are also rotating, yes, generically, yes. All the charges are turned on. So the parameters of the solutions are essentially these parameters you see here and the distance between the centers. Yeah, it is. Importantly, because of supersymmetry, it plays an important role, yes. In fact, you can see the wall action reduces to a sort of Chern-Simons term, so it's important. For simplicity, I'm also imposing an additional U1 symmetry so that we have in total the 3 U1 symmetries that I already presented before. this is once I'm in R3, I assume that there is a rotation symmetry around an axis in R3. So this is the one parameterized by this coordinate phi. So because of this, all the centers of our solution should be aligned. The centers of the harmonic functions, they should be aligned along this axis. So they are represented by these dots. So this is how these solutions are constructed. As you see, it's a systematic construction. So one can construct very general solutions. And so clearly the asymptotic charges Q, J plus, and J minus are not enough for characterizing the solution. We need to provide more data in order to account for all the parameters of the solution. The more data, the additional global data are given by what is called the rod structure. What is a rod structure in a few words? So here we have the axis with all the centers, and then we can consider the intervals between two centers. One should realize that there some killing vector can collapse. Killing vector will be given by the combination of the three ones, but the three ones can have different coefficients. The combination can have different coefficients, so there are many possible killing vectors that collapse, and given which killing vectors collapses defines this rod structure. And this is important in order to fix the topology of the full solution. Let me give you an example just to clarify a bit. So I have a three-center solution here, 1, 2, 3. I have killing vectors that are combinations of this del phi and del psi with integer coefficients characterized by this integer p, and p in the solution is related to the coefficients of the harmonic functions, as you can see here. Once I specify what are these p's, I'm specifying the killing vectors that collapse, and the fixed loci of these killing vectors, they give us the bubbles of the topological solitons. So what are these bubbles? They are the fixed loci, so the bolts of these killing vectors that collapse, and I have to choose these. One can see, for instance, that in order to have a solution with smooth bolts, with smooth two spheres, one needs to fix these coefficients as here. These are the famous Benner-Werner solutions. However, if the coefficients HA of the harmonic functions are integer but not plus or minus 1, you still have almost regular solutions. You just have some conical singularities at the centers. So you get what are called teardrop or spindles as bolts. Yeah, the line here is in R3. For me, then at some point I will allow the parameters to be generically complex. But this line is in R3. So you see the metric has this form. So there is time. If we are in Lorentzian signature, this is actually time. Then there is an additional killing vector, psi, parameterized by psi, and then I have this R3. So this line is in R3 at fixed, if you want, a fixed tau, psi, and phi as well. Psi, yeah, that's a Gibbons-Hawking base. Well, okay. So the solutions with an extremal horizon. So far I presented the rod structure for a solution with no horizon. Solutions with an extremal horizon have a special center. It's a blue center instead of being red because it's an isolated center, but the vector that collapses there is del tau. So it's a supersymmetric killing vector that is this del tau instead of being a combination of the angular ones. So this picture here is meant to represent the BMPV black hole. It's a solution where the only other vectors that collapse are those the poles of this S3, del phi minus del psi and del phi plus del psi, and then there is this supersymmetric killing vector that is time-like that collapses, becomes null at the horizon, which is this one. So a black ring, sorry, what is a black ring? It has a slightly more complicated rod structure because there is another vector that can collapse, and there is correspondingly another rod that you can see here. You can see this is an S2 horizon because del phi minus del psi collapses at both poles of the horizon, which is what happens in S2 instead of S3. And the black lens similarly has an additional rod. Let me skip this. And the topology, one can also study the topology of this bolt where these vectors collapse. It's the one of a disk. So all this is in Lorentzian signature, and this is already known from past studies. One should also specify the gauge flux through these cycles or the dual potential in order to fully characterize the solution. But again, and there are many generalizations that one can combine all these ingredients, but let me just go on and try to ask the main question of the talk, that is, if these solutions or a version of these solutions, a finite temperature version of these solutions, can be considered as saddles of this grand canonical partition function that I defined and that I called the gravitational index. In order to do this, we need to assign finite chemical potentials and action to each of these solutions. However, all of these, as long as they are extremal, they have an infinite throat, so there is a problem with computing the action. So we will use again a trick that we used already in the past for ADS solutions, that is deform them into supersymmetric non-extremal solutions, compute the action, and then possibly take the beta to infinity limit. However, the results will be independent of beta as expected for a gravitational index. So let me just present what I should do starting from the BMPV black hole, the very basic black hole, asymptotically flat black hole that is the rotating version of the Strominger and Waffa black hole. So it's the most basic black hole we know about in 5D. This is based on work with my two collaborators, but I should also emphasize other papers, including one by Ashok and collaborators, one by Amitabh Virmani and collaborators, one by Samir Murthy and collaborators, etc. So the finite temperature version of this black hole is a solution where the Rho structure is as follows. It's the same as before, but the extremal horizon that was an isolated point in this, along this axis now becomes a rod of finite size. And the size is, of course, related to the temperature in a way that can be made very specific. Here I'm representing the vector that collapses. One can see that in the supersymmetric solutions, omega plus is indeed 2 pi I, so this is even seen directly in the solution, so this vector simplifies, and this is what I'm representing here. However, here I'm also presenting the relation between the parameters of the solution and these chemical potentials. You can see that if delta, which is the distance between the two centers here, goes to 0, beta goes to infinity, that is, the solution becomes extremal. So these schematically are the finite temperature versions of the BMPV black hole. One can now compute the action by different methods, including equivariant localization, and obtain a result, which is also familiar from the ADS case. And by Legendre transforming, one finds the correct entropy and requiring reality of the entropy as the correct relation between the charges, that in this case is just the condition that one of the two angular momenta vanishes in the BMPV solution, which is realized in the BMPV solution. So although we went through this complexification and finite temperature deformation of the solution in order to assign an action and also assign finite chemical potentials, once we perform the Legendre transform and we require reality of the entropy, we obtain the correct, we do obtain the entropy of the known Lorentzian BMPV solution. So we want to see if a similar game can be played with this phi is the electrostatic potential. It's beta times the electrostatic potential, roughly. It's a gauge holonomy of the gauge field at infinity. Yeah. Okay. In blue, I have all chemical potentials, in red, the charges. Yes. Yeah, here G Newton is set to 1, just for simplicity. Correct, anyway. Now I want to see if the more general topologies can also contribute as saddles in the same spirit. So this was the rod structure of the black ring, the extremal one. So again, we turn on finite beta. Now we have a 3-center solution with a finite, this is representing the horizon. Again, the vector that collapses is the thermal killing vector with the supersymmetric condition implemented. Omega plus is 2 pi I. And again, we can map the parameters into the chemical potentials and see indeed the omega plus is fixed. The other chemical potentials are generically arbitrary. Then we have some additional information that appear in the Earnshell action that is given here. there is an integer h1, which was again the integer of the harmonic function appearing there. This must be integer in order to get rid of Misner-Dirac singularities. And again, if h1 is not plus or minus 1, we have conical singularities, but we can also take h1 plus or minus 1. Then the topology of the horizon will be smooth. Sorry, the topology of the bubble that we have outside the horizon will be smooth. And then there is an additional datum. As I said, one has to specify something about the gauge field that I'm not really discussing in the talk. So by going through the quite delicate computation in this case, because the gauge field is not globally defined everywhere, one has to do this by patch, precisely because of the Chern-Simons term. One reaches finally a concrete expression for the Onshel action. It is this one. You see, it's a sort of correction to the Onshel action of the black hole, which was this one, which includes this additional data. However, if I want to obtain the topology corresponding to the black ring or black lens, I have to fix this h1 to plus or minus 1. So h1 equal 1 gives the topology of the black ring. h1 equal minus 1 gives the horizon topology of the black lens. And so you see, these are explicit Onshel actions. So these are meant to be the contribution of each of these solutions in their finite temperature version to the gravitational index. So a priori, all of them we find can have a finite action. So a priori, you could take them as good saddles for the index. Yeah, all of these solutions have killing spinors. Yeah, based on the general construction that I presented at the beginning. Those are all solutions with killing spinors locally. Then one has to check the global conditions. So the main result is, this is a good question. We don't know yet. We should fix the chemical potential. So a priori, I'm saying chemical potentials can be generic, so generically complex. Then we should find the range of the chemical potentials where both the BMPV black hole and these black rings exist, and then compare. This we have not done really, because also there is a question of integration contour, whether the integration contour is defined in such a way that it passes through all these candidate saddles, or maybe some are included, some are not. These are open questions that deserve more study. Yeah, there are all these. These are for fixed charges. Here I'm asking a different question because I'm in the grand canonical ensemble, so it's a priori a different question, but indeed the hope is that maybe in the long term we would also have to clarify these other questions that are asked in the microcanonical ensemble. But here I'm still remaining in the grand canonical ensemble. A priori I would like to compare all these solutions, but there are some open questions to answer first, I think, before going into a natural comparison. Anyway, one thing one can see is that each of these saddles carry the correct entropy, in the sense that if I take the Lejeune transform again and fix the reality condition, I indeed obtain the expression for the entropy as a function of the charges that is realized in all of these solutions, including the condition, the relation between the charges that always exist in these solutions. Eventually, if we want, we can take the extremal limit. These expressions don't depend on temperature, so I could declare that this and or this are indeed the Onshel action of the black ring, of the black lens in the extremal limit, because I can take the extremal limit after having made the computation. Exactly, I think so, yeah. We had some confusions about the big fly because they are not as fixed asymptotically. Since they are not fixed asymptotically, a priori one should find sum over them. That's why I'm representing them in a different color, indeed. It's an important point that a priori one should sum over all of them. In this sense, they compete. The black lens, black ring, and black hole, they compete because they have different values of phi. If I should have kept them fixed, they wouldn't have competed. Yes. Killing spinors are there since the beginning. Then one has to check maybe global conditions that are maybe delicate, but yeah, they are there. Killing spinors. Exactly. Yes. There is also How much time do I have? 0. Okay. There is an interesting limit that I have to skip. That is the horizonless limits, where we can also take beta to 0 in this game because nothing depends on beta eventually. But in this way, you see this part of the vector goes away. So this horizon solution is transformed into a bubbling solution. So there is this limit that we also analyze. However, there are some issues that, as you can see here. However, I don't want to take more time. There are many generalizations that can be studied, and some of them have been studied also by people in the audience and collaborators. And there is also a nice question to ask, in more formal question, that is if we are able to compute the on-shell action of these solutions given any possible Rod structure. We are not that far from answering this. And so just to conclude, I presented a systematic construction of saddles of this gravitational index that I defined. All these ingredients can be combined in order to construct more solutions. And we have assigned chemical potentials and actions to each of these candidate saddles, and which can have very rich topology, black ring, lenses, etc. Now the question of the integration contour I already mentioned before is which of these saddles are actually saddles, that is, they belong to the integration contour. And after having answered all these questions, we could analyze what Ashok was asking about, what is the phase diagram of quantum gravity understood in this grand canonical ensemble, that is compare the action of the different solutions and see which ones dominate. And eventually we would like to match at least one of these results, say the action of the black ring, with some microscopic computation to see if this can indeed have a microscopic counterpart. So thank you for your attention.
I think you can take maybe 2 questions. You have asked, those people haven't asked.
Do we know of these kind of solutions in ADS spaces as well?
That's a good question. So the black hole, of course, yes. Black ring and black lenses are not known in ADS space, asymptotically ADS5. There are some no-go results for the minimal supergravity case. In minimal supergravity, there can be no black rings, but this is not excluded in supergravity coupled to matter. And some recent nice results are that even if we don't know the solutions, the action has already been computed, because using this equivariant localization method that I mentioned, Dario Martelli, Alberto Zaffaroni, and collaborators have shown that even in asymptotical ADS space, by assuming something about the topology of the solution, in particular the topology of the horizon, you can compute the action. So the expression for the action is known, even if the solution is not known, and it actually matches the one I presented here. Though with a different constraint. Omega plus is not 2 pi I, but otherwise the expression is the same I presented here.
Sorry. What about the lens solutions? Do they
same discussion for the lens.
But from the CFT point of view, do we know of?
That's another good question. If we take some index, the superconformal index or a version of that, do we find a saddle that corresponds to this? Maybe this saddle with an action like this? I don't know. I would like to know.
No, I was asking this because from the CFT point of view, if you have a lens space, is there a notion of this operator, state operator map, right? From the CFT point of view.
Because it's a radial quantization.
Yeah.
Yeah, I don't know, but yeah, you're right. For the black lens, okay, you should take an orbifold. Okay, maybe one should check that the action of the orbifold.
And also just one more in the flat space case, we know these solutions.
But let me just emphasize that if I stick to the path integral formulation, I can define some index for the theory on S2 times S1. It's not interpreted as the field theory in radial quantization, but there is a partition function for n equal 4 super Emils on S2 times S1 times the thermal circle. So I would stick to this partition function and ask if there are saddles, Lagrange saddles of this partition function. Sorry. Thanks.
I have some naive questions. So, this do you have this bubbling saddle solution 4D also? Is it possible to have them? 4D in 4 dimension?
Dimensions. No, these are, that's why I'm studying 5 dimensions. All
Five
these solutions appear in 5 dimensions. Then there is a similar construction of finite temperature solutions that are still supersymmetric in 4D, but the zoology of topologies is less rich. But there are similar constructions that have been studied.
Okay, so you started with the action and then the solution, it was an analytically continued solution to Euclidean signature, right? That the first solution you take, Gutters-Kyriel, that gauntlet solution,
Yes,
5D.
correct.
So basically, if you take in 4D, matter coupling is also possible in 4D, right? In 4D
Yeah, the
supergravity.
same construction is there. It's just that the richness of topology is a bit reduced, but the same construction can be done.
Yeah. The question I was wanted to ask that for the scalar fields in 4D, because in 5D you have pure gravity, right? In 4D, if you have matter coupling, do we know the proper analytic continuation rule from Lorentzian to Euclidean?
Here I'm assuming everything can be complexified. Then you can ask what is a reality condition field space. But yeah, things have been done. Yeah, there are some results. There is. Yeah, I'd like just to make a comment about the black ring from N=4. Here the asymptotics of all these solutions are anyway flat space. So if we were in ADS, we would assume that all the solutions are asymptotically ADS in global coordinates. So they should have S3 asymptotically. It's just at the horizon that the S3 becomes S2 times S1. So asymptotically it should be N=4 super-MEs in radial quantization.
Okay. Thank you.
Thank Davide once more. I see there were more questions, but we're running late, so we have to catch him later. Our next speaker, I guess, is Narayan, right? Where are those people who set things up? Very long title. Okay, so Narayan will talk about a lot of things, de Sitter extremal surfaces, replicas, pseudoranies, and time entanglement.
Am I audible? Okay, so it's a pleasure to be here, and I'd like to thank the organizers for inviting me to speak at this beautiful conference. So I'm going to talk about various aspects of de Sitter extremal surfaces and the time entanglement structures they lead, and most recently a replica story and pseudoranian entropies. Okay, this is based on a large body of work. More recently these papers and this most recent one, but also a large body of earlier work. So I'll begin by talking about de Sitter broadly and DSCFT, which is what these structures broadly fit into, and then I'll talk about extremal surfaces and pseudoentropy and so on. So it's been more than 25 years since ADS-CFT began, and the broad statement is that holography is a statement that quantum gravity in a space-time region is dual to a theory without gravity on the boundary of that space-time region. So at a very broad brush level, we've seen these broad structures probably articulated by Witten long back. So for negative cosmological constant, we have ADS-like asymptotics at spatial infinity. So the dual is a unitary Lorentzian CFT, which includes time. Time goes vertically up in more or less everything I'll say. For flat space, 0 lambda, we get null infinity-like structures asymptotically, and there have been many investigations of the S matrix and its symmetries and Carolean and celestial structures over the years. For positive lambda, positive cosmological constant, we have de Sitter space, and the natural boundary appears to be in the future, at future time like infinity or past. The dual is living on the spatial slice, and so it's a Euclidean CFT, and bulk time is supposed to be emergent from this. Okay, so whatever the CFT is, if it exists, we expect that this is going to be something exotic, because if you look at the gravity dual of an ordinary Euclidean CFT, we expect Euclidean ADS from all our experience over the last many years. A broad question that's going to play out in the theme of this talk is on whether de Sitter entropy can be thought of as some sort of holographic entanglement. So let me just tell you a little bit about what this entropy is. So we're thinking of de Sitter as a sphere that's crunching and growing with time. So if you look at these spatial slices, these are spheres. So if you draw one of these lines, then the top wedge or the bottom wedge can be described by the Poincare slicing. If you draw both of these lines, the static coordinatization describes this. And for for observers in these left and right wedges, the static patches, these lines are they look like event horizons. They're cosmological versions of event horizons. And the area of these horizons is the entropy as formulated by Gibbons and Hawking long back. So I'm going to play the holographic game. I'm going to ask if de Sitter entropy can be thought of as some sort of holographic entanglement. And then you'll actually let to ask whether there are appropriate generalizations of the Ruta Akinagi story that we've all seen extensively over the last nearly 20 years in ADS. Okay. Before I get to this, let me just tell you a little bit about the context for this thing, which is DSCFT. The details of this are not going to be so crucial for what I'm going to say, but it's important. But it's very useful to keep this as the underpinnings. So long back, Strominger and Witten, mainly spearheaded by Strominger, formulated DSCFT based on the future time like infinity as a natural de Sitter boundary. This leads to a Euclidean non-unitary CFT dual with bulk time supposedly being emergent. Okay. So as I was saying, the gravity dual of an ordinary Euclidean CFT is Euclidean ADS. So this is expected to be some sort of exotic object. Okay. So in his well-known paper on non-Gaussianities, Maldacena soon after argued that the entire structure of inflationary perturbations can be organized as an analytic continuation about ADS. Okay. This led to a very precise formulation of the DSCFT dictionary, which is a statement that the Hartle-Hawking wave function of the universe at late times, subject to certain regularity conditions at early times, is to be equated with a partition function of this dual hypothetical CFT. Okay. One can now do holographic studies with this. So for example, if you think of this thing as a generating function for dual operators and so on, then the dual operator correlation functions can be studied using this object semi-classically. And if you do this, then it turns out that the dual energy momentum tensor 2-point function shows a negative or imaginary central charge. Okay, so this suggests a ghost-like CFT. So this was fleshed out in an example, in a class of examples by Areno, Stadtmann, and Strominger in the context of high spin de Sitter, where the dual that they suggested was a theory of symplectic fermions in 3 dimensions. Okay, anti-commuting scalars basically. Bulk expectation values, on the other hand, as Maldacena argued, are given by the standard quantum mechanical formula that we see. So they come with a mod psi squared. Okay. So now this suggests that the dual contains the dual should be thought of as comprising 2 CFT copies in some sense, 2 copies of psi and so 2 copies of ZCFT. Okay. So this broad theme will play out in what follows, that if you use 1 copy, then you get a certain class of boundary observables, and bulk objects end up requiring 2 copies. Okay. There's various things that are there in the detail in the details of how this fleshes out, and it also plays out differently for different dimensions and so on. But I'm not going to go into that right now. On the future boundary. This is what is going to be the theme of this investigation, and this is what DSCFT naturally plays out as. Over the last many years, there have been always suggestions about different holographic screens. Other holographic screens include, for example, cutoff boundaries here, cutoff time-like boundaries here, or the stretched horizon, for example, and so on. They lead to very different thinking. These themes don't seem a little disjoint right now, and even including all these investigations that have happened over the last few years. In some ways, maybe there's some sort of complementarity at play, in the sense that stuff here is probably complementary in some sense to structures that you see from here, and this is something that one has to keep in mind. But it doesn't. It's not evident from what we've seen so far. So this just suggests, if you interpret this object from the point of view of the dual CFT, it looks like it's not just one object that emerges, it looks like there are two copies just because there's psi and psi star. That's all. It's just at this heuristic level that I'm saying. And there are ways in which this plays out in other ways. This is to be contrasted with the ADS safety dictionary, where you have Z bulk is Z boundary, so Z safety Z bulk, and then the bulk object is the boundary object. It's just at that level that I'm saying this. Okay. So back to this question about whether one can think of the entropy as some sort of holographic entanglement and Ruther-Kinagi generalizations. So a natural generalization of the Ruther-Kinagi story to de Sitter. So I've said what I had to say. I have nothing more to say. This is just a it's just a statement that seems to be what that formula suggests. The two copies is something that we'll see in other versions in what follows. Let's wait for that. Okay. Yes. It's a difficult question. Yeah, it's a difficult question in many ways. But so it's not directly going to play into what I'm going to say. So we can talk about that later. Okay. So a natural generalization of the Ruther-Kinagi story to de Sitter involves setting up the bulk analog of entanglement entropy in the dual Euclidean CFT. So the Euclidean CFT has no time; it's entirely spatial. So I'm going to think of one of the spatial directions as boundary Euclidean time. I define that as the boundary Euclidean time slice. On that time slice, which now in the bulk is this sort of vertical time slice, for example, I define subregions on that, and then I stretch off RT surfaces that extend off from the boundary of that subregion. Okay. So these become now codimension 2 RT-HRT surfaces, which are anchored at I plus at the future boundary on this boundary Euclidean time slice, and then they dip into the bulk holographic time direction. Okay. So there's a kind of picture that one might ask whether this plays out. So for example, in ADS, what you do is you take a constant time slice, and if there's a subregion, the RT surface starts off here, and then there's natural optimization, the surface ends there. And so there's a natural turning point, and the surface goes back, and the area of this is what we interpret as entanglement entropy. If that same thing were true, there would be a rotation of that to this sort of a picture, and then one might ask whether that plays out. You can do this extremization in great gory detail, and the experimental finding that I had many years back was that there is no such real I plus Y plus turning point in Lorentzian de Sitter. These surfaces that start here do not have any tendency to go back. They don't return. Okay. So what can you do? One can do two classes of things. In entirely Lorentzian de Sitter, there are future past surfaces that start here and end here. So since they don't go back, one can start here and they end at the past boundary. So that's these. These are entirely time-like, and their area is pure imaginary relative to ADS space-like surfaces. The other thing one can do is to look at no boundary surfaces. So one looks at the Hartle-Hawking type no boundary proposal, chops de Sitter in the middle, and attaches the Euclidean hemisphere to the bottom half, and then the top time-like part of these future past surfaces joins up with the spatial surface in the hemisphere, and that gives a complex area. Okay. So these are all direct de Sitter studies, but for global and static de Sitter, you can show that there are analytic continuations from ADS which amount to a space-time rotation. Okay, so in many ways you can think of the ADS RT story and then flip it on its and then turn it sideways, and that becomes a de Sitter story. So good question. We'll get to that. So they are extremal surfaces. Really. They are extremal surfaces. So we'll get to that later. So these objects, these areas are all, they all have time-like components, and so these objects are not ordinary entanglement entropy in any sense. They are new objects. They are a pseudo entropy or a time entanglement. They're really entanglement-like structures with time-like separations, and this can be fleshed out by formulating a Leukowitz-Martinsson type replica on the DSCFT dictionary, which I'll get to later. For future reference, pseudo-entropy formulated independently just in quantum mechanics and so on is the entropy of the reduced transition matrix. Okay, so you look at two states, you construct this sort of a transition matrix operator, take partial traces, and construct a reduced transition matrix. The entropy of this object is what's been called pseudo-entropy. And this is what these structures naturally seem to lead to. Okay, so this is a broad one-slide summary, so to speak, of this whole thing, but I'll get to more of this.
So this is all the bulk story. You could ask, if you do believe this DSCFT dictionary and take this ghost like CFT seriously, can you do something in the dual ghost like object? So the full ghost like theory is a hard object to understand, but in various toy models you can actually do many things. And so there are versions of replica arguments that I had long back, but they are much cleaner. But these things have, there are subtleties and so on. There are much cleaner toy models of what I call ghost spins. These are basically two-state spin variables with indefinite norms. So unlike an ordinary spin which has up as 1 and down as 1, you can cook up a ghost spin. So I was abstracting this away from the B0 C0 subalgebra of the BC-CFT, for example. So if you look at this, there are off-diagonal inner products here, and so this leads to negative norm states. Okay, so you can come full circle and look at ghost spin chains, infinite ghost spin chains with certain nearest neighbor interactions, and take appropriate continuum limits, and then that gets back to the BC-CFT family that I began with. The entanglement game can be played here in the sense that one can construct generic states, reduce density matrices, take partial traces and construct a reduced density matrix for the remaining ghost spins, and then look at its one-element entropy. So for example, for 2 ghost spins, if you do this, the generic state has a norm which looks like this, and you can see that there are minus signs that come along because there are negative norm contributions from various places. The reduced density matrix can be constructed in this way by appropriate contractions. Since there are minus signs and so on, this contraction has to be defined appropriately. The one-element entropy can be then calculated like this, again with appropriate contractions defined correctly. The bottom line turns out to be that these negative norm contributions lead to imaginary parts of the of this entropy. Okay. Now, when I was doing all this many years back, I really had in mind just entanglement-like structures. But the whole point is that these sorts of ghost-like theories have non-trivial adjoints, and so while this looks innocuously like a density matrix, it really should be thought of as a transition matrix because the adjoint of a state like this is non-trivial. Okay, so this operation, these manipulations really do again give back pseudo entropies. Okay. Now these are toy models, of course, and it's a fascinating thing to ask whether one can do much more in actual examples of DSCFT. But that's a hard question. Okay. Yeah. So for DS, so these are just two-dimensional. So no, this replica was two-dimensional BC-CFT, just very basic toy models that we are familiar with as such. The DS3 CFT2 statement gives you imaginary central charge for DS. So it's not even in the class of these ghost spin families and so on. So these sorts of microscopic lattice models, I don't even know how to use to construct imaginary central charge. So this is good for negative central charge. So while these are 2 dimensions, and you can come back to the go from these lattice models to 2-dimensional BC-CFTs. We tried for a while to look at 3-dimensional ghost spin chains and appropriate. They were just technical things that we ran into, and then we just gave up. But the elements are basically, I think, all there. So I think versions of this should be usable and applicable to study the SPN model, for example, and so on for DS4. I think, but it's I think broadly there are hard questions, and we'll see more as we. Yeah, but over here, this was just an experimental observation, so to speak, that we found that in general you find complex objects. We were asking, is there ever anything positive? Are there positive structures that come along? And then we find that if you take 2 copies and entangle them identically, kind of like thermophile double type state, then in fact you do get positive structures. In fact, you can actually see examples of that right here. So in fact, if you just focus on this subsector, turn off this stuff. Generically, you get all sorts of stuff. But if you just focus on this class of states, then this is entirely positive, and that's the kind of thing that you can. Hard question. I don't know. We should. Yeah. So these are toy models, and they sort of they suggest that they have the same sort of structure, and there are other things that also happen, which suggest that there's some sort of object that one might think of as collectively bulk time emergent or something of the kind. But okay. So let me tell you a little bit about the deceptive extremal surface story now. So the simplest place to see this whole thing began, is just in the Poincare slicing. If you look at So what am I doing? I have planar slicer. I have planar slices. I take one of these planar directions as boundary Euclidean time. That's W. Then in the remaining, I call one of those things as the subregion width, and on that I define the extremization problem. If you do that, it's straightforward to do. If you do that, you find that there's a plus sign which correlates with the fact that there's a minus sign here, which came from the time direction. Okay, that plus sign is the thing that's responsible for saying that the surface doesn't turn back; it really just keeps going on. Okay. So there are these future past type surfaces which you can construct. So for example, in the static coordinatization, if you take appropriate slices, then you can reconstruct these things as certain rotated versions of these Hartmann-Maldacena surfaces in the ADS black hole. For global ones, you can show that these kinds of future past surfaces exist, which start from the future boundary and go to the past. The Hartle-Hawking one, the Hartle-Hawking no-boundary proposal is a statement that Lorentzian de Sitter evolves in time for a mono-boundary Euclidean initial configuration. So we cut global de Sitter in the middle on this moment of time symmetry, on the slice of time symmetry, and then we join the top half, the top Lorentzian half with the hemisphere in the bottom half, which for my purpose is going to be given by this analytic continuation. Now I can play the same game. I look at this SD at the future boundary. I take an equatorial plane as the boundary Euclidean time slice. On that SD minus 1, I look at the maximal subregion, just two hemispheres, and then the surface sort of goes anchors down from that boundary down into the bulk. You get this, and now if you calculate the area of the bottom surface, so the top part was just what I showed you for the future past ones. If you look at the bottom part, the bottom Euclidean surface has area which works out to be precisely half de Sitter entropy on the nose. Okay, in any dimension. So now the thing is, this emerges differently from the area of the cosmological horizon for static patch observers. So for example, one of the hemisphere directions here is the Euclidean continuation of what was time in the future universe. Okay. So so we've seen these future past surfaces and these no boundary surfaces. They're related in this way. The future past surfaces are the imaginary part of the no boundary surfaces, and the real part is related to half the entropy. For DS4, the area expressions work out to be like this. RC here is the future boundary cutoff over here. For DS3, it's an isolated example. The area works out to be like this, which you can recognize as two copies of the Calabrese-Riccardi answer with the DS3 CFT2 central charge put in. Okay, so the no boundary one, the area has this pure imaginary piece from the Lorentzian part and the real piece from the hemisphere, which you can recognize, which you can recast in this form, with C being this central charge. But this expression now has an interesting aside, which relates to a completely different branch of investigations that have also been happening parallelly on the entropy of time-like intervals and time-like entanglement entropy. If you look at ordinary Euclidean or ordinary unitary two-dimensional CFTs, the entanglement entropy is this expression, where this delta squared is a space-time interval between the 2 points. For ordinary space-like intervals, you get the standard Calabrese-Riccardi expression. But if you rotate this space-like interval to be entirely time-like, then this piece drops off. You get a minus sign here, and that minus sign gives you this imaginary part. Okay, and this object looks a lot like so this prompted me to write down these sorts of expressions, and then there's a whole class of investigations that happen here for just the entropy of time-like intervals. So this can also be recovered from the usual Euclidean CFT replica after, and then we rotate to the time-like interval. Okay. Everything I was saying was direct de Sitter, but you can also recover all these things from an analytic information from ADS. The analytic information in this case turns out to show that the ADS RT surface, which is like this, it starts from the boundary, goes all the way and goes back. This thing now rotates, and it becomes a space-time rotation. It starts from the future boundary, goes in, and then goes back. Okay, and the turnaround is in the hemisphere, not in the Lorentzian part. Okay, if you do this, you can also work out the areas and show that the areas precisely give you this for maximal subregions. And so in fact, the ADS answer, the ADS4 answer gives you this object. The ADS3 answer here gives you this object that I just showed you for DS3, and so on. Given the analytic continuation, an actual question to ask is whether one can formulate some version of the Ljukovic-Maldacena formulation, and recover these answers in that way from a replica point of view. And so I'm going to think of so because we are dealing with a wave function, we think of the Hartree-Locking wave function of the universe in this context as an amplitude or a transition matrix for creating the universe with final boundary conditions from nothing. In other words, satisfying Hartree-Locking no boundary conditions. Okay. Semi-classically, this wave function looks like this. It's given by the action, which is purely real, and so this is a pure phase in the Lorentzian part, and then the hemisphere part is given by the Euclidean gravity action, which then again works out to half the entropy. The Leuckoitz-Multizener formulation is a bulk ADS replica dual to the boundary replica entanglement entropy argument, and it follows from the ADS CFT dictionary that ZCFT is Z bulk, and so boundary entanglement entropy is bulk entanglement entropy. Okay, so replica here is a replica here, and both of these are partition functions, and so you recover the same sort of thing. In detail, if you construct a replica space, when you look at the quotient space, there are conical singularities which we then argue are sourced by a cosmic brane, and you can use that to calculate various things. For the DSCFT case, ZCFT is psi ds, the wave function, and so a boundary replica via ZCFT translates to a bulk replica on psi ds, on the wave function. Okay. So this interpreting this wave function as an amplitude or a transition matrix leads to pseudo-entropy. So this was a heuristic argument I had 2 years back, but there's very explicit construction that we have now, which I'm going to tell you very soon. A crucial point here is that the cosmic brane now is not space-like, because what you end up finding is that the cosmic brane is now Euclidean in the hemisphere part and time-like in the Lorentzian part, and so that the replica formulation here leads to the statement that this entropy or the pseudo-entropy is the area of this cosmic brane created from nothing. So now you could worry that this amplitude would be divergent if the Lorentzian part, which went all the way till I plus, was real. Okay, but on the other hand, you can see that the time-like part is a pure phase, and so that cancels the probability, and so in the end, the probability of this cosmic brane creation is finite and it's bounded. It's bounded from the bounded real part from the hemisphere, which is set by de Sitter entropy. Okay. So this was a heuristic argument based on the analytic continuation. You can actually flesh the great gory detail and actually construct these replica spaces, at least for some various subfamilies of real interest. So what we're trying to do is to extend the boundary replica at I plus to explicit de Sitter-like smooth bulk replica geometries. Okay. And then if you have these, then one can construct the boundary Rényi entropies by this formula. But then from here we go through DSCFT to here, and this then translates semi-classically to this expression for the boundary Rényi entropies. Okay. So for DS3, I have an S2 at the future boundary. The subregions I'm talking about are maximal. So on this S2, I take an equatorial plane slice. So that's an S1. On that S1, I construct a maximal subregion, which is this half circle. It turns out to be convenient for writing out these replica geometries to go to a boundary conformal frame where the boundary is a cylinder. So this is like the standard radial quantization story that we have. We go from the cylinder to the from the sphere to the cylinder, and that's what this is. So once you do this, this half circle becomes this full line along the length of the cylinder. Okay. In these coordinates, it turns out that after some thinking, after a lot of thinking, the correct replica geometry turns out to be this, where this phi is the angle around the cylinder, and it has replica boundary conditions. So it satisfies phi equal to phi is identified with 2 pi, phi plus 2 pi. So the idea is that, for example, for n equal to 2, we have 2 copies of the cylinder. We construct a replica space like this. We take cuts along the subregions, and we join the 2 copies appropriately in these replica boundary conditions. So the cut from here joins up to the cut from here, and this one joins back here, and so on. So in this case, as you can see, since the cut goes all along the entire length of the cylinder, what you end up with is simply a fatter cylinder. Okay, so the 2 pi periodicity here becomes a 4 pi periodicity. Okay, and that's what then leads to simplifications and writing of these replica geometries. Then there's a Euclidean part to this thing, which I'm not going to tell you much about here. It's straightforward to do. Then we evaluate the Rényi entropies using this expression, and this requires writing out the semi-classical action, and that requires going through this holographic renormalization story that we know, unique counter terms and so on and so forth. I'll suppress all that. The bottom line is that the Renyi entropy comes out to be this. It's a simple n multiplicative factor over this expression, and the n goes to one limit recovers the external surface area that I was telling you earlier. Okay. The plus sign here arises because we're talking about the expanding branch of the wave function, and this piece is one subleading term, so it's one L squared factor less, and that's why you get this plus sign. The cosmic brain here can be realized by looking at the same metric here, but now in boundary quotiented variables, where this phi now is phi plus 2 pi. And now you can see that there's a singularity at r equal to 0 here, which are the north and south poles. Okay, and this is basically, if you write this in conventional variables, this you can see that this is Schwarzschild ds3, where the energy parameter here is related to the n of the replica. Okay, and so as you can see that the cosmic brain here is time-like in this Lorentz group. Okay, so this was ds3. You can do the same sort of thing for ds4. Just there are many more features here, it turns out. It's convenient to work out these replica geometries for ds4 in hyperbolic coordinates. That's mainly because there's already old work of Rob Myers and company on ADS hyperbolic black holes and Renyi entropies and so on, and that was useful as a crutch. Okay. The main new thing here is that if you work out the replica story in the appropriate way, you see that these end up being complex geometries. So we construct a potential replica space. We have to invent a criterion for regularity, and the criterion for regularity that we choose is that this leads to a smooth Euclidean continuation, and basically a minus ADS type space. So this is something that is familiar from various previous studies that we've seen over the years. So we noticed this first long back in a paper with Shumit Das and Deeptarka Das on a complex version of a DS4 brain, which was an attempt at understanding DSCFT at finite at uniform energy density. The same sort of logic applies here. A regularity criterion comes out to be a smooth requiring a smooth Euclidean continuation for these sorts of things. But if you look at directly this object in de Sitter variables, this is a complex geometry, and it ends at a complex horizon, which is a complex zero of this blackening factor. Okay. The boundary Renyi entropy then can be calculated the same way that I was telling you earlier, and you get this expression, and in the end goes to one limit. You recover the external surface area and stuff. There are details here that are quite interesting because the embedding of this hyperbolic surface in global de Sitter is a rather non-trivial thing, and therefore this leads to interesting complexifications, which you can see from the embedding by using explicit embedding coordinates and so on. So this story can also be, well, I've said this whole thing for DS4 specifically. This story also generalizes for higher dimensions, it turns out. And overall, you can recognize that this is equivalent to some analytic continuation from the ADS story here. Okay. Everything I've said was for de Sitter. There's a whole separate story of this of entanglement-like structures with time-like separations, which are fascinating in their own right. So we've seen. So I arrived at this from studying de Sitter and all of these structures. So the takeaway here is that these de Sitter extremal surfaces anchored here do not return. So there's extra data that's required in the far past. So this suggests this looks a little like scattering amplitudes, final states from initial states, or time evolution. Okay. So a simple thing that one can try is to ask whether there are entanglement-like structures from the time evolution operator, regarded as a generalized density operator. This leads to reduced transition amplitudes and the entropy. There's various structures here which resemble finite temperature entanglement, but with imaginary temperature. Okay. So these objects connect directly with pseudo entropy if you look at the time evolution operator as a complicated object, but then look at components of this time evolution operator by appending projection operators. This object then directly dovetails with the standard definition of pseudo entropy. So an example you can look at in qubit systems is like this, and there's a circuit diagram representation for this object which looks like this. Okay. This is all with one copy. With two copies, you can construct a transition matrix like operator of this kind. How much time do I have? Am I done? Thank you. Okay, so I'm done. So this is all quantum mechanics. There's a lot of stuff here, but I'm not going to tell you all that. But now we go back to de Sitter and we can construct a cosmological transition matrix with two copies of the wave function of this kind, And now one can construct various time entanglement or pseudo entropy quantities in various contexts. There's a boundedness that comes along that you can see if you take the case where psi I minus is the same as psi I plus, and so this and that's the same as the Hartree-Locking wave function, and then a version of the replica argument shows recovers the entropy from the entropy of this transition matrix, from this entropy of this cosmological transition matrix. Likewise, you can do something similar for the entirely Lorentzian thing, which then leads to the future pass surface and so on. By DS safety, this suggests that there's a cosmological version that this cosmological transition matrix translates to some object involving two copies of this of ZCFT, which probably dovetails with two copies of Postman-like objects that I was telling you about earlier in those toy models. But this is something that we would like to understand more. Okay. So there's more that you can do with slow roll inflation, but I'm going to skip all that, and I'll leave you with these conclusions.
Questions? We might have time for one question.
Hi, thank you. So I have this question when you said that we can analytically continue from DS to ADS. So to understand more about what kind of CFT we want in DS, can we like analytically continue the CFT from the ADS side and check?
That is one of the things that Arrhenius Hartman's drawing were motivated by. So when they got the SPN ghost-like CFT that I was telling you about, what they did was the analytic continuation from the Klebanov-Polyakov ON model in ADS, in high-spin ADS4. So that's in fact how they got that, and that fleshed out a lot of things.
Thank you.
Hello. So here you have one wave function which is dual to entire partition function of the CFT, whereas as in ADS CFT we have like duality. I mean, two partition functions are same.
Yeah.
ZCFT, Z ADS bulk, and that tells me like there is some sort of isomorphism between the Hilbert spaces of the bulk and the boundary. But here, like it is many to one sort of like one state is dual to entire Hilbert space. And
but that state is really, it's the state of the whole universe. It's a pretty complicated beast. So it's not a light thing.
But is there then isomorphism between the Hilbert spaces?
I don't think it's a simple thing to understand the Hilbert space in this context, although there have been many studies on that.
I see. And one more question. Here, because you are entangling the CFT at the top with CFT at the bottom, and by some thermofield sort of, and we see like when we, in the ADS CFT, when we entangle two CFT right left, we get some connectivity, spatial connectivity. Is this why here we have like temporal connectivity due to ER, EPR sort of argument?
So this does suggest some sort of time like ER equal to EPR and so on. And in fact, in earlier versions of this, I had in fact, so I think that slide was not there in this. I was thinking of DS4 as dual to two copies of the CFT in a thermofield double type state, but with future past entanglement, whatever that means. But that version of the story for purely the Lorentzian thing is something I think we still need to understand.
Thank you.
Okay. So, hi, Narayan. So here, the pseudo entropy, has it been realized in like a more simplistic system like quantum mechanical systems? And
so all of this was in fact.
Yeah, look, can we have like the usual inequalities that we have for entanglement entropy? Similar inequalities, do they exist for pseudo entropy?
No, they don't. And what you get, I think I might have a slide on versions of the entropy inequality. So if you look at DS3, you can construct, the retrieval surfaces for generic subregions, and what you get is an area that looks like this. You look at multiple subregions, and you get, you can ask for the analogs of the standard entropy inequality combinations, and what you get are new things because they're all complex objects.
Yeah.
There are certain patterns because all of this encodes in some ways the analytic continuation, the entropy inequality structures that were there in areas that this came from under analytic continuation.
So you're basically comparing the real part in some sense.
No, so this entire thing collapses down under analytic continuation to the ADS side.
I
So the standard entropy inequalities that we know
I see.
in ADS map to these under anti-computation.
I see.
The question then is, are there independent ways of thinking about this intrinsically in Disitter? That's unclear, at least with one copy. Now I think with 2 copies there are probably more things that one can do. So this is 1 copy that I was doing. But there is something that one can do, which is to compare, for example, the inequality structures that you get for the real and imaginary parts for these things, and contrast them with what you get for just qubits. And already you can see that for qubits, in fact, the imaginary part can take both signs and so on. That was not true for the for the de Sitter side. So there are analogs of these observations that Hayden, Hildrich, Maloney began long back, which led to this entropy cone and so on.
Yes.
There seem to be analogs of that kind in the de Sitter side also, but
not well studied.
Not so. This is something that I noticed 2 years back and said that. But I think there's more that needs to be understood.
Thanks.
Maybe we need better organizing. We were sort of, I was sort of motivated by the standard entropy inequality combinations that we have in ADS for ordinary CFTs and so on, right? Maybe that's not the way to think in this intrinsically. Maybe it's another way to think also. Yeah. But then there were combinations of that in where if you took 2 copies, which made it real valued and so on. Maybe that's what one needs to do here.
Okay, let's thank Narayan once more. Next speaker is Ayan. Even longer titles. So Ayan will talk about how strings arise from gravity and can be decoded as quantum maps between theories.
It's working. Okay, so I'm going to talk about something that resonates with the first talk of today about the origin of string theory. But I have moved to Chile, and in Chile, string is not part of particle physics like in US or many other countries. It's part of gravity. So we are looking for a different origin story of string. If string or matter can arise purely from gravity, and the question would be how to see it as a holographic in the holographic way. So this talk will be based on these 5 papers. Actually, the 5th paper can barely get time to talk about, and the first paper was in last year with Abhik, whom Giuseppe also mentioned in his in the work that he was doing, and with Giuseppe. Giuseppe is here, and then there are these 4 papers that we have written. That one of them is coming out this year, and it's done mainly with Abhik. And Abhik has done most of the calculations, and Martin my PhD student has set it up. So he has he has done a brilliant push in this project, and many of the main significant conceptual issues were actually figured out together with Tanay, who was my previous PhD student. He's going to Argentina to join the group of Cassini and Huerta. And I will also mention 2 more papers whom I'm working with along the way. Okay, so here is the introduction. So string theory, the way it arises is that it unifies gravity and matter together. It gives a way to understand how you can unify gravity and all forces together in a consistent quantum framework. But you can ask some question that actually Einstein asked long ago, that can matter arise out of pure gravity? So according to Einstein, the right-hand side of the equation is ugly, but the left-hand side is pure geometry and beautiful. So he was trying to understand if you could bring matter, geometrize matter. And a precise way to ask this question is as follows. Find a gravitational action in which the metric is the only degree of freedom, so only the metric you are extremizing with. And can this gravitational action give rise to matter-like vibrations? So we can ask the question in this way. And this is the main results that I will talk about. The first result is that in 3D gravity, it is possible, certainly in 3D gravity, this is the main result that we found last year with Joseph and Avik Banerjee. And the solutions of these Israel junction conditions for 4-dimension 1 junction are in 1-to-1 correspondence with the solution of the full nonlinear Nambu-Goto equation for the string. So if you know, if for every solution of Nambu-Goto equation of the string, there is a unique solution of the Israel junction condition. So this is modulo something we call rigid parameters, we'll talk about later. But if you, instead of gluing 2 spacetimes, you can think also of junctions, which I'm going to talk about, gluing 3 or more Einstein manifolds. And here something beautiful happens, that you can get matter-like vibrations from pure gravity, even in the limit of the tensionless junction. So the junction has a parameter called the tension, and of course, and that's the only allowed parameter if you want the metric to be the only degree of freedom. You cannot write anything else. And but even if you take the tension to 0, you can get matter out of pure gravity, and this is something. So generally, n-way junctions are described by n-1 strings following the Nambu-Goto equations, the full nonlinear Nambu-Goto equations, but they're also coupled by Monge-Ampere-like terms, which I will mention. Now you can wonder why I'm sticking to 3D gravity. You can also go to higher dimensions, and here we will argue that matter-like vibration may arise from gravity only in form of the strings. It cannot come in kind of higher dimensional objects, only in the form of strings. And for that, you have to embed these multi-way junctions of 3D Einstein manifolds in higher dimensions. So I will talk about it later. And furthermore, these multi-way junctions in ADS also can be thought of in the holographic side as interfaces between theories. So if you have a 3D space-time, the dual is a CFT. So you can think of 2 quantum wires being joined at a point, and the string and the junction becomes duals to this interface, a point like object. It has, I mean spatially point, but it is a 0 plus 1 dimensional thing. So but this interface tells you it's like a quantum map. So if you give a state on the left hand side of the left quantum wire, there will be a specific state on the right quantum wire, and they also can be obeyed by 2 different theories. They can follow 2 different theories. So it becomes a kind of a way that 2 theories talk to each other, and the tension of the junction is a parameter of this quantum map. Now what we show is that these Nambu-Goto modes of the gravitational junction can be decoded in terms of these linear quantum maps, which generalizes usual conformal defect operators, for which actually Joseph get a very beautiful review in his talk yesterday. And they generalize this by one-sided automorphisms of the Virasoro algebra. I'll make it clear. So it's a very new kind of definition of. So you can actually decode this in terms of linear maps, and holographically, actually, you can think strings generally are the universal language through which different distinct theories can talk to each other. It's sort of you can see it in this way. That's the most kind of the way to see, another way to see strings. Okay, so now I'm going to the main part of the talk. So I'll talk about, just from the gravity point of view, not the holographic point of view, how strings arrive from gravity. As I said, it is the first work that we did with Avik and Joseph, and then it is thanks to this, we had very brilliant progress with Avik Chakraborty, who is a postdoc in Santiago, and he has done actually very work. And Martin was a very brilliant PhD student of mine. Avik is looking for postdoc now, so yeah, so I highly recommend him. And Martin is just in his first year in PhD. He's doing PhD with me, and Tanay, as I said before. Okay, so I'll also talk about 2 more papers. So let us directly go to multi-way junction. So here I'm taking 3, but you can take n. So what you have to do to glue different spacetimes, you have to consider n identical. So for the moment, I'm thinking of you need not do that. You can have many different 3 manifolds. But just to simplify, I will talk first to say you consider n identical copies mi of a 3 manifold M, and so these are the 3 copies of capital M, and sigma I are the images of the junction sigma in Mi. So you have 3 images. So it is sigma 1, sigma 2, sigma 3, and these are distinct, so they can have distinct profiles. They need not be the same. And what you have to do is that you have to discard one part of it. So you can take the left part and discard the right part. So the discarded part is shaded, for example. Here you are taking the right and left discarded, and then you have to take a point each in sigma 1, sigma 2, and sigma 3. Let's call them P1, P2, P3. and you identify these points. And once you make this identification, it identifies to a particular point P, and then you form this junction sigma. Okay, so this is the general procedure, and that's how you form a junction, gravitational junction. And the coordinates of mi, because mi's are basically identical copies of m, so all of these mi's inherit the same coordinates, ti, zi, xi, and z is the radial coordinate, and it's a longitudinal coordinate of the string, and xi is a transverse coordinate. And the embedding of these junctions of the strings in each of these spacetimes can be written as xi as a function of fi, ti, zi, and these are distinct embeddings. They need not be the same. And worldsheet coordinates. So now you have to define a worldsheet coordinates, because the gluing makes sense. Oh, these are simply the boundary interface. Yeah, this. Yeah. So there's nothing there. There is no point there. There is no mass there or anything. Yeah. Sorry, it is a it's just to yeah, maybe I should not have kept this. Okay, so now so you have to choose worldsheet coordinates, and it turns out that if you want to analyze it, it becomes easy if you choose this worldsheet gauge. So what I do is I fix the worldsheet time tau at the point P as the average time of all these embeddings. So every embedding has every embedding point Ti. So you're identifying P1, P2, P3 to form P. So I have to sum over the times, the bulk times of each of these coordinates, P1, P2, P3, each of these points, and I take the average of them, and that's my tau. And similarly, I take the longitudinal coordinate, longitudinal bulk coordinates Zi, and then I put sigma. So this is analog of choosing the temporal gauge in string theory. So this is how I fix my worldsheet coordinates. I could have done it otherwise. It would have been much harder to state the results if I did not do it. And then how many variables we have? So you have only fixed, we have only fixed average time, but there can be difference of the times can be arbitrary. So that the time coordinates of these different points that I'm identifying can have a difference, and that's a function of tau sigma. Similarly, the sigma di can be different. The relative spatial longitudinal space coordinates can be different. These are the z's minus zi plus 1. So you have n minus 1 of this t, z, and x, and this is the average x. So we have in total 3n minus 3, because n minus 1 into 3 plus 1. So we have 3n minus 2 variables, and these are the variables that we should solve directly from gravitational equations, and there is no other degree of freedom. So here is the gravitational action, which is just straightforward. It's a gravity in ADS, so we can generalize everything to flat space and also to de Sitter. But for the moment, let me talk about ADS. And then and this m tilde is the final space time that we get here. And then this is the tension, and because you have only the induced metric is not a new variable, it's induced from G, and there is nothing else because the metric is the only degree of freedom here, so we cannot add anything else here. And then there are n Gibbons-Hawking Y terms, York terms, and these are because actually you have this n surfaces, so there are n normals, so you have to add n Gibbons-Hawking York terms and other GHY terms if the other, so there's a boundary at infinity, you have to add those. And away from the junction, only this has to be varied, and you get a locally ADS free space. Yeah. Yeah, these are the GHY terms. Yeah, this is extrinsic curvature GHY. The Gibbons-Hawking York. Yeah. Yeah. So and then now when you state the action, you automatically assume that because you're gluing them, the induced metric should be continuous. Otherwise, you cannot write this action in the first place. So this is sort of and you see there are n minus 1 conditions here, and this is a 2 cross 2 matrix. So you get 3 into n minus 1 equations from here. And now if you vary this action with respect to the bulk metric at the junction, you will get the sum of all these things. So here what I'm doing is I'm assuming that I am actually taking the left parts of each. So if I take left part of one and right part of one, I will get a relative minus sign because the normals are oriented differently. But suppose for the simplicity, I'm taking only the left part of each of these junctions. Then I have to add it all with the plus sign. And this has to be equal to the contribution that comes from here and this is my this is the generalized Israel junction condition. However, if you take the Gauss law constraint, so this Brownian stress tensor, if you have a locally Einstein manifold, because this tells you that the away from the junction, a local Einstein manifold. So the Brownian stress tensor is conserved on its own by Gauss law constraints. So then these are the two equations. So out of these three equations, only one is actually independent, and therefore in total we have 3n minus 2 equations, and this is exactly the same as the number of variables that we have, 3n minus 2. So essentially you should, so from these 3n minus 2 equations, you can solve for the 3n minus 2 variables. Okay. So this will determine, and this is the solution of the junction function. So once you have a solution of this 3n minus 2 variables from this 3n minus 2 equations, you will have a specific gravitational junction. Okay, so now let us talk about the general results. So first, let us take the two-way junction. This goes back to a paper last year with Giuseppe and Abhik Banerjee. So, so you can show that this is in one-to-one correspondence with the solutions of Nambu-Goto equation. And how to see that? You first constructed auxiliary hypersurface, which is, so once you solve the gravitational junction, suppose here you have only 4 variables because you have 2 ways, so you have 4 variables. So you have a very complicated solution of the, say, of this thing. But you remember that we are gluing we have the same manifold copies. So this M is so we have 3 copies of the same manifold. So I'm talking of this manifold M, where we are replicating the coordinate charts n times. So in this manifold M, you just construct this auxiliary surface, which is t equals to tau, z equals to sigma, and x is equal to xd tau sigma, where xd is a solution that you obtain from the solution of the gravitational equation. It turns out that these hypersurface, the solution of nonlinear Nambu-Goto equations in M, when the tension and the 6 rigid parameters vanish, I'm going to say what are the rigid parameters. So once these vanish, you get a specific solution of the Nambu-Goto equations. And once you make a choice of this Nambu-Goto solution of the nonlinear, or the solution of nonlinear Nambu-Goto equations, the other variables, the other 3 variables, tau d, sigma d, and xs, they're completely determined. So the Nambu-Goto is the only degree of freedom of this system. So there's a one-to-one correspondence between the solutions of Nambu-Goto equation and the junction conditions. Now, what are the rigid parameters? These are 6 in number, and these are essentially, there are 3 wall sheet isometries, and because I can always do a wall sheet isometry, it will not change my gluing condition, because it doesn't change the induced metric, so the induced metric will still be continuous. And then I can do 3 space-time isometries. So ADS, if you have a locally ADS3 space-time, there are 6 isometries, but 3 of them preserve the junction and 3 of them displace the junction. So these 3 which displace the junction will not change the extrinsic curvature. So therefore we have, so these will be also, will preserve the solution that we have. So there are these 6 rigid parameters, and in the tensionless limit, so if you take the tensionless limit with this presence of the 6 rigid parameters, the solution is not a smooth manifold. So it's a non-trivial, only if the rigid parameters is 0, in the tensionless limit you get a smooth manifold. However, only 3 rigid parameters which are related to wall sheet isometry survive when we impose the Dirichlet boundary condition of the end point of the string. So if we say that that these 2 copies have to end at a very specific place with some Dirichlet boundary condition, then actually you kill many of these rigid parameters. And another important thing is, if we glue the left side of M1 to the right side of M2, then actually you have to simply interchange XD with XS here, and XD will go here. So the average embedding satisfies the Nambu-Goto, whereas the XD will be determined by XS. Okay, so these are the simple changes. Now you can say what happens for if we go multi-way junctions for n greater than or equal to 3. For 2, we have 1 degree of freedom, which is the Nambu-Goto. If I take more than 3 or more, then there are n minus 1 degrees of freedom. And these, how to see and what equations are satisfied. So you have to consider again this n minus 1 hypersurfaces. Again, I'm assuming I'm only taking the left side of each of the manifolds and gluing them. And these n minus 1 hypersurfaces, they satisfy Nambu-Goto equations in M, but they're also coupled with each other, and they're coupled with each other with Monge-Ampere-like terms. And then in this case, the remaining 2n minus 1 variables, and these are determined by the choices of the solutions for these coupled Nambu-Goto equations. It's exactly like the two-way, except that you have more degrees of freedom, and these involve this coupled string. Okay, so for concretely, we can start by gluing n identical BTZ black holes, and these BTZ black holes have this metric, and we are taking n copies of this. And now it's useful to consider this dimensionless parameter lambda, which is 8 pi g, and this is not a 2 coupling. This is simply the parameter of this tension of the junction, and we say this is order epsilon, and we set the ADS radius to 1. So there is a trivial solution when we take the lambda to 0, and this solution is simply that all the parameters vanish, and this xs is at a particular point x0, and then if you perturb it at the first order, you find this, that x is perturbed by lambda by n, and up to there is no epsilon square correction actually, there's only epsilon cube. And then if you actually see what the xdi satisfy at order epsilon square, they satisfy these coupled Nambu-Goto-Monge-Ampere equations. The left hand side is simply the Nambu-Goto equation for xdi in BTZ metric. This is simply the Nambu-Goto equation, and these are Monge-Ampere like terms. And if we go to higher order, you will get the full nonlinear Nambu-Goto actually here on the left side, and everything will be multiplied in overall lambda, because Nambu-Goto has no lambda in it. So this is you will simply see that. And then these couplings are happening with Monge-Ampere like terms. So this is a self coupling, and this is a determinant of this Hessian matrix, and this is it's simply something like this. You can obtain for it by replacing xdi with xdi xdj, and but we do not know what are the higher order terms here. So we do not know what is if you go to higher orders, what exactly happens here, we do not know. So we have only done up to this order. So for the two-way, we understand to all orders in perturbation, but for the three-way or higher, we only understand up to this order. And then we can show that the other variables are completely determined once you choose a solution of these equations. And for this, Abhik Chakravarti has done a brilliant work, and he has really shown this. I don't want to go, it's a bit technical, so I'll not tell you here. Okay, so but the paper is on the archive, you can look at it. So now if you look into solutions of these equations, how they look like. So if you go to this coupled Nambu-Goto-Monge-Ampere equations, and when the tension is not 0 and say n is equal to 3, you have two variables, and these are two dynamical variables. And in general, the solutions are like that, where a1 and a2 are functions of time, and these are the amplitudes of the Nambu-Goto modes, and then you find corrections. And however, when you take the tension to 0, you see the tension to 0 is like a little bit of singular limit, and then you have to only the Monge-Ampere only survives, and there's a lot of Fields medal work on Monge-Ampere, and then you see that you have this you have these solutions in this case, and it starts with sigma square instead of sigma, and then yeah. And actually, so what happens is that when you have n greater than equal to 3, there are non-trivial degrees of freedom even in a tensionless limit. So even in a tensionless limit, we get non-trivial degrees of freedom because B1 and B2 are not 0. Yeah. So so these was what I was saying, that you can get matter from pure gravity if you take tensionless limit, but you need to have more than 3 or more. You cannot just do it with 2. And the important thing is that the Nambu-Goto equation is encoded in the time reparametrization. So let me go back to this picture. So what happens is that when you go to the boundary, when you look at this, so gluing say this with this, so this is the time at the boundary. They are not continuous when you at the boundary at this endpoint. And actually, so you might find what is this weird? I mean, if there's a discontinuity of time. But actually, what you can do, you can actually undo this time difference with a conformal transformation or with a bulk diffeomorphism, and then you can convert it to a quantum map. So basically, you can establish continuous coordinates and metric at the boundary. So for that we see later. So, but the main point is that this is what is controlling the quantum map that we'll discuss later. Is that these relative time differences are completely determined by this Nambu-Goto amplitudes, which is the amplitudes here. And in the tensionless limit, you have this other B1, B2, and they are determined in this manner in this kind of equation. Okay, so I will skip the de Sitter part. Maybe I'll come back to it at the end of the talk here. So de Sitter part is. So now you can see what happens in higher dimensions. In higher dimensions, actually, these are the number of variables that you get, and these are the number of equations from the junction conditions, the independent equations, and the system is overdetermined unless d is equal to exactly 3. So if you want to get matter-like vibrations from gravity in higher dimensions, what you have to do, you have to embed this multi-way junctions of 3 manifolds inside this 4-dimensional space-time, and then in this intersection, this red line, you will get this string-like, so matter vibrations can come in the form of strings. So it cannot come in the form of higher dimensional branes, it will only come in the form of strings. Okay, so now I come to the second part, which is decoding strings as quantum maps between interfaces between theories, and these are these 3 papers. So, I mean, I already said that, so you can think of an interface as some kind of 2 ways. One is a map between the Hilbert space of the left theory to Hilbert space of right theory. So if you have a state here, the interface will tell you what state you have on the right side. And the other way to think about is in the scattering way. So if you take 2 excitations, one moving to the right, one moving to the left, and they convert to one moving to the left, one moving to the right. So this is a scattering matrix, H in to H out. And you can also write it in this way. So there are 2 ways of thinking of an interface. And so the mathematically or even physically, a conformal interface has a particular, so this is ILR is a map from left to right. They commute with this, they have this property. This is something that Joseph has reviewed in his talk, and I don't give references. And so this is sort of a condition that this map should satisfy. And there is a folding picture, which I skip now. And what was shown, and this is from, actually, this figure is from Joseph's slide. So this is the Maineri Penedos-Rousset result in 2019, that all conformal interfaces have universal energy reflection and transmission. So you can create this thing with an arbitrary operator and take this operator to infinity, like this, so that you can think of in terms of S matrix incident from infinity. And then the reflection or transmission coefficient is universal of the operator. And when the 2 sides have the same, 2 CFTs have the same central charge, this is basically given by the CLR, which is that controls the 2-point function of stress tensor between one side and the other side. And the N bound, which was discussed by Joseph, is simply the CLR should be less than C, and this means the lambda is 0. So this is the CFT result that was obtained by these people. And what happens when you have a junction that has Lambo-Goto modes? So what is going to happen is a gravitational junction with quasi-normal modes generalize this conformal defect operator to something like this. So you have the usual, so you have the usual Virasoro algebra on this left side, and the transform Virasoro algebra on the right side, and these are related by some kind of transformation, a similarity transformation. This is not necessarily unitary. So if you just retain this part, this is like a conformal transformation. So ln's will only go to linear combinations of ln's plus some constant, and then this will actually give you some nonlinear thing. And this is something, so this map is actually a linear map in Hilbert space, but the transformation, this automorphism can be nonlinear if you consider these higher terms. And essentially what the Lambo-Goto modes do, they determine this alpha p and alpha rs, these kind of factors. So of course we have only gone up to the first order, and this we see the alpha p explicitly. And so essentially you can now think of this. So how much time I have? Probably 5 minutes, and I started at 1, so I surely have 5 minutes. Yeah. Anyway, so the gravitational junction you can decode in terms of quantum maps, and these characterize the dual holographic interface. So you can think of for each Lambo-Goto vibration of the junction, you will get a distinct HL to HR map or a distinct H in to H out map. And to do this, you basically construct this Bernoulli's geometries. And so these are all, but the only difference from what we did before is that you don't have the same, M1 and M2 are not identical. They're 2 distinct Bernoulli's geometries, and these actually capture the fluxes, energy fluxes that come in and come out. And so we are only in the universal sector, so we have only this. And so if you go to what equation XS, now we have XS because instead of XD, because we are doing the left and right part of the 2 manifolds. So the left-hand side is exactly what I said before, it's just a Lambo-Goto, but the right-hand side, there's a source term now because M1 and M2 are not identical. So you get an additional source term that determined by these fluxes. But now we are perturbing exactly, so we are keeping lambda exact, so it's an exact solution. This is a static exact solution, which actually Giuseppe and Costas and Shiva Chapman analyzed like 5 years ago, and this and then you and then this is also what they analyzed, but now we are also going to consider Nambu-Goto modes. So this is most general solution of X's. So one part of it is you say there is a causal response. So ingoing boundary condition at wall sheet horizon, and if you just put ingoing boundary condition, you cannot determine it completely. So additionally there will be a quasi-normal mode, because you can have some initial conditions in ADS CFT, and so you have one free parameter which is AN, and Giuseppe and other people, Giuseppe and Costas and Shira, they fixed it in some way. So you can solve for sigma d tau d, and they fixed it by requiring that there is a Dirichlet boundary condition for tau d sigma d actually. So now if you put Dirichlet boundary conditions, so both xs and xd should be ending at 0, and this xd equals to 0, as Giuseppe said, it implies this conformal boundary conditions. And if you set xs is equal to 0, you fix this non-normalizable mode, which is the ANN. Yeah, this ANN mode, the non-normalizable mode, is fixed by the normalizable mode is a Nambu-Goto mode, which is a solution of the homogeneous equations. Here is a solution of simply the homogeneous equations, and this is free, but this non-normalizable mode get fixed by the Dirichlet boundary condition, and this is simply the implements for the XD, it implements a conformal boundary condition of the defect. Now what actually Giuseppe and they did, this paper in 2020, they actually set also Dirichlet boundary conditions for tau d and sigma d, and they had only one input flux, and they took the static homogeneous solution of instead of the full general Nambu-Goto solution. So, but this has some drawbacks. So the firstly is that the gravity is nonlinear. So independent reflection and transmission of input fluxes from left to or right has to be demonstrated. You cannot assume it, because if you make some assumption at the linear order, it might create inconsistency at higher order. You should just take the most general perturbative solution at the first order and then see what happens. Also, it is not possible to demonstrate in this method the universality of reflection transmission process, because if you go back to the CFT side, they say that it's this result is independent of how you are creating this energy flux, which operator you're using. So you have to demonstrate both, and actually we have succeeded in doing that. And the trick that we do is as follows. The trick is that yeah. So let me just go here. So you see that okay. So let me put it this way, that you have the T2 and T1 at the boundary is discontinuous, and they differ by this Td, which is simply the boundary limit of this tau d. That's the definition. And then you can define this H2 and H1, and then what you do is that you do this conformal transformations on both sides, where H2 and H1 are given by this, and see alpha is an arbitrary parameter. This alpha plays the role of arbitrary. Instead of having the vacuum as a base state, you can have some Bernoulli as a base state, some other universal sector state, and this alpha plays that role of choosing of showing or demonstrating universality, that it doesn't matter how you're creating this energy flux. Okay, and when you do this conformal transformation, it's easy to see that when x1 and x2 is equal to 0, where the interface originally was, x1 tilde 1 and x1 tilde 2 is also 0 when you put x1 and x2 to 0, and when x1 is equal to x2 is equal to 0, T2 is equal to T1, because actually T2 is equal to h times. So you can easily see from here. Actually, from here, the T2 will be equal to T1 in this specific case. Yeah. Okay. So and that is how you define this function h. Okay. So so now this conformal transformations can be uplifted to different bulk diffeomorphisms. And under a bulk diffeomorphism, induced metric and extrinsic curvature transforms as scalars. So we will get equivalent solutions of the junction function. So we preserve the junction function. Anyway, but what happens is, so we have now established continuous metric and continuous coordinates across the interface of the boundary. But the physical stress tensor due to these conformal transformations will change. And these are the physical fluxes that the observer will measure, that the experimental will measure. And then you see that I don't know why the tildes have disappeared. So what you find, sorry, maybe. So anyway, so what you find after doing all this, that these are the general things. And if I just impose this conformal boundary condition that comes from Dirichlet boundary condition of XD, I will get TL and TR as two arbitrary parameters. And this is my explicit time reparameterization at the boundary, which I'm undoing with conformal transformations. And if I do that, then I see that I have, these are my physical fluxes. It's not important explicitly, but you see that these physical fluxes have 4 arbitrary parameters, TL, TR, alpha, and all this. Remarkably, if for all values of these parameters, you get this conformal boundary condition and a very universal map, which is here. And so this universal map is a scattering map, which is composed of this CFT scattering operator, which does not depend on how you're preparing the state. And then the rest of it, this D, is basically an energy redistribution map, which acts differently from left and right. And so this is a conformal transformation that acts differently on left movers and right movers. So you can also write it as a left to right map. And this is also universal. So I don't want to now, okay, maybe I should. But the important thing about this universal of this map, I just need 3 minutes. Yeah. So, so important thing is that this quasi-normal mode A and omega, which actually controls this this kind of this conformal transformations that you see in the HL to HR map or in the H in to H out map. So these actually is a omega dependent, but these should vanish as omega cube at small omega. That is because if you look into this explicit value of TD, you see that there is a 1 by omega cube. This actually gets removed when you take the Schwarzian derivative. So there omega cube that comes from top here. But this omega, so therefore A and omega has to vanish. And similarly, all the fluxes have to vanish as omega cube. So, yeah, so that is what it is. And if you do that, then actually this unitarity and NX bounds are satisfied, because when you put this condition, the NX operator sees the 0 mode. And this 0 mode is not affected by the conformal transformation. And these and the NX bound simply says your lambda should be greater than 0. That's all the NX bound says. So which is anyway satisfied. So so there is no violation of this. But one very interesting thing about this, so this is how the Ward identities look. The displacement operators become functions, become state dependent. And but the interesting thing is that you cannot tune the tune this junction to be completely topological if you tune the ANs, which means that you have perfect energy transmission and the expectation value of displacement operator, so the Ward identities become perfectly satisfied. And you can also tune it so the junction becomes factorizing, so you have perfect energy reflection in this case. So the junction becomes a tunable energy transmitter, and we can realize actually quantum gates with this junction. Anyway, so I don't have, and similarly, but I will skip this. You can show that in the special case of this, when you have a thermal background on both sides, you can resum the perturbation theory and show that this thing is a causal process. This scattering is a causal process. But the main point is as follows. So you have, as I said, this is the generation of the defect operator in this case. And alpha p you can explicitly calculate, but we have to actually go to nonlinear order. And if you go to nonlinear order, L4 can, for example, mix with L2 square. So these kind of corrections can also arise at nonlinear order. This is something that we have to do. Yeah, and we have been able to generalize all of these things to the n-way junctions also. I don't have time to talk about the entanglement. So I just end with an outlook. So I just need a minute. So, okay, so upshot of all this is as follows. So somehow it seems like a non-exotic string theory because we start from gravity and there is no other ingredient here, only pure gravity. But 3D gravity can be quantized, right? So you might wonder if you can get a version of quantum string theory by quantizing 3D gravity with the junctions. And I don't know how to do it yet, but this is an interesting thing to think about. And holography, what it means is it seems like a third quantization, like quantizing quantum maps. But it's not that crazy, because what happens is that these quantum maps actually have this automorphisms of the Virasoro algebra. And these automorphisms, these parameters of this or one-sided automorphisms will be determined by some wave functional in a probabilistic way. So maybe it's not so super exotic. The other thing is that, as I said, that you can also generalize to higher dimensions by embedding the multi-way 3 manifold junctions in higher dimensions. Now you can wonder, if I now quantize these junctions and not the gravity itself, whether I can get the graviton. So that's an interesting question. I don't know. So now another question is that we can try to see how do we actually generalize, how to realize what kind of physical ways we can implement this automorphisms of the Virasor algebra and create this fine-tuned quantum processor, tunable quantum processors. And maybe we can patent this, so we can actually what we know is that this is possible, and then we can try to see how to actually make it happen. So that's beautiful. So here you predict some very new kind of quantum technology from gravity. But one important thing I want to say here is that okay, maybe I should skip it. Now we can also generalize this construction to space-like junctions. Okay, and this is a work which I'm doing with Sumit Das and my PhD student. So here the interface operator is a very complicated thing. It's not a usual quench. But here, if you go to the word identities that I described here, so instead of a displacement operator, you get an energy cost. Yeah, that was the word entity. Yeah, these word entities have an energy cost, but here it is 0. And this would be the way you can go. Really, it's a theory changing. You can translate from one theory to the other. And this is very fascinating also, and this should also exist in the theory if you quantize it. So it's interesting to understand it. And the final thing is that there is no initial value formulation of classical gravity with junctions, but the full solutions are causal, as that we can check by explicit resummation of like perturbation theory and determine self-consistently. And it can also potentially change your understanding of quantum gravity in de Sitter space. So let me just say this thing for 1 minute in my talk. This is my last thing to say, that I will say. So I go back to the beginning, so to this slide that I had on this de Sitter. Yeah, so what happens is that, I only talk about this. So if you think of a three-way junction in de Sitter, so if I take a two-way, then there is a string vibrations. So if you take the string on the equator of these two, that's an exact solution on Nambu-Goto. And the other solutions are transient fluctuations of the string, which vanish in the far past and far future. But they are actually born out of some kind of gravitational memory, which is like time shift and the radial and an angular shift across the two hemispheres at early time. So essentially, you set up, all strings set up their own clocks, and in a closed universe. So this is very interesting because many people argue that if you cannot set up a clock, your quantum gravity in de Sitter should be just one-dimensional space. And the other thing that you can do, if you now take three-way junctions, even without tension, you can actually create de Sitter from nothing. So what happens is that as you go back in time, you lose de Sitter volume, or you lose de Sitter space, but the volume is also expanding, and together they cancel out, and de Sitter space just goes to a point, and this point actually has a finite volume. So although it's nothing, it can have some DNA that can. So there could be some nothing states in quantum gravity that gives a DNA for the creation of the universe. And this is quite fascinating, and this is something that requires beautiful understanding. So this is all that I want to say. Yeah, thank you.
Unstoppable Oyunda, thank you. I'm afraid we do not have time for questions. You have some announcement to make.
So, sorry. So today we have to start the next session sharply at 2:30. Sorry for cutting down on your lunch time. Yeah, I can't help it. So, and also there is a public lecture by Ashok at 5. So there will be buses from here at 4:45 to take you to the auditorium. Huh? Here, IIT auditorium. Here.
So, am I hello? Am I audible? Yes, everything is fine, right? Okay. Yeah. I can hear you. করছি। Um, করছি ଟିକେ। 1 second. Present করছি কিছু ଗୋଟେ। पूरा proper ଆସୁଛି। ଅଡିଏନ୍ସ ଦେଖିପାରିବିନି ବଟ୍ ଟକ୍ ଶୁଣିପାରିବି। ଅଡିଏନ୍ସକୁ କହିଲା ବେଳେ ତାଙ୍କୁ ଆନାଉନ୍ସ କରିବାକୁ ପଡିବ ଯେ କାଇଣ୍ଡଲି ଟିକେ ମାନେ ଇଏ କରିବେ। ମୁଁ କହୁଛି ଟିକେ ରୁହ। ନା କହିକି ଆରମ୍ଭ କରିବେ। ଜଣକୁ ବସାଅ କ୍ରାଉଡରେ ବସାଅ କୋଶ୍ଚିନ୍ ପଚାରିଲା ବେଳେ ତାଙ୍କ ପାଖକୁ ଯାଇ କିଛି ପଚାରିବାକୁ ଟ୍ରାଏ କର ମତେ ଶୁଭୁଛି ନା ନାଇଁ ମୁଁ କହିବି ଠିକ ଅଛି। ସ୍କ୍ରିନ୍ ସେୟାର ହେଲା। So on the stabilizer of complexity of Hawking radiation. I can hear you. I can hear you. I can hear you. Okay, going good. This is the full screen. It is the full screen. I mean ତମକୁ ଦେଖା ହଉଛି ବୋଧେ ଏଇଟା ଯୋଉଟା ଉପରେ ଆସୁଛି right? Wait a second. ହଁ minimize କେମିତି କରନ୍ତି? Next second. ଗୋଟେ ଥାଏ କୋଉଠି? ନାଇଁ ରୁହ। Spotlight nahi auto रे not like this. This one will be good. Wait a second. Now ଏଟା spotlight ତ ତାଙ୍କୁ ଇନଫର୍ମ କରିଦବ kindly put it into a spotlight. ତ ଓପନିଂ ସ୍କ୍ରିନ୍ ରେ ଯାଇକି ରେଜ୍ ହ୍ୟାଣ୍ଡ ପାଖରେ गोटे ट्रिपल डॉट थाए से ट्रिपल डॉट जाई कि एडजस्ट व्यू जिबे एडजस्ट व्यू कि स्पॉटलाइट प्रेजेंटेशन ऑडियो विल बी देयर तो तांको मोबाइल स्क्रीन रे जहां भी ऑडियो थिबो सेटा भी सुना जिवो किछि इशू नै तो तो एक बार लाइव लाइव का चेक कर लो बस Um, I mean, doesn't matter, right? Um, whatever. Cameraman କିଛି କାମ ନାହିଁ ଏଠି only କି ଅଡିଓଟା ଯାଉଛି ନା ଖାଲି ଦେଖ ନାଇଁ କ୍ୟାମେରା ଖାଲି ଅଡିଓଟା ଯାଉଛି ନା ନାହିଁ ଷ୍ଟ୍ରିମ୍ ରେ ଦେଖ ବାସ୍ ଖାଲି ଭିଡିଓ ହଁ ଭାଇ ଖାଲି ଅଡିଓଟା ଖାଲି ଅନ୍ କରିକି ଟ୍ରାଏ କରନ୍ତୁ ଯେ ଅଡିଓଟା ଯାଉଛି ନା ନାହିଁ ଷ୍ଟ୍ରିମ୍ ରେ ଷ୍ଟ୍ରିମ୍ ରେ ବି ଯାଉଛି ରାଇଟ୍ ଠିକ ଅଛି ଫାଇନ୍ ଫାଇନ୍ ହଁ ସେ ଏନଫ୍ 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 ଦେଖି ଦିଅ ହେଇଗଲା ନା ସବୁ ଠିକ ଠାକ ଚାଲୁଛି ଫାଇନ୍ କଲ୍ କାଟିଦେଲି ତ 5 ମିନିଟ୍ ପୂର୍ବରୁ କ୍ରିଏଟ୍ କରିବ ହେଲା ଏବେ କ୍ରିଏଟ୍ କରନି
हाँ उसी से मीटिंग बनाओ ना मतलब कुछ गड़बड़
Can you hear? Hi, can you hear me? Hi, Abhishek. Uh, I'm just trying to, yeah, I'm just trying to figure out how to share my screen. One second. You can hear me clearly, right? Okay, just give me 1 second. Can you see my screen now? Uh-huh. Click on the three dots. 1 second, just 1 second. Just 1 second. Just 1 second. I'm trying to figure this out. Yes, this one. 3 bars by the side. Wait, present. Yeah. Can you see it properly now? I can hear you. Can you hear me? Yeah. Just to check, can you see my pointer? Yes. Can you hear me? Yes. 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 Yeah, yeah, of course, of course. At 3:30. No, no, no. Of course not. Yes. Of course. Of course, of course. So I'll make sure to stop at 3:30 sharp, right? Okay. Can you see my pointer?
Something right now.
Okay.
Once your screen reappears, yeah, show me your pointer. Yeah, we can see it. We can see it. Brilliant.
Okay.
Yes.
Okay, great, great, great. So just tell me when to start and I'll
Yeah,
get
yeah,
going.
I'll tell you. Yeah. 2 more minutes.
Of course.
All right, welcome to the post-lunch session. So we'll start this session with a talk by Onkar Parikar from TIFR. And then, the title is Stabilizer Complexity of Hawking Radiation. Onkar, you may start your talk.
Great. Thank you. Thank you for inviting me to this conference. And let me begin by apologizing for not being able to be present there in person for various reasons. Second of all, I should also say that my voice is a little bad today because of a cold. So if something I'm saying is not clear, then please just ask. Okay. So this talk is going to be about a recent paper that we wrote and some work in progress with my students Ritam, Abhiroop, Suprakash, and Harshit. They're all excellent students, but Ritam, Abhiroop, and Harshit are all applying for postdocs this year. So if you're looking for postdocs, please take a look at their applications. So let me begin by saying that recent work on the black hole information problem has shown how to reproduce a unitary page curve for black hole evaporation, at least in the context of ADS-CFT, from the quantum Ryuta-Kainaki formula. And sort of what happens is that before the page point, one finds that the quantum extremal surface is the empty surface and the radiation entropy grows with time. But after the page point, a new quantum extremal surface appears close to the black hole horizon, and the entanglement wedge of the radiation system includes the island or a region, a portion of the black hole interior, and then this phenomenon sort of cuts off the growth of the entropy. Now, while this is sort of an elegant resolution to the information problem, it also points to an essential non-locality in quantum gravity because, for instance, after the page point, a portion of the black hole interior is encoded in the radiation. And so an observer with access to the radiation at infinity can perform, let's say, a unitary deep inside the black hole interior. This ordinarily, this would be like a flagrant violation of causality. But several authors have conjectured that such operations which manipulate the black hole interior from infinity in an apparently acausal way should be exponentially complex. And so in some sense, the semi-classical notion of space-time is an emergent notion for low complexity operations. This idea that manipulating the black hole interior from out at asymptotic infinity should be a complex operation was then geometrized and in many ways generalized in ADS in the context of ADS-CFT in what is called the Python's lunch conjecture. The authors of this work conjectured that whenever a boundary subregion in ADS-CFT has multiple extremal surfaces homologous to it in the bulk, then bulk degrees of freedom in the Python's lunch region, namely the portion of the entanglement wedge behind the outermost extremal surface, i.e. Behind the outermost but within the entanglement wedge, are sort of exponentially hard to reconstruct. And not just that, but they gave sort of formula in terms of, for the complexity of bulk reconstruction, in terms of the exponential of 1 by g Newton times the difference of the area of what is called a bulge surface in the Python's lunch and the outermost extremal surface. Okay, so these last 2 points points are sort of, if you like, complexity conjectures that have come out of thinking about the black hole information problem in recent years. And the point of this talk will be to argue that what is called the theory of stabilizer quantum computation can provide a useful language to make progress towards these complexity conjectures and actually do some useful calculations in this direction. Now, a central object throughout this talk is going to be the discrete Wigner function. So let me begin with a review of the discrete Wigner function before we get into the gravity calculations. But before that, are there any questions about the motivation? Okay, please feel free to interrupt if you have any questions. So let me go on. So many of you are probably familiar with the Wigner function in the standard quantum mechanical case. If you have, let's say, a particle moving on a line in some potential, then the Wigner function is a quasi-probability distribution in phase space defined as shown here. So given any density matrix rho, one defines a function W of Q comma P, a function in phase space, which sort of tries to mimic a probability distribution in phase space, as would be the case for a classical system. Equivalently, you can think of the Wigner function as the trace with respect to rho, or the expectation value of a certain operator, A hat, called the phase point operator. This phase point operator, what it is basically a Fourier transform of what we call the displacement operator, the thing in blue over here. And very heuristically, you can think of this phase point operator as being some sort of a delta function localized operator in phase space. Okay. Anyway, the point of the Wigner function is that it sort of mimics a probability distribution in phase space. For instance, it is normalized. If you integrate it over phase space, you get 1. If you integrate the Wigner function in either just P or over Q, then you get the probability density in Q or P. But the Wigner function is not a probability distribution, as you might have guessed, and that is because in general it can take negative values. Now, states for which the Wigner function is everywhere positive can be thought of as classical states in some sense, and we'll discuss this more in detail below. But just to give you a hint of why this might be a reasonable thing to do, if you look at pure states, then the only states which have positive Wigner functions are Gaussian states, and so in some sense generalized coherent states. So that seems like a reasonable thing to say. Now, so far, the discussion was about the continuous case where the Hilbert space is L2 of R. But for this talk, it will be important that Wigner functions can also be defined in finite or for finite dimensional Hilbert spaces, as has been shown in a series of papers over the years, especially in the quantum information community. So the way one proceeds in this case is that for a Hilbert space of dimension capital D, I'm going to call the dimension of the Hilbert space capital D throughout this talk. The phase space is taken to be a lattice, ZD times ZD, or basically a set of D squared points, if you like, labeled by Q and P, position and momenta, which are both discrete in this case. This formalism, at least the formalism of the discrete Wigner function, works best when D is prime, or actually more generally even a power of a prime. But much of what I'm going to say can also be generalized to general dimensions. But for sake of convenience, I'm going to restrict myself to prime dimensions in this talk. So the way you define the discrete Wigner function is that at first or foremost, you have to pick, you have to make a choice of an ordered orthonormal basis. I'm going to call this Q. So this is just a choice of an ordered orthonormal basis labeled by integers 0, 1, 2, and so on, up to d minus 1. And then with respect to this choice of basis, one defines the clock and shift operators. So the z's here are, roughly speaking, exponentiated position operators, and the x's, the shift operators, are, roughly speaking, exponentiated momentum operators or translation operators. And now once you have a notion of exponentiated position and momentum operators, that is essentially what displacement operators are in classical quantum mechanics. So the fixed point operators are then just defined as Fourier transforms of these displacement operators. So in complete analogy with the continuous case, one can define the discrete displacement operators in this way, and you can check that if you do that, then the formula one gets is very analogous to the one that one has in the continuous case, and then the Wigner function is just defined as the expectation value of these phase point operators in your given state. I'm sorry, I wrote this formula for the Wigner function in the case of pure states, but it's equally valid for mixed states. just replace the expectation value here with trace of rho of the phase point operator. Okay, so that's how one defines a discrete Wigner function for finite dimensional quantum mechanics. And no, I should have pointed out that this Wigner function is a function of two discrete labels, Q and P, each of which go from 0 to d minus 1. Okay, so just like the continuous case, the discrete Wigner function is also real and it's normalized. If you sum it over entire phase space, you get 1. And again, if you sum it only over the p direction or only over the q direction, then you get the probability density in the other direction. But as before, the Wigner function is not a probability distribution, as you may have guessed. And again, the reason is the same, that it can take negative values. But remarkably, in this case, quantum information theory provides a very beautiful interpretation of what the negativity of this discrete Wigner function means in terms of what you might at least heuristically think of as the complexity of classical simulation. So at a heuristic level, as I was saying, any circuit which involves initializing to a Wigner positive state, by which I mean a state whose Wigner function is everywhere non-negative. So any circuit which involves initializing to a Wigner positive state, followed by what you might think of as positivity preserving quantum operations or measurements, can be efficiently simulated on a classical computer. This is at least a heuristic version of what is called the Gottesman-Neal theorem in the information theory literature. And the underlying intuition here is that any circuit that's constructed out of such Wigner positivity preserving operations essentially reduces to classical stochastic or Markovian evolution in terms of the Wigner function representation. And therefore, it's essentially a classical process which can be simulated efficiently. This is sort of intuitive or the heuristic way of thinking about the negativity of or what the positivity of the Wigner function buys you. There is a much more precise way to formalize this in terms of what is called the resource theory of stabilizer quantum computation. And the idea here is that pure states with positive Wigner functions and convex combinations thereof are what are called stabilizer states. Actually, if you're familiar with the notion of stabilizer states, people often define them in a slightly different way in textbooks in terms of positive, +1 eigenstates of a certain subset of operators. But it turns out that this, the way I've defined a stabilizer states here is equivalent to that definition. So anyway, pure states with positive Wigner functions and convex combinations thereof are called, sorry, was there a question?
No, there was no question. Please continue.
Okay, thank you. So yeah, so pure states with positive Wigner functions and convex combinations thereof are called stabilizer states. And in this resource theory of stabilizer computation, one treats these kinds of stabilizer states as being free of cost. Then there's a subgroup of unitaries called Clifford unitaries, which is sort of a special subgroup of the unitary group, which maps stabilizer states to stabilizer states. And these are also regarded as being free. Okay, so okay, and in more generally, one is also allowed to bring ancillas, initialize to stabilizer states, perform joint Clifford unitaries, make measurements on the ancilla in the computational basis, and so on and so forth. There's a bunch of classical operations, what you might think of as classical operations, which are allowed and treated as thought of as being free in this group of stabilizer protocols. The idea being that this set of operations which we are treating as free essentially map Wigner positive states to Wigner positive states, and therefore leave you within a subspace, a very small subspace of the Hilbert space, where classical simulation becomes efficient. However, from what I've said, you might have guessed, and it's true, that stabilizer protocols are not universal. Indeed, they leave you within a very small subspace of the Hilbert space, where classical simulation is efficient. In order to achieve universality, meaning in order to be able to efficiently produce almost any state, one needs access to an additional resource, what you might think of as a resource. And these resource states are sometimes called magic states. The term magic was coined by Bravi and Kitaev and has since remained. So I'm just going to continue calling them magic states. Much like entanglement plays the role of a resource in the theory of quantum communication, where local operations and classical communication are treated as free, magic plays the role of a resource in the theory of stabilizer quantum computation, where stabilizer states and stabilizer operations are treated as free. So the resource theory of stabilizer computation or of magic is very much analogous to that of entanglement. It's a very similar structure, except what magic sort of tries to quantify for you is the difficulty or the complexity of classical simulation. Now, in order to come up with a precise quantifier of magic, one defines what is called a magic monotone. Again, this is very similar to entanglement theory, now applied to the theory of stabilizer quantum computation. But one defines a magic monotone, M, as any real valued non-negative function on density matrices, which vanishes on stabilizer states and is on average non-increasing under stabilizer protocols. The intuition here is that if you could find such a function, then it would never increase under stabilizer operations, and therefore you couldn't possibly add magic by you couldn't possibly add magic by doing a stabilizer protocol, more or less by definition, and therefore such a monotone would more or less be a useful or a faithful measure of the amount of magic. But more than that, having a magic monotone or a monotone in general at hand is very, very useful because it gives a precise operational, it has a precise operational meaning. Given such a monotone M, you can show pretty easily. It's not very hard, but I don't have the time to show it here. Given such a monotone M, you can show that there exists a stabilizer, if there exists a stabilizer protocol which converts an initial state rho naught to a final state rho with some probability P, then that probability P is necessarily upper bounded by M of rho naught divided by M of rho. Therefore, in order to obtain the desired state, one would need to repeat such a protocol at least M of rho divided by M of rho naught number of times. So if you imagine that rho naught is some initial fiducial state, then this monotone sort of quantifies the relative magic between rho naught and any other state in terms of, and more precisely, also bounds the probability of conversion between rho naught and rho by using stabilizer protocols. So for this reason, for the reasons that I just explained here, you could sort of think of a magic monotone as some measure of the complexity of preparing the state rho, the final state rho, using only stabilizer quantum operations. Yes.
But for some choice of rho and rho naught, can P be greater than 1? I mean the right hand sides.
Yes, it can be, and in that case, the bound is useless.
Okay, thank you.
Yeah, yeah. So the bound is only useful if M of that's a great question. I should have said the bound is only useful when M of rho is much greater than M of rho naught. Yes. Any other questions? Okay, maybe I move on. So then this discussion this was a sort of review of the theory of stabilizer quantum computation. But now having discussed all this, we come back to the discrete Wigner function. So let me for given a general state psi, and this doesn't, although I wrote it here for pure, as if it's a pure state, it doesn't have to be a pure state. Given a general density matrix psi, the negativity of the Wigner function, let me define that object as follows. You just take the absolute value of the Wigner function and you sum it over phase space, and just for good measure, you subtract a 1 from it. The reason to call this quantity the negativity is that if the Wigner function was everywhere positive or non-negative, the sum over the absolute value of the Wigner function would just be equal to the sum of the Wigner function, which is 1 because the Wigner function is normalized. And then when you subtract a 1 from it, you get 0. But if the Wigner function has negativity in it at any point in phase space, then this quantity is greater than 0. And therefore, the quantity defined in this equation is in some sense a measure of how much negativity is present in the Wigner function. Now, remarkably, the Wigner negativity defined up here turns out to be a magic monotone. Okay, so this gives the Wigner function and its negativity a very precise interpretation as, if you like, the stabilizer complexity, meaning the complexity of preparing a state through stabilizer protocols, or more intuitively, you can think of Wigner negativity as a measure of the complexity of classical simulation. This latter statement is more intuitive, and you have to take it with a little bit of care. There's a little asterisk here that I hope you can see, but it's morally speaking true. But you should take that with a little bit of care. Okay, so that concludes the first part of this talk, where I was just reviewing the Wigner function formalism in finite dimensional Hilbert spaces. I'm going to now move on to evaporating black holes, but are there any questions before that? Okay, so, okay, if there are no further questions. So as I said, the point of this talk is to apply some of this technology of the theory of stabilizer quantum computation to the context of evaporating black holes. And in particular, as we discussed, Wigner negativity is a very useful and, well, first of all, it's an operationally meaningful quantity. It quantifies the notion of classical simulation complexity, or stabilizer complexity. So the point of this talk was to apply this measure to the case of evaporating black holes, and see if we can learn something interesting from in this case. So what we are going to do is we are going to discuss a couple of toy models for evaporating black holes, where we can actually compute Wigner negativity pretty explicitly and see what we learn. So the first model that I'm going to discuss is what is called the West Coast model, or the Pennington-Schenkel Stanford-Yang model, the PSSY model, where one models an evaporating black hole by taking a set of black hole states psi sub I, which have end of the world branes behind their interiors. The label I on the black hole states is a semi-classical index, which you can think of as living on the end of the world brane. This is mostly in the context of JT gravity in a two-dimensional toy model for quantum gravity. And then one sort of writes down an entangled state between these end of the world brane states psi I and some set of orthonormal states of the radiation, which I'm just going to label with the same index I. So on the radiation side, these states I are orthogonal or orthonormal. There's some orthonormal basis of states, and one takes D of them and entangles them in this way with D number of end of the world brane states on the black hole side. Given that state, the reduced density matrix on the radiation is just given by this formula. This formula is just obtained by taking the state and tracing out the radiation and tracing out the black hole. Now, for small d, one can treat these states psi sub I as being approximately orthogonal. In fact, it's easy to check on the gravity side that these states psi sub I, which are labeled by the semi-classical index I, are orthogonal, but up to e to the minus s corrections, where s is the black hole entropy. So when d is much smaller than e to the s, it's a good approximation to treat these states psi I as being orthogonal. And in that case, this density matrix essentially becomes diagonal. And as a function of capital D, the entropy of this density matrix will essentially grow as log of capital D. However, when D becomes of order e to the s or larger, this approximation where we are treating the psi-i's as being approximately orthogonal is no longer a good approximation, and then one has to do a more careful calculation. And indeed, this calculation was done by PSSY, where they showed that when capital D becomes larger than e to the s, the entropy saturates to e to the s, and this is what sort of cuts off the naive semi-classical growth of entropy of the black hole radiation. The more explicit mechanism by which this happens in their context are what are called replica wormholes, which are a class of wormholes that one must include in the gravity path integral. I'll have more to say about this in the coming slides. But anyway, the point of this talk now, or the point now for us, is to try and compute the Wigner negativity of this reduced density matrix rho sub r using the rules of the gravitational path integral. In order to compute the Wigner function, one must choose an orthonormal basis for the radiation Hilbert space. I hope that you remember that when I was trying to define the discrete Wigner function, I began by telling you that you have to first make a choice of an ordered orthonormal basis. So that's what I'm talking about here. Even to begin the calculation, we must first choose a basis for the radiation Hilbert space. And in general, it is very much true that the Wigner negativity depends on the choice of basis. However, in our gravity calculation for the black hole, we are going to find that the answer that we get is universal and basis independent. I can explain a little bit more why that happens and what are the important, what is important to keep in mind while making that statement a little bit later. But if you're worried about the fact that we haven't really chosen a basis, then the point is that the negativity in this calculation turns out to be basis independent on the radiation. Anyway, so now we begin in earnest to do the calculation. So as you may remember, the Wigner function is just defined by the trace of the phase point operators with respect to the density matrix. So on the quantum mechanics side, what we are instructed to do is take the phase point operators, which I'm labeling here by this box, AKL, and contract it with the reduced density matrix on the radiation. If you, for a moment, ignore the pink and the red stuff, then that's what this slide, this diagram is trying to depict. The dotted lines are the sort of radiation indices. The solid blue line is the black hole index, and maybe the solid red line is the black hole index, and the dotted lines are the radiation indices. And what this is, ignoring the shaded pink region, what it is a calculation of the Wigner function, just the Wigner function, not its negativity at this point, just the Wigner function in gravity. Or more precisely in the quantum system, quantum mechanical system dual to gravity. Now, what gravity allows you to do is it allows you to calculate this thing from the gravitational path integral by just filling in the asymptotic boundary conditions, namely the red line over here, with all possible bulk topologies and correspondingly integrals over the bulk metric. So in this figure, I've sort of depicted the leading correction or the leading contribution to this calculation. And as you know, as many of you know, when you use the gravitational path integral, at least in the JT gravity context, what you're actually calculating is not the Wigner function in a particular quantum system, but more precisely an ensemble average of the Wigner function in an ensemble of quantum systems. So using the gravity path integral to calculate the Wigner function gives you an ensemble averaged calculation for the Wigner function. Okay, and then this calculation is not very hard to do. Essentially, what happens is that the bulk geometry is the two-dimensional black hole with an end-of-the-world brane behind it. That is the solid blue line over here. And because of the way semi-classical indices contract in this path integral, what you find is that you the answer up to an overall number is essentially proportional to trace of A. And if you just sort of calculate that, you get 1 by d squared. Okay. So what you find is that the averaged Wigner function, the ensemble averaged Wigner function, as per the rules of the gravitational path integral, is just 1 by d squared, independent of Q and P, and therefore is everywhere non-negative. Okay. However, one must be a little careful, because what we've done here is that we've calculated the averaged Wigner function, and we find that it's non-negative everywhere. But that doesn't necessarily mean that the Wigner function, the negativity of the Wigner function is vanishing, because what one should really be calculating is the ensemble average of the negativity, not the negativity of the ensemble average. Indeed, the ensemble average here is washing out all the negativity in the Wigner function. So what one must really calculate is the ensemble average of the negativity, namely the sum over Q comma P, the absolute value of the Wigner function, and the whole thing averaged. So the average sign here, the overline symbol here, I should say the absolute value sign in the Wigner function is inside the averaging, not outside. You may remember that I defined the negativity with a -1 in my previous discussion, but just for convenience, I'm dropping that -1 because it doesn't change anything. Okay, so now one wants to calculate this quantity using the gravitational path integral, but this is a slightly tricky business because of the absolute value. The gravitational path integral is quite good at calculating things like products and powers and stuff like that, but it's not so, it's a bit hard to calculate things like absolute values, which are non-analytic. And so one way around it, which I'm going to use for now, is the replica trick. Namely, what we will do is we will just calculate w to the power 2n for some integer n using the gravitational path integral, which it is good at doing, and then just analytically continue the result to n equals half. Okay, so you might think of this as some kind of replica trick for calculating Wigner negativity. There is a much more systematic way to do this calculation, which I'll allude to a little bit later, but for now, this is going to be good enough. The answers agree. So from the boundary point of view, what you're then left to calculate is this w to the 2n, or more precisely, the ensemble average over w to the 2n. And so from the boundary quantum mechanics point of view, what that looks like is just 2n copies of that density matrix that I showed you before, each one contracted with its own phase point operator. So the red lines here are like the black hole indices, the dotted blue lines are the radiation indices, and the A boxes are the phase point operators. So what this is just 2n copies, in this case n equals 3, but 2n copies of the Wigner function. And that's what we are expected to calculate using the gravitational path integral. Now, when capital D is much smaller than e to the s, where s is the black hole entropy, the dominant contribution turns out to be the completely disconnected diagram. Namely, each one of these black hole legs is just filled in independently by its own black hole geometry. And the end of the world branes cap off within each disconnected black hole geometry. It's not hard to see that what this is doing is just taking the averaged Wigner function and raising it to the power 2n, because each one of these blobs over here is just the averaged Wigner function that we discussed 2 slides back. So therefore, this calculation just tells you that the negativity is vanishing, or 1 in my convention, because remember that I neglected to subtract a 1 from here. Okay, so this is just the sort of boring answer that we got previously. But something changes when d becomes greater than e to the s. This is exactly the page point. When you cross the page point and d becomes much larger than e to the s, something more interesting happens, which is that now the dominant contribution is no longer these disconnected black hole saddles, but in fact the dominant contribution comes from pairwise connected wormholes. So here I've just displayed one particular example of a pairwise connected wormhole, where these, for instance, these two asymptotic black hole boundary conditions get connected by a geometry, and the end of the world branes sort of cross connect between them. And then when all such asymptotic boundaries get paired up using these kinds of wormholes. I've just shown one of them here, but you have to actually consider all possible pairings. They're all equally important. Now, when ordinarily you might think that this is not a very important contribution because it's subdominant in e to the s because of the way topology, the counting of the factors of e to the s works in using topology. Basically, there are 3 disks here where there were 6 disks here. And so this is subdominant in terms of e to the s counting. But what happens is that because of the way the radiation indices contract, in these diagrams you get trace, in the previous diagram, what you got was a trace of A, where the trace of the phase point operator. But, but in these diagrams, what you get is powers of trace of A square. And it turns out the trace of A square is D. So that gives you an enhancement. Okay. So while naively these kinds of connected diagrams might look like they are subdominant from e to the s counting, D counting tells you that they are actually dominant when D is much greater than e to the s. And then you can do a pretty simple analysis once you realize this fact. You get some formula using this pairwise connected wormhole contribution. You can calculate W to the 2n when D is much greater than e to the s, and you get some formula, and then you can just, that formula looks analytic in n, so you can take n to half, and you find that the negativity is exponentially large, where here S max is just log D. Roughly speaking, you can think of that as the coarse-grained entropy of the radiation, and S2 is the Renyi entropy, second Renyi entropy of the radiation after the page time. Okay. But since D is much greater than e to the s, this quantity here is exponentially large. Okay. So what one finds then, what we learn is that before the page point, the Wigner negativity of the radiation is close to 1 or close to 0, depending on how you define it. So the radiation system is classical in a sense. It's easy to simulate classically. It doesn't have a large stabilizer complexity, which is in keeping with our intuition that the radiation is thermal and looks like a thermal gas, and it's sort of classical. But beyond the page point, one finds that the negativity of the Wigner function is exponentially large, so the state is very hard to simulate classically, even though the averaged Wigner function continues to look classical. Now, that calculation was done by the replica trick, and you might have thought that that is a little too quick, but there's a much more systematic way of doing this analysis using sort of contour integral representation of the absolute value, namely this one. So what you can do is you can take this formula, then expand out the exponential of the W in a Taylor series, then calculate each one of the terms, which is simply W to some power, using the gravitational path integral at large D and large e to the s, and then resum what you get. And when you do that, you get a more precise formula. You get a more precise formula for the absolute value of the negativity, a slightly more complicated formula, but you can. It's not very hard to check that when D is much smaller than e to the s, this thing is close to 1, and when D is much greater than e to the s, it's close to square root of D by e to the s, as I was saying before. So this is the plot of the more precise formula for the negativity as a function of D, and we also checked this formula, which was derived analytically by doing some numerical calculations, and it matches pretty well. The red curve here is the replica trick answer after the page point. So at large values of D, this more precise formula approaches the replica trick answer, and at small values of D, it sort of goes to an order 1 constant, which is what we expected. In particular, it goes to 1. I mean 0 because we are plotting log of negativity here. So in summary, the radiation negativity has an order 1, the radiation density matrix has an order 1 negativity before page time, but an exponentially large negativity after page time. And what we would like to do is we would like to attribute this complexity after the page point to the fact that the entanglement wedge of the radiation includes an island region in the black hole interior, but I'll have more to say about that in a few slides. We also did this kind of a calculation in a more dynamical model of black hole evaporation, where we took some state of a black hole and some state of the radiation, both classical at t equals 0, and then coupled them together with a joint unitary transformation of this type, where O sub b and O sub r are taken to be random matrices from GUE. And in that case as well, what we find is that the negativity has at early times, just after the coupling is initiated, the negativity shows a sharp rise or a sharp jump, which you can think of as a negativity shock for the radiation. But then at late times, it sort of decays and saturates to a late time value. And what we found was that this late time value for the saturation of the negativity was precisely the same value that was obtained in the PSSY model. So that was another calculation in which we were able to confirm that the negativity saturates to an order 1 value well before page point, but to an exponentially large value after the page point. Okay, so in the last few minutes of this talk, I wanted to end by giving you a proposal for a geometric proposal for Wigner negativity in more general holographic states, at least in the ADS CFT context. But maybe I can pause briefly for any questions.
Yes, there's a question.
Yes.
Hi, Onkar. Why are
Hi.
the wormholes which were dominant only pairwise connected, and how about multiply connected wormholes?
Yeah, that's a good question. Yeah, that's a very good question. You can sort of justify that in the present calculation because what is secretly happening is that because the gravitational path integral is calculating an ensemble average, the negativity is turning out to be basis independent. That's sort of where the basis independence of the negativity comes from. And then because of that, you can actually just calculate, instead of picking a particular basis, you can just Haar average over all bases. And then you find that when you do that, it's a property of the Haar average that lands you on these pairwise connected wormholes. But I suspect that if one does a more refined calculation, where instead of taking the radiation density matrix in this language is a sort of, it's the system that we are looking at is a bipartite system, namely that of a black hole and a radiation. If you were to look at a multipartite system and trace out one of the legs and then consider a density matrix on, let's say, a 2-party or a 3-party subsystem and calculate the negativity with respect to some locally or some tensor factorized basis, then in that case, I suspect that you get more of these multiply connected wormholes, multi-boundary connected Euclidean wormholes. But that's some work in progress right now, so let me not say much more than that. Yeah.
Sorry, one more question.
Sure.
Are there any measures of magic which are basis independent? Are they easy to compute in
Yeah.
holography?
Yes. So, I mean, there are a few ways of making magic basis independent. The way it ended up being basis independent in the present context is just the fact that the gravitational path integral was calculating an ensemble average, and that sort of made it basis independent. Another way in which you can make things basis independent by hand, if you like, is just to pick a local basis and then average over all possible choice of local bases. So That also gives you basis independent answers. And so for instance, if you have a bipartite density matrix, then you can pick some tensor factorized basis, but then you Haar average over each factor independently, so that the local choice of basis doesn't matter. And then that would naturally give you basis independent information theoretic quantities, which are related to multi-party entanglement measures. There are also other ways of defining basis independent magic quantities, but those are a couple.
Any other question?
Hi, Omkar. Just to understand what you did, to compute the average of negativity, you just had to compute the moments of these phase point operators, right? Is that what you did, or
That is correct, yes.
Okay.
Moments, meaning like moments of the expectation values of the phase point operators, like trace rho a to the power n. Okay, maybe I move on then. Okay, so in the last part of this talk, I wanted to make a geometric proposal for Wigner negativity in ADS-CFT. So as you all know, in ADS-CFT, the entanglement wedge reconstruction paradigm states that bulk degrees of freedom in the entanglement wedge of a given boundary subregion B are encoded in B. But when there exist multiple extremal surfaces dual to or homologous to a particular boundary subregion, the story sort of gets more interesting. In this case, operator reconstruction up to the outermost quantum extremal surface is known to be accomplished or can be accomplished by simple operators in B, which essentially generalizes the ideas of HKLL, but operators behind the outermost quantum extremal surface, but still within the entanglement wedge, do not admit a simple reconstruction of this type. And indeed, the Python's lunch conjecture is a statement about the complexity of reconstruction for such operators. So I've just given you an example. I've drawn a picture here to just give you an example where if you treat B, the subregion B in the boundary CFT as being two intervals, then when the intervals are small enough, then the entanglement wedge of B is just the shaded gray region on the left. And in this case, the outermost extremal surface is the true extremal surface. But when the region B becomes big enough, then the entanglement wedge becomes larger, and then the outermost extremal surface, namely the dotted blue lines, are not the true extremal surfaces. Indeed, the true extremal surface is the solid blue line, which lies behind the outermost extremal surface. So in this case, the region B prime is what you might call a Python's lunch, and then operators in B prime do not admit a simple reconstruction. Now, based on the analogy between the time reflection symmetric slicing ADS and tensor networks, it was conjectured by some authors that the reconstruction of operators in the Python's lunch region has an exponentially large complexity. In particular, the complexity of bulk reconstruction in the region B prime is exponential in the area of what they call the bulge surface, which you can think of as sort of the area of the maximal cross-section surface of the Python's lunch portion, and the area of the outermost extremal surface. So this conjecture was based on some intuition coming from tensor networks. And in our PSSY calculation, for instance, we found an exponentially large Wigner negativity precisely when the entanglement wedge developed a Python's lunch region, namely after the page point. And so if this interpretation is correct, namely that the presence of the Python's lunch portion in the entanglement wedge leads to a large Wigner negativity, then a similar phenomenon should also be present in more general holographic states. And so based on that and some intuition from tensor networks, which I'll explain in a moment, it's natural to propose a formula for the negativity in holographic states. And the formula is that the negativity is exponential in 1/8 g Newton times the area of the outer extremal surface minus the area of the true extremal surface. So this formula is kind of similar to the formula in the Python's lunch conjecture, except the difference in this case is between the area of the outer extremal surface, not the bulk surface, and the area of the true extremal surface. The reason that we believe this formula is correct is that the formula that we derived for the negativity in the PSSY model turns out to also be true more generally of random tensor network states, except with the difference that the S2 over here, the second Renyi entropy which appeared in the PSSY formula, gets replaced by the one Neumann entropy, because random tensor networks have a flat entanglement spectrum. So at least in random tensor network states, the same universal basis independent formula for the Wigner negativity applies, and if you in the limit where there's a Python's lunch in the tensor network, you get this formula for the negativity. So when the area of the outer extremal, when the outer extremal surface is the true extremal surface, then the negativity turns out to be order 1. Whereas when the outer extremal surface has a much larger area than the true extremal surface, then the negativity ends up being exponentially large, and in particular given by 1 by exponential of 1 by 8 g Newton times the area of the outer extremal surface minus the true extremal surface. So as a corollary of this formula, you also learn that whenever the entanglement wedge involves a Python's lunch, it automatically has a large stabilizer complexity. Okay, so that is by and large what I wanted to say in this talk. So let me quickly summarize in 1 minute. So I hope I've convinced you that the Wigner negativity is a computable notion of stabilizer complexity, and in particular, it has a nice operational meaning in terms of either stabilizer complexity or the complexity of classical simulation. We have tried to argue in this talk that the Wigner negativity is a useful tool in quantum gravity and in holography. We computed the Wigner negativity in the PSSY model for black hole evaporation and found that the negativity was order 1 before the page time, but became exponentially large after the page time. And we attributed this to the fact that after the page time, the entanglement wedge of the radiation develops a Python's lunch. Taking off from there, we proposed a more general geometric formula for negativity in holographic states, and argued that whenever the entanglement wedge involves a Python's lunch, the density matrix on the boundary automatically develops an exponential in 1 by g Newton negativity proportional, in particular, to the difference in the areas of the outermost and the true extremal surfaces. So that's all I have to say. Thank you.
Thanks a lot, Omkar, for a very nice talk. Other questions, comments? Yes, there's.
So I want to ask this increase in the exponential increase in the Wigner complexity after the page time, is it sudden or is it gradual?
It is, it's gradual. I can show you the formula. Yeah, it looks like this. It's not, if you want, I mean, it's not like a step. Yeah, it's not a step function. It's gradual, but it sort of starts the negativity deviates from being order 1 when d starts becoming order e to the s, and then it's sort of, yeah, I guess what I'm saying is that when d is much smaller than e to the s, it's close to 1. When d is much greater than e to the s, it's close to the exponentially large value, like this formula that I flashed before. But in between, when d is of order e to the s, that's when you have to be a little bit more careful to get the precise formula. So when d is much larger or much smaller than e to the s, then you can get away with the approximate replica trick formulas that I showed you. But when d is of order e to the s, then you have to be a little bit more careful and you have to do a more precise calculation, but we can do that and you can get a more precise formula, which was this one, which matches very nicely with the numerics as well.
Other questions?
Hello.
Yes.
Yeah. So the statement that this radiation has a large negativity, is it in
Yes.
tension with the statement that the radiation is also kind of thermal, or?
Yeah. So good. So thanks for that question. So it's not, because if you look at the average Wigner function, sorry, not the average of the negativity, but the average of the Wigner function itself,
Mm.
which I did at the beginning, then you find that the averaged Wigner function is always non-negative, no matter what value of d you are at, both before the page time and after the page time.
Yeah.
So on average, yeah.
So sure, it's non-negative, but maybe I'm just maybe let me rephrase my question. Like
Yes.
in some simple system, could you create a state which looks very thermal but still has
Yes.
a large negativity?
Yeah, I think that's what this is. That's what I was trying to say. So what this radiation system is doing is that on average it looks kind of thermal, because its average Wigner function is everywhere positive. But if you look at it in more detail, namely there are these exponentially small correlations between in the density matrix, which you can only get access to by actually calculating the average of the negativity. It's that when you do that, you see that actually the negativity is very large, even though the average density matrix looked very classical. So that's exactly what the system is doing.
Yeah, but for example, is there a qubit example where something like that?
Sure. I think you can easily cook up qubit examples like this.
Okay.
Yeah.
Okay.
Yeah.
Questions?
Hello.
Yes.
Yeah. So first question was like, can we think of the signal negativity as some complexity of reconstruction?
That's a good question. I don't. I mean, there are ways of using Wigner negativity to probe complexity of reconstruction, but I did not explain. I mean, I did not say that in this talk. So, but yeah, there are. In particular, you can assign a negativity to a quantum channel more generally. So here I was talking about the negativity of states and density matrices, but you can talk about the negativity of the Wigner function for quantum channels, and then you can apply that to your favorite channel of bulk reconstruction, let's say the PETS map or whatever, and talk about the negativity or the complexity of the complexity of reconstruction in that case. So yeah, it can very much be done. Yeah.
And then would it be similar to what we would get, let's say, by let's say a circuit complexity for that reconstruction, or would it be different in?
That's a good question. I don't know the connection between circuit complexity and this notion of complexity, because as I said, this notion of complexity is more tuned towards the complexity of classical simulation or the complexity of stabilizer quantum computation. I don't know whether there is a direct connection to circuit complexity, although that's a good question.
Thank you.
If there are no other questions, let's thank the speaker once more. Let's thank Onkar for a very nice talk.
Thank you. Thank you.
Okay, we'll move on to the next talk of this session. So our next speaker
Yes, can you hear me?
Yeah, we can hear you. So our next speaker is Alexander Jan, and so he'll be telling us about. So can you share your slides, please?
Yes.
He'll be telling us about, I think, some new developments in holographic error correcting codes. Yeah.
That is correct. Can you see my slides now?
Yeah, we can see your slides.
Excellent. All right. Well, first of all, thank you very much for inviting me. Sadly, I could not join you in person. I had some other urgent meetings to attend. So unfortunately, I could not join in person. But thanks to the organizers for making it possible to give this talk virtually. So I hope you will find it interesting. So the topic, as already said, is holographic quantum error correction. Now, my understanding is that most people in the audience have a background mostly in pure string theory, although, of course, the previous talk already went quite far into quantum information already. So I've structured this talk roughly to be 50% introduction and then 50% new stuff that I was involved in. So let me start. So I think you've seen the slide probably many, many times, or a version of it, which is, of course, the IDS-CFT correspondence. Now, the IDS-CFT correspondence, of course, has this nice geometrical soup can picture where you have a bulk ADS spacetime in which generally fields live on some exotically ADS background. And the dynamics within this bulk spacetime are mapped by this holographic map to a boundary conformal field theory. And in the simplest picture, of IDS-CFT, or the general picture, when we think about it, we think of having access to the entire boundary CFT, imparting us effectively access to the dynamics of the entire bulk as well through a reconstruction process, which I suppose was already mentioned a lot in the previous talk. So from this very general question emerged very quickly the more specific question: what if you have access only to a subregion of your boundary CFT? So a subregion A, which I've drawn here as a line, and the causal diamond on the boundary, which is eventually equivalent in terms of information content to this time slice region. Another question is, what can you reconstruct in the bulk? And this, of course, was already answered, as previously mentioned, by HKLL in 2005 and 2006. And the answer that they provided was the so-called causal wedge CA. So this is essentially the causal extension of this boundary diamond into the bulk. Oops, there we go. And they gave us a very specific way of reconstructing it, which is essentially a low complexity dictionary. Essentially, they told us that if you want to know a bulk local field at some local space-time point in the bulk, where it has support, then you can get there by just integrating or smearing over the boundary operators that live in this corresponding causal diamond. And you can do this essentially for any bulk local field which live anywhere in this causal wedge CA. So this is HKLL, but of course, this is just one way of reconstructing the bulk. And people sometimes started asking, well, is this really the maximal bulk region that you can reconstruct from A? Is there any way to reconstruct more? And of course, it's not the whole story, as you've already heard previously. The maximum region that you can reconstruct is not just the causal wedge, but the entanglement wedge, which I show here as curly A sub A, and sometimes it's simply called lowercase a. And this was a result that only came out in 2016 because it required quite a bit of quantum information theory. And why is it called the entanglement wedge? Well, you probably know, but I'll just tell you anyways. It's called the entanglement wedge because this wedge region of the bulk is bounded by the new Takayama surface gamma A. And the area of the surface, or in this case, it's essentially just a geodesic in 2+1 dimensional spacetime. The area of the surface in general tells you about the entanglement content of the subregion A in the CFT. And generally, this entanglement wedge, even though here on this picture it looks pretty much like a time slice cut of this picture, is generally much smaller than the entanglement wedge. And an example that, again, you saw on a slide just a few minutes ago is this case of A being composed of two disjoint subregions that are large. In this case, the causal wedge also consists of two disjoint bulk regions here and here. By the way, you can see my cursor, correct?
Yes, we can see your cursor. Yes.
Ah, excellent. So I'm not just, okay, that's good. So yeah, so in this case here, you have this causal wedge, which consists of these two disjoint parts. So this is an easily reconstructible region. But generally, if these regions are big enough, actually this RT surface, this Takayama surface, will take this form over here, where it connects the two endpoints of these two disjoint parts in this following way. So you have like this throat connecting both subregions. In that case, the entanglement wedge also contains a huge additional chunk of the bulk, which is much larger. And as you already know, this part is generally much harder to reconstruct than the causal wedge, but it is a maximal region that one can reconstruct given information on operators living in this boundary subregion. Now, a crucial property that emerges from this, which is crucial for understanding quantum error correction, is complementary recovery. So if you look at a local bulk field that only has local information around some point, then really the recoverability is exclusive. If you choose a boundary subregion A, then recoverability of this local bulk field will be possible either exclusively on region A or exclusively on region AC, which I denote as a complement region. And this is called complementary recovery because really there's only two choices of where to reconstruct, and they're exclusive. And from this property, one can actually derive a property of quantum error correction. And this arises first from noticing the following paradox, which is that if you look at this local bulk field and look at two subboundary regions that are overlapping, a region A and a region B, one finds that there exist these local fields that are contained both in the entanglement wedge of A and the entanglement wedge of B, which means that it can be reconstructed both on the boundary region A and on the boundary region B, but where the entanglement wedge of the overlap region on the boundary, so A and B, does not contain this local bulk field. And this creates an apparent paradox because if the information about this bulk field is somehow encoded in A and encoded in B, you would have naively expected that the information should be somehow stored in the overlap region, but it is not. And in fact, from this overlap region, you actually have absolutely no information about this local bulk field because, thanks to complementary recovery, the information has to be entirely encoded in the rest of the system. So what does this have to do with quantum error correction? Well, if you think about this whole region A and B together, then you have the following protection of this local information with regards to erasures. So now imagine you have this whole region A and B, and you erase either the part B without A or the part A without B. And in both cases, you will end up with a wedge that still contains information about your bulk local field phi of x. But if you erase both pieces, this one and this one, then you lose the information. And this is in fact very similar even to classical error correction. And so let me give you a little analog. So imagine you have a single bit that takes a state 0 or 1, and you want to encode it. And you encode it in the following way. Instead of choosing the bit 0 or 1, you choose two logical states, logical 0 and logical 1, which I denote by this bar over the number. And you encode them physically as just a tripling of the original bit. So 0 becomes 0, 0, 0, and 1 becomes 1, 1, 1. And now imagine you have these bits stored on some classical computer, and a bit flip error occurs. You know, some cosmic ray hits your computer, hits your memory, and one of the bits flips. So for example, the state 0, 0, 0 gets flipped to 0, 1, 0, where the second bit is affected. Now this can easily be corrected. If you look at 0, 1, 0, you know where it came from, what the original state was, so you can correct it. However, if two such bit flip errors occur, on two different bits of course, then you end up with a state where it's no longer clear what the original bit was that you started with, what the original logical state was. And really here we have the same situation. If you think of the region A without B, the overlap region, and the region B without A as your three physical bits, which you've encoded the information, you're allowed to lose access to one of them, so you can have an arbitrary operation on one of the three regions. But if you have an action on two of the regions, if you lose two of them, then you can no longer reconstruct your logical information. So in that sense, this geometry of the bulk to boundary map of ADS CFT gives you features of quantum error correction. Now, the analogy that I just gave you is, of course, for classical error correction, but quantum error correction has a very, very similar definition, which I will briefly tell you about now. So the idea of QEC, quantum error correction, is that you want to protect logical information against small, simple errors, so simple operators, low-weight operators, acting on your physical states in which you encode them. And mathematically, quantum error correction is really just an embedding of Hilbert spaces. You take a logical Hilbert space, and you take this as a subspace of your true physical Hilbert space, with an encoding isometry, usually called V, that maps each of your logical states that you wish to describe to an equivalent physical state in this larger Hilbert space. Now, how do you know whether this embedding actually gives you error correction? Well, there's a very specific way of defining error correction, which is through the so-called Miller-Flam condition. And it's defined as follows. You take a set of error operators E, so this is just a set of operators that you think of applying to your system that you consider your errors. And you say that this set of errors is correctable on a code space H logical, so the subspace of your logical states, if the following condition holds, which means that if any two errors, E1 and E2 from your error set, applied on the bra and cat basis states, again, any basis states that span your logical Hilbert space, preserve orthogonality. Now, this essentially is just a quantum statement of what I just told you about in the bit example, because it means if you apply a single error operator to one of your states, then you are able to reconstruct which operator you came from, so which state you came from, and you can undo the operation incurred by the error. So this is what we call a quantum error correcting code. And the holographic code is now very simply defined by just choosing this isometry, this logical to physical isometry V, as the bulk to boundary isometry of ADS CFT. In particular, we take this bulk Hilbert space to be restricted to low energy bulk states around semi-classical entity sitter. That means where we can still talk about this geometrical picture that I just told you about before. And now the exciting thing for practical quantum error correction is that we don't even have to stay in this continuum picture, but we can actually go to a discrete finite dimensional setting where we talk about qubits instead of continuous degrees of freedom, and we essentially get the same features. And the very useful tool to do this, as I previously mentioned, are tensor networks. So here's a picture of a tensor network. These bluish pentagons here are the tensors. Black and red legs correspond to the indices of the tensors, and connected legs are contractions. And we think of this as a representation or discretization of a time slice of ADS, so that it has the same geometrical properties I just showed you before. And you can think of this entire tensor network as defining your encoding map V. So you contract it all together, you end up with two sets of open legs, or two sets of indices. In the bulk, you have these red indices that define your bulk Hilbert space or logical Hilbert space in the code picture. And your open black legs on the boundary define your physical boundary Hilbert space. And so this V is just this tensor network map, mapping you from bulk to boundary states. Now, how do you actually build this tensor network? What kind of tensors do you choose? Well, the first proposal on how to do this came in 2015 in this so-called happy code model, a brilliant acronym from the authors Harlow, Pasterski, Preskill, and Yoshida. And what they found essentially is that there's a very nice construction by just choosing these individual tensors to have a very particular property called perfectness. You choose them to be perfect tensors. Now, each tensor itself has 6 indices, one bulk index that I've drawn here in red, and 5 physical indices that are contracted with its neighbors, except if you're on the boundary. And this property of perfectness just means that if you take an inner product over a subset of these indices, and the inner product, the subset includes at least half of the indices, then this inner product has to give you something proportional to the identity. So for example, here, if you contract this inner product sense over k, m, and n, then the result should be a delta function on the remaining pairs of indices. Now, this property is essentially equivalent to saying that if you think of this tensor as a map between qubits corresponding to each of these indices, then the tensor, in some sense, mediates maximal entanglement between any subset of indices that you can choose. Any bipartition of these indices will give you, this tensor will give you a map that maximally entangles both sides with each other. This is called a perfect tensor, and this is clearly a very restricted condition that only a few states fulfill. But it turns out that for this case of these 6-leg tensors, these perfect tensors actually have a very nice interpretation in quantum information theory and quantum error correction, which is that each tensor itself is a quantum error correcting code, the so-called 5-qubit Laflamme code, which has been discovered already in 1996, one of the earliest quantum error correcting codes to be discovered. And if you take these properties of this perfectness, and you look at how each individual tensor creates a linear map, you find exactly that you can reconstruct a discretized version of this entanglement reconstruct feature, which is that if you start having access to part of your boundary, a boundary subregion A, you can again recover all the logical information in this wedge-shaped region, and you end up at this cut corresponding to a Utah-Kainagi surface that even tells you about the entanglement of your boundary subregion. So this is really a discrete version of entanglement wedge reconstruction. And from that also follows complementary recovery and all these nice other recovery properties that I told you about. So this perfect tensor construction is quite nice. All right, but of course, this is not the whole story. And now I will tell you about new developments in this field that went beyond these previous insights that people had almost 10 years ago. So there are now many open questions that emerged from these initial constructions, and mainly there's really two directions. The first question is, how can we extend these models to really capture more detailed features of ADS CFT? And the second question is a more practical one. Can we actually use holographic codes for any kind of practical quantum error correction that can be applied, for example, on quantum computers? And in this talk, I want to present some recent work that really goes into both of these directions. So first, I will tell you about holographic codes that include finite n corrections. So we have small quantum gravity corrections in the bulk. Second, I will tell you about something called subsystem codes, which is a very important concept in quantum error correction, which helps us to understand certain features of holographic codes and makes them also more useful. And finally, mostly towards the second main question, I will tell you about fault-tolerant holographic code constructions, which are versions of holographic codes that are particularly suitable for practical quantum error correction on quantum computers. All right, so let me start with the first one. So what do I mean by finite n holographic codes? Well, finite n essentially corresponds to having a non-zero G. So you can think of having back reactions in your bulk. And what that means is that your bulk to boundary map takes some more general forms than what I told you about earlier. And this idea of complementary recovery gets a bit more complicated. Why? Because your bulk state can now correspond to different geometries that can be in superposition. And what that means is that in each eigenspace of this geometry, your Yutaka-Hanagi surface can take a different shape. And so the corresponding entanglement wedges will look differently. So generally, you will have a map that maps a superposition of these geometries to a product of bulk subregions. Because, of course, on the boundary, there's no gravity. So on the boundary, everything is still quantum mechanics. And Daniel Harlow already found in 2016 that we should, in this more general setting, really think of the area of this Yutaka-Hanagi surface as an operator-valued quantity, not just a scalar value. And so the question arises, can we also build these qubit codes, these tensor network codes that reproduce this behavior? And the simplest way you might want to do this with stabilizer codes turns out to be not possible. This was something that Charles Tsao found in 2023. If you build a stabilizer quantum error correcting code, you will find that this area term always has a trivial spectrum. So all its eigenvalues are the same. So that seems that none of this behavior can be represented in stabilizer codes. But actually, there's a little loophole that we exploited, which is that you can still build holographic stabilizer codes where gamma A follows different geometries, but each of these geometries corresponds to the same constant area. So the spectrum is still trivial, but the geometries are not. And so I will show you now how this works, how this can be achieved. Well, this is achieved by a generalization of a tensor network that was originally introduced by Glenn Evenbley in 2017, and that we extended in 2023 into holographic codes that we call Evenbley codes because they're based on his original idea. And the idea is you add a very simple ingredient to this original construction. So in the original construction, you have a tensor network, and your tensors are implanted on a hyperbolic geometry. What you now do is, between every pair of tensors, you add another extra unitary. In some sense, you do a basis transformation between any pairs of legs before you do the contraction. And this simple extra ingredient actually allows you to get a code structure without having perfect tensors, because these perfect tensors are the reason why these more general holographic features do not appear. So in this combination, you get a new type of quantum error correcting code that's still an exact bulk to boundary code. It's also, in some instances, still a stabilizer code. So they're very easy to construct for us. They're very precise in some sense, and we can analyze them very easily. But they have slightly more general features. And we can see this if we try to do entanglement wedge reconstruction in both cases. If we are in one of these happy codes, entanglement reconstruction is always fixed. So if we start with the boundary region A, we're always going to reconstruct the same bulk region, no matter what bulk logical state we are in. So another way of saying this is that there is no state dependence. So we have these two fixed wedges. Whereas in these Evenbley codes, most of the bulk reconstruction will be fixed. But there's a small strip of tensors in the bulk, a small thin bulk region, where we can have state dependence. And where the dependence of depending on which bulk state we are in, depending what logical state we are in, we can get different reconstructions and different RT surfaces. And as I will show you now, these still obey this no-go theorem by Charles Zhao that the areas have to be the same and remain constant. So let me give you a very simple example of that. So this example, we have a region A and a region A complement. And here we have the entanglement wedge of A and the entanglement wedge of A complement, and a strip of 3 tensors where the reconstruction is indeterminate. Well, what do we find now? Well, if we take this logical qubit over here and project it onto a 0 state, and project this one onto a plus state, so in some sense we are taking now a subspace of the code space, we find that this qubit here in the center is now reconstructed on the left, so on this region A. However, if we swap these 2 projections and we project this one onto a plus state and this one onto a 0 state, then suddenly this logical qubit is reconstructed on the complement region. So really we found now that this code space can be decomposed into different subspaces that correspond to different bulk geometries and in which the reconstruction looks differently. And this really is an example of state dependence in holographic codes. But if you look carefully, you will find that this region gamma A here still cuts exactly through 4 legs. So 1, 2, 3, 4, and 1, 2, 3, 4. So the length of the RT surface is going to be the same, following this no-go theorem by Charles. All right, so let me move on to the second example of things that have recently occurred in the field of holographic quantum error correction. And that's the question of subsystem codes. So in holography, we generally consider codes generated from the full logical algebra. So we consider the whole bulk as our logical space, of course, up to like some semi-classical restriction. And these codes have a rate. Now, rate is just defined as the number of logical qubits divided over the number of physical qubits. And of course, for an exact code, the rate has to be smaller than 1. And so, for example, for this happy code example on a pentagonal hyperbolic tiling, a 4-5 tiling, you find this asymptotic rate as you keep adding infinitely layers of tensors, approaches 1 over square root of 5. Now, in general quantum error correction, however, things can be a bit more complicated because in general quantum error correction, you can apply gate fixing.
Sorry to interrupt.
What?
We have about
Sorry?
10 minutes left.
Oh, 10 minutes. Perfect. Yes, that's more than enough time. Thank you. All right. So in general quantum error correction, we can apply gauge fixing within our code space. So as I mentioned previously, the code space is a subspace of your physical Hilbert space. But generally, you can decompose your code space again as a product of your true logical space and a gauge Hilbert space. And this construction is called a subsystem code. Now, the choice of this gauge, the choice of which state you apply in this gauge sector, can greatly improve the quantum error correcting properties of the general code and protect the information in your logical space more strongly. And now it turns out that in holography, we actually have a very nice geometrical picture of this. So let's consider again one of these Evans codes. It has a rate of a square root of 3 over 2. You can calculate this exactly. So if you have infinitely many layers, you have 0.8666 logical qubits per each physical qubit that lives somewhere on the boundary. Now, this, of course, is only the rate if you consider all of your logical qubits to be part of your code and there is no gauge fixing. However, alternatively, you could choose to gauge fix some part of your bulk. So you only, for example, you only take the center of your bulk. You take a bunch of logical qubits. You consider those as your true logical qubits. And you fix the remaining ones by projecting them onto some state, onto some gauge state G. And now, depending on the state G, you consider how protected your logical information on the remaining region is. And of course, this gives you an asymptotically 0 rate because you have a finite number of logical qubits, and as you add infinitely many layers, you get infinitely many physical qubits. And what we now found is that there are even examples where you have a non-zero rate, so where you keep a certain fraction of these logical qubits. You can find codes that have a very important property in quantum error correction, which is called an error threshold. So you can choose states G that essentially filter out errors as they come from the physical layer on the boundary, as they sort of propagate into the bulk. And what an error threshold here means is that if your probability for an error for each physical qubit goes below a certain critical value, then applying more and more layers will successively reduce the probability of that error occurring onto a deeper layer. So if you have infinitely many layers, and any error below this error threshold rate will be completely filtered out by the time it reaches your logical so IR region of your bulk, so the deep bulk region, so to speak. And this is a generally desirable property in quantum error correction, where you try to build quantum error correcting codes this way that if you stack them on top of each other, so if you, here in this case, if you add layers over layers over layers, then you want errors below a certain threshold to be arbitrarily suppressed as you have arbitrarily many layers. And so this is something you can achieve with the right gauge, even for these codes here, these FMBL codes. All right, finally, since I don't have that much time left, let me go to the last recent development that we just published this year, which concerns fault tolerance. So there's another very fundamental theorem in quantum error correction, which is called the Easton-Nil theorem. And the Easton-Nil theorem tells you that if you have a quantum error correcting code and a set of logical operators L, so the logical operators you are allowed to apply, then there are two properties that cannot be fulfilled simultaneously for any simple quantum error correcting code. And the first one is transversality. Now, transversality means that if you apply any of these logical operators, you do not spread errors among the physical qubits. Meaning if you have an error acting on a single physical qubit, then you don't want the application of the logical operator to spread this error onto your other physical qubits, which of course would be very bad in practice, because then a single physical error could suddenly spread through your entire system and destroy your entire computation. And this property of errors not spreading is often called fault tolerance. Now, the second property that this is in tension with is universality. Now, universality means that if you repeatedly apply elements of this logical operator set, you can approximate any arbitrary logical unitary. Now, this, of course, you want if you have a code where you want to be able to do any arbitrary logical operation. Now, if you're familiar with classical circuits, for example, a universal classical logical set would be a NAND gate, a not AND gate. So if you combine not AND gates in an arbitrary fashion, you stack arbitrarily many of them together, you can create any bitwise operation on arbitrarily many bits. And so similarly, for Hilbert spaces, you can define universal logical operator sets that you can combine to approximate any arbitrary unitary by just applying arbitrarily many elements of this logical operator set. So these two are in tension by this Easton-Nil theorem. So the question is, do holographic codes allow for a way out of this? Do they have some way of breaking this theorem? And again, generally, this is not possible for these happy codes. It was already shown in 2021 by Sam Cree and company that this is impossible. And even slight generalizations of these happy codes will not do. And generally, you have this tension between universality and transversality represented through the geometry of happy codes. And actually, complementary recovery plays a very important role there. But we found just this year that for more general holographic codes, it is actually possible to combine these two features in a way that in some ways generalizes previous approaches that people in the quantum error correction community developed to essentially go around this Easton-Nil theorem. And how do you do this? Well, I'll just give you like a very brief idea of how this is achieved, which is by generalizing to tensor network codes that instead of being filled with the same tensor contracted over hyperbolic tiling, consists of at least two types of tensors that are still contracted onto a regular hyperbolic tiling, but now with alternating tiles. And the reason why this is possible, why you can achieve fault tolerance to this, is that it allows you to combine two individual so-called seed codes that correspond to each of the two types of tensors that have complementary error sets, complementary logical sets that in combination allow you to do a universal operation in a way that still allows you to contain the spread of errors through your system. And though this is very nice, we really do not quite understand what the implications for holography are. So this, of course, a model that was derived with practical QAC in mind. And the reason why this puzzles us is because at finite N holography, we would always expect that by just doing local boundary evolution, we should be able to describe essentially arbitrary local bulk evolution. So somehow we would expect that we would be able to apply universal logical unitaries in the bulk by doing something local on the boundary, which does not spread errors very much. So somehow something like this should be possible, but it is not clear what these constructions really mean for holography. All right, so with that, I've reached the end of my talk. So let me just give you a brief overview of the results. So as I said, we looked at holographic quantum error correcting codes and managed to extend them to model at least some features of finite N holography. Then we found that these codes can also have features of interest to practical quantum error correction. And so 3 examples of this are these error thresholds, that we can build codes that suppress errors below a certain probability. We can build codes with tunable rates, and where the features of this threshold, for example, are changing according to this rate. And we can even build protocols for logical fault tolerance, which might make them useful for practical quantum error correction. And really, I think the take-home message should be that there are very interesting and surprising connections between these 2 fields of, well, high energy theory, holography, and quantum error correction or quantum information on the other hand. So for example, we have bulk gauge fixing, which corresponds to this quantum error correction language to code rates. We have state dependence in the bulk, which on the boundary corresponds to a requirement of having non-stabilizer codes in the general case. And somehow having bulk inhomogeneity in our discretized models gives us or allows us to achieve fault tolerance in our quantum error correction protocol. So there are lots of open questions from this. The first one being, if you go to a really smaller n, where you go to more general quantum gravitational corrections in the bulk, we should expect quantum error correction to become approximate. So how exactly does this emerge? How does it look like? This is a hard question because approximate quantum error correction is generally hard, and we don't have good tools to study it. Second, can we also implement holographic codes on near-term devices? Now this, of course, incurs all sorts of practical questions about how these codes could be implemented, how you would build circuits, how you would actually detect and correct errors. And finally, is there also a quantum error correcting picture for this emerging field of de Sitter holography, where the encoding of information, I think, is still not completely understood, but looks somewhat different from ADS CFT. So is there something we can learn in the field of quantum error correction from these kind of holographic maps as well? And so with that, I want to thank you for your attention. And if you're new to this field of holographic codes and you would like to learn more, I've provided a very short list of introductory papers on this, shamelessly including my own from 2021. And so I will not be here in person to answer your questions. I believe Ayan is here in person, so you can certainly ask him, and yeah, he'll be happy to answer your questions, I'm sure. So again, thank you very much.
Thank you, Alexander, for a very nice talk. Questions and comments? Yes.
Thank you for a nice talk. This is a question on for the first part of your talk, I think, about this Evenblik codes.
Yes.
So there, I think there were some unitaries introduced on the links. So are these? So basically, when you construct these tensor networks, you generally use the maximally entangled state to to form this link. So now you just use different state, is it, or uniformly throughout this code, or are they dependent on where you are?
So yes, so exactly. So for these happy codes, so the thing that you want to do is, so you have a tensor network map, right? And the constraint that you want to have, of course, is that this map has to be isometric. So it has to, if you go from the bulk to the boundary and then you go back, you want to recover your logical information exactly. In order to achieve this happy construction, you essentially need your tensors to be perfect tensors, or almost perfect tensors. Otherwise, this reconstruction cannot work. So the constraint of having an exact boundary map essentially tells you that these tensors have to be perfect. Now, this is basically this insight of Glenn Evenbly in 2017, that if you have this extra unitary gauge essentially on every contraction, you could get away with slightly less entangled tensors. So your tensors do not have to be perfect. And the way this works is that instead of every single tensor being perfect, you require tensors in pairs to have certain isometry conditions where you're allowed to reconstruct information with essentially two tensors together acting as a single isometric map. And this allows you to still have an exact bulk to boundary map as a whole, but where each individual tensor is no longer perfect and no longer maximally entangling. And this actually has another interesting feature that I didn't mention yet, which was actually the original motivation for this construction by Glenn Evenbly, which was that he wanted to get these holographic tensor networks that have non-trivial correlation functions on the boundary. So where if you think of boundary two-point correlation functions, for example, he wanted those to be decaying as you move away your operators. and not just have a like a stepwise function where they're perfectly correlated and then just drop to 0 immediately, which is what happened for these happy codes. So this was the original motivation, and for that you also need these non-perfect tensors. So this is how this construction comes about.
Thank you.
Other questions?
Hello. Yeah, you can hear me, right?
Yes, I can hear you.
Yeah, so I had two questions. The first is in the happy code, the prescription to draw RT surface is basically some kind of greedy algorithm while cutting the lengths, right? And
Yes.
in your state dependent thing, I did not get what would be the prescription to draw the RT surface.
Yes, great question. Yeah, this is related to the previous question. Exactly, for the happy code, you have this greedy algorithm, where this property, exactly, so this property for the perfect tensors allows you to do reconstruction, right? If you have access, for example, to 3 physical boundary legs, you can reconstruct the logical leg and the other 2 physical ones, and this is your greedy step. And if you iterate this step, then you can recover your entire bulk. By just starting with these legs, you greedily recover your bulk, and then you end up as your RT surface. Now for these assembly codes, you have similar greedy steps, but they're a bit more complicated. So generally, if you have access to, for example, 4 legs of your tensors, you are able, if you have access to 3 physical legs, you are able to recover the 4th physical one and your logical leg. This is weaker than perfect because, well, perfect, here it sort of looks similar, but for the perfect tensor, you would want to have access to half your legs and then recover the others. For assembly codes, generally, if you only have access to n-1 physical legs, then you can recover the remainder and the logical one. This is a weaker condition. And this by itself will not be enough to get this greedy reconstruction. But then you have another step on top of that, which allows you that if 2 tensors are contracted, and you have access to 4 physical legs of this pair of contracted tensors, then you are able to recover the other 2 physical legs and the 2 logical legs. So you have a 4-to-4 unitary map that is emerging from pairs of tensors. So you have a bit of non-locality added to your reconstruction step, and you can sort of imagine that this is, in some sense, you go a little bit into this quantum gravity regime because you're now looking at your bulk information being a little bit like spread out, not just you recover not just on one logical qubit at each single tensor, but in some sense the information is a little bit spread out between pairs of logical qubits in the bulk. And that's how you get this residual bulk region that's exactly one strip of tensors.
Okay, thanks for the. And the other question I had was, so you in the theorem there's this term simple as a prefix QEC. So what's that condition?
Yeah, you meant for the Eastern-Nil theorem, right? So simple basically just means the way I defined codes previously. So the idea is if you have a single bulk to boundary map, or sorry, single logical to physical isometric map, and you measure errors by having a single round of so-called stabilizer measurements, then this sort of quantum error correcting code fulfills this theorem. And so, for example, one way to break this is by taking several quantum error correcting codes and sort of putting them in sequence with each other, and then iteratively running the quantum error correction step for each code. So you have like several codes that are somehow combined, which in some sense makes the code worse, but it allows you to circumvent the theorem. And something similar is also what we did for these heterogeneous codes. So really, to decode these in a fault-tolerant fashion, you start at the boundary and then you apply quantum error correction inwards. So you start with the outermost layer, and then you go one layer in, one layer in, one layer in, and you successively correct errors, and that's how you achieve this fault tolerance procedure.
Okay, thanks.
Other questions?
Thanks for your questions.
Okay, if there are no other questions, let's thank the speaker once more. All right, a couple of announcements from the organizers. So you'll have a tea break now, which will be followed by this public lecture. And there'll be a bus at 4:45, which will take you to the auditorium. So don't miss the bus.
স্যার লাইভ স্যার লাইভ को বন্ধ করবো